machine to recognize images, understand patterns, make prediction, and solve real-world problems almost like a human brain. That is the power of deep learning. Hello everyone and welcome back to Simplilearn. In this video, we will explore the complete beginner to practical journey of deep learning. We will understand how neural networks work, how machines learn from the data, and how frameworks like TensorFlow and PyTorch help us build real deep learning models. This topic is important because deep learning is behind many of today's most powerful AI applications, including image recognitions, speech assistance, recommendation systems, natural language processing, self-driving cars, and even generative AI. If you want to build a strong foundation in AI and machine learning, deep learning is one of the most important skills to learn. In this session, we will cover the basics of deep learning, artificial neurons, perceptrons, weights, activation function, forward progression, loss function, gradient descent, and backpropagation. We will also move into practical implementation using TensorFlow, Keras, and PyTorch. You will see how neural networks are built, trained, evaluated, and applied to real classification problems using datasets like fashion and a capstone-style projects. By the end of this video, you will understand how deep learning models learn, how training works, and how to start building your own neural networks using modern deep learning frameworks. Before we move ahead, let me quickly share you something exciting for anyone who wants to build a strong career in generative AI and machine learning. The ENICT Academy IIT Kanpur Professional Certificate course in Generative AI and Machine Learning is designed to help you learn the complete AI and ML skill set from Python, data science, machine learning, deep learning, and NLP to generative AI, prompt engineering, LLMs, computer vision, and reinforcement learning. The program includes live online classes, master classes designed by IIT Kanpur faculty, and practical exposure to popular tools like ChatGPT, Hugging Face, DALL-E, TensorFlow, Keras, Gradio, LangChain, OpenAI, and more. You'll also work on 15 plus hands-on projects covering real-world use cases like employee attrition prediction, loan default analysis, AI-powered HR assistance, text-to-design platforms, recommendation engines, sales forecasting, and deep learning applications. On completing the program, you'll receive a program completion certificate from ENICT Academy IIT Kanpur, along with official Microsoft course badges for eligible learning paths. So if you want to go beyond just using AI tools and actually understand how generative AI and machine learning solutions are built and applied in real-world business problems, this program is worth checking out. The link is given in the description box below and in the pinned comments. Go check it out. Before we continue, here's a quick question for you to answer. Which of the following is commonly used as an activation function in hidden layers of neural networks? Is it ReLU, HTML, SQL, or Excel? Let me know your answers in the comment section below. Let's get started.
I've always found that in teaching this several times in this program, getting to the deep learning is challenging. Doing the deep learning is challenging, but very rewarding. And I think a lot of people enjoy the topics here because they're very modern and very relevant to very advanced kind of modeling techniques. So a lot of people enjoy it, but it is going to be a little bit more challenging than what we've done so far. So, but that's okay. I think we can handle it. Um, so yeah, let's start with our introduction here. Okay. So what we're hoping to cover here are just the some of the background, mostly just background information about deep learning. So some of the achievements that have really happened in recent times. And we're talking, less than 10 years old, and some of these achievements that are have brought deep learning to the forefront and made it a really popular field. So we'll understand some of the applications and also some of the challenges of deep learning is not perfect. It has some drawbacks and some challenges that make it difficult at times. So we'll talk about that. And then we'll talk about some of the frameworks. Kind of already mentioned PyTorch and TensorFlow as the two main ones. Just talk about that a little bit. And then talk about what are the main steps of any deep learning project that we would want to follow. I think what you're going to see there is they mostly mimic the same kind of steps we were doing in machine learning, things like data preparation, then kind of building a model, training it, evaluating it on test data. Those kind of steps are mostly the same. It's just the details of those are going to be drastically different. That training process is going to be more involved, I think, with deep learning. Building the model is a little more hands-on with deep learning as well, because you're literally going to be architecting and constructing a neural network. It's much different than just instantiating a model from scikit-learn, which is pretty easy to do. There's going to be more hands-on work involved in building these deep learning networks that are going to be our models. So we'll talk about that process. Okay. All right. So let's start with just AI in general. So the reason to start here is just to see where deep learning kind of fits into the rest of the stuff that we've studied so far, such as machine learning, and historically, where has deep learning fit in? So I think we've seen this picture before early on in our machine learning and even data science courses, but here it is again, where we have AI as this pretty broad umbrella that is basically involving machines, so computers, trying to perform tasks that normally humans would have to do. And what we just got finished studying was machine learning, right? So machine learning is primarily having the machine learn from data how to make a decision, right? How to complete some task, whether that's prediction or maybe like an unsupervised case, doing things like compression, dimensionality reduction, or finding patterns and clusters. It's learning from data how to do that, right? That's machine learning broadly. Where deep learning fits in is really a subset of machine learning because we're still learning from data. We still are doing that. It's just we're using a specific tool to do that, which is going to be a neural network. So that's why in this diagram you see deep learning as kind of a circle embedded inside of the machine learning circle because it is kind of a sub field of machine learning. You're still learning from data. You're just doing it in a very particular way. So it's kind of like a specialization. That's why I said earlier, not everybody studies deep learning because you can get pretty far without deep learning. You still have this whole field of machine learning and you can still do a lot with that. But this is certainly kind of a specialization is drilling down into working with neural nets in particular as your model. It turns out that working with neural nets is really powerful for many reasons. And what we're going to see is that deep learning really unlocks working with specific types of data that we have not worked with so far. And, we already have a sense of that. Things like images, things like text, we really haven't worked with too much or at all. But deep learning really unlocks the ability to do that. So you can see that here. Yeah, there are. We've briefly talked about a couple of them. So inside of machine learning, that is not necessarily deep learning, would be something like RL. And it's not really a small circle, but probably another big one is, and it honestly it kind of overlaps with deep learning because you can use neural networks inside of reinforcement learning. So RL is short for reinforcement learning. I draw it overlap just to say that nowadays a lot of RL is done with deep learning ideas in terms of using neural nets, but it wasn't always that way. But yeah, there's RL, and then there's certainly like a lot of use cases of unsupervised learning inside of machine learning that does not use neural nets. So unsupervised learning, so things like clustering, uh, unsupervised learning, basically things that do not use neural nets but are still considered machine learning because you're still learning from data. Yeah, it's basically everything we covered in the last course. So even supervised learning that's not using neural nets is still in this bucket of machine learning. All right, so this is where we're studying deep learning. We're going to be in this course. This is where it kind of fits in. It's just a subset of machine learning because at the end of the day, we're still learning from data. It's just going to be using a particular type of model, which is a neural net. And more so than just a basic neural net, it's often going to be what we will term as a deep neural net, meaning it will be a pretty complex model that has a lot of layers to it, as we will see, but it is just a subset of machine learning. Okay. So historically, how has this evolved to get to that point? Well, we had the very first model of a neuron was proposed in 1943 by McCullough and Pitts. So they produced a paper kind of proposing a potential model of the brain and the neurons in the brain in 1943. So obviously a long time ago. And at the same time, some other things going on. We had the Turing test, which you may have heard of, basically testing the intelligent ability of a machine. And so we had that going on as well. Obviously, other things going on from the 40s to 50, but the big one that's relevant to deep learning is the very first proposed model of the neuron that was as old as 1943. It was more of an idea then. Obviously, they didn't have computing power to do anything with that. It was more just the idea. The concept was kind of as old as that of just modeling an actual neuron. It wasn't until the 50s that we see the actual term artificial intelligence being adopted, um, as well as the very first, very basic neural network model, the perceptron, that was invented in 1957. At the same time, we have some programming languages being invented to take advantage of machines. Not Python yet, obviously, but some older languages that end up inspiring the generation of Python later on, but still some high level languages that are invented. But this perceptron is really relevant. Actually, we're going to study perceptron in the next lesson as kind of the first model, the first basic neural network model that will propel, deeper and deeper networks built off of the idea of kind of a perceptron. So we'll talk about perceptron quite a bit. Okay, so then we go to the 60s. Are perceptrons still being used today? Perceptron itself is probably not used too much, but the idea of the perceptron is very present in so many think of it like the building block of any neural network was founded on the perceptron idea. So the perceptron itself, like just a single neuron. So we're going to learn about this, but the perceptron is basically the model of a single neuron. A single neuron, not quite used too much. It's very basic, but it forms the building block for nearly all neural networks that are around today. So I would say, yeah, I would say it's inspired. Pretty much any neural network is inspired by the perceptron. So it's a very, very important idea and concept, and we're going to spend some time talking about it and studying it as kind of our foundation for neural nets, and then we'll build on that by kind of stacking neural multiple perceptrons essentially together till we get a larger and larger network. Yeah, so the thing is, the idea's been around a long time, but there hasn't been the, computing power to really take advantage of it until recently. And when I say recently, probably last 15, 20 years, hasn't been, right? There hasn't been the computing power available to really unlock the capabilities of these and make larger and larger networks that can solve harder and harder problems. So we don't see that. We don't see that until recent. First job was a key punch operator. I think it's the don't know what key punch is. I think it's the like the binary the bit cards that fed the original kind of computers or older computers. And you had to literally punch out the bits. Also, this time in the 60s was the original chatbot, Eliza, 1966. Now, it's nothing like generative AI, right? This chatbot is all rules driven. So, nothing data driven, nothing like that. Certainly no neural net, nothing that we see today with these transformer based models and GPTs and such. But it is a chatbot in the sense of you can input text and then it can respond with text. Basically, it's all rule driven though, so it had to be pre-programmed how to respond to things. But that was, the first kind of AI chatbot. Okay, so then we see kind of a lull in the 70 to 80. Interest in AI drops significantly. Funding from government sources was insufficient. So there's kind of a lull period here. Now, that's not to say that there wasn't anything going on. There's still statistical research going on and advancements in the machine learning community, but nothing really relevant to neural networks at this period. But still, some of the developments in the statistics community are still relevant during this time uh, to machine learning, just not necessarily deep learning. But there's a rebound of that in the 80s. And you may be able to guess why, maybe due to geopolitical things going on in the 80s, like the Cold War. We see a revival in research and dedication to AI. We also start to see some communities develop that dedicated to the advancement of AI. So the Stanford hosts the inaugural conference, the AAI, which is kind of the inspiration for some of the conferences we see today, like NeurIPS and things like that. So in the 80s, there's kind of a revival. And then there's a kind of a interesting period of time in the late 90s. So kind of early, I would say even early 90s to early 2000s. In this period, we see a significant investment in AI from the big players like Facebook's and Netflix's of the world and Google, of course, Twitter. They start investing in AI quite a bit. 1997, we have the IBM Deep Blue, if you've ever heard of that, beat the world chess champion. So that was a really cool kind of AI achievement. But this period's called out here in particular because AI, its particular deep learning, had not advanced that far even by this point. However, there are some significant investments in this period that lead us to kind of where we are today. I would say two of them that are not necessarily listed here, but will be coming up, are where it says companies like Facebook, Twitter, and Netflix, and Google not mentioned, but should be there. They really start investing in AI. I want to call out Facebook and Google in particular because they build the frameworks that we use today. So Facebook invented PyTorch around this time, and Google invented TensorFlow around this time. They did those independently. Now they are mostly open sourced, so anybody can use them, but they were in-house tools to work with neural nets. Everybody wanted to work with neural nets. They had their own in-house tools, like PyTorch and TensorFlow, to kind of build and manage neural nets at the time. And this all started right around this period, 2006 or so. Not that long ago relative to history, only about 20 years, not that long ago. And we see kind of those foundational libraries being developed. And obviously, there's been a lot of advancements since then. So, in the period after that, this is kind of where the deep learning golden age is, like really the 2010s onward. 2012 is called out here. We're going to talk about there's a really big event in 2012 that happens, which is the AlexNet convolutional net is published and studied. It's a really big computer vision model. So a lot of really amazing achievements from this period, really 2010s onward in deep learning. And it kind of coincides with hardware being more available, neural nets being more readily available with those frameworks being more mature and developed, like PyTorch and TensorFlow. More people have access to them. They're open sourced, so more people can work with them and really get their hands on it, including the research community. So there's a reason it kind of blows up in the 2010s onward and even today. It's so I'll tell you why. It's because a lot of generative AI is powered by the transformer, and the transformer was not developed really until 2017. So that's less than 10 years ago. But the computing power and data availability to work with something like a transformer has not caught up until really like the last 5 or so years. So that's why it's so recent. The model that they're all built off of is less than 10 years old, the transformer, but it's more like just other things like hardware and data availability we've caught up to that, and now we can have these really massive language models that power generative AI because compute power is relatively easy to manage, and data is pretty easy to get your hands on too. But that's what I'm saying. The model is not that old that powers it. All right, but a really good question. So what are some of our motivations for deep learning? So there's a number of topics that we're going to study. They're all listed here. We're going to start with the perceptron. We're going to talk about these topics later on that have to do with like the backpropagation, really having to deal with how to train a neural net. So we'll talk about how they get trained. We'll talk about the earliest model of a neuron, which is going to be the perceptron. So we'll certainly cover that. Then we can stack perceptrons together in what is known as a multi-layer perceptron. That's kind of the next level. That's kind of like a miniature deep neural net. It's not very deep, but it does have multiple layers to it. And then we have the kind of in more recent times, these very advanced networks like these that we're going to study, convolutions mainly being used for images, and recurrent neural networks mainly being used for text. So we're talking about the motivation. One of the primary motivations for talking about deep learning is really this idea that deep learning is going to unlock our ability to work with text data and our ability to work with image data. There are so many problems out there that work with this kind of data, which in the community is known as unstructured data, right? So far, we've really only done problems with structured data. And structured meaning that it's basically a matrix that has rows and columns with really well-defined features, right? That are rows and columns, like our housing data that has square footage and bedrooms and bathrooms. That's all very well structured. Text is not structured at all. It can be variable length. You can have paragraphs, you can have whole documents. It's unstructured. Images, same thing. They can be many different resolutions. They have a little bit more structure to them in the sense that they are matrices somewhat, right? They have rows and columns of pixels, but still they're considered unstructured data. Um, so neural nets and deep learning will unlock the ability to work with those. There's so many problems that work with images, like object detection, image recognition, and that extends to so many applications. And then working with text, obviously, generative AI working with text, or even doing things like sentiment analysis or language translation. A lot of things work with text. So we need these advanced neural nets to be able to deal with that kind of data. The models that we've studied so far just are not capable of working with that data very effectively at all, like logistic regressions or decision trees or even things like an XGBoost. They're going to struggle on that unstructured data. They're not really going to be able to process it. Neural net, on the other hand, is going to be able to. That's one of our motivations for studying it, is it unlocks this whole set of applications for us that we couldn't do otherwise, namely working with text and image data, right? Okay. So some particular tasks there that we are going to study. So things like image recognition. Now, the very basic example that I probably have said before, but something like being able to predict if an image is a cat or a dog, or if an image is a cat, dog, a giraffe, or a wolf, or whatever it is, right? So image recognition tasks, and that really extends into so many applications like object detection. So working with images, really huge deal. We're going to devote a lot of time to it, but we really need neural nets to be able to do that effectively, as we are going to find out. Things with language, like understanding and processing human language, we have these transformers that do this so effectively, but it wasn't always that way, and it was nearly impossible to do with basic models. Just nearly impossible to understand language at the level that we see today. If you think about the amount of language understanding it takes to have these things like GPT and Claude and stuff, It's just immense. And they're really huge neural networks that are doing that, and they're learning against so much data. But we really need deep learning for that. And other applications, things like speech recognition. We haven't talked about it, but another type of unstructured data is audio, right? So audio data, being able to do things like recognition of audio, translation into text, that's a really hard problem, basically impossible without neural nets to be able to recognize speech and audio. Same thing with video. I know it's not listed here, but video, certainly unstructured. We need neural nets to be able to process those as well. So basically, any type of unstructured data, we're going to use neural nets to be able to process them. Yeah, a lot of neural nets. So speech recognition is powered by. We're going to cover this later, much later on in this course when we get into RNNs. A lot of things like Alexa devices, for instance, have been powered by RNN neural networks to basically recognize your commands, your voice commands. That's all neural network powered, right? To be able to recognize a voice command, translate that into some text, and then use that text for creating tasks or doing things or generating new text to be able to respond. Yeah, they're neural nets. So this speech recognition part is all neural net driven, namely RNNs, recurrent neural nets. And in modern times, RNN slash transformers, we see transformers kind of taking over this space as well. A lot of language stuff is being taken over by transformers, but traditionally they've been RNNs. Okay, so let me give you some breakthroughs. So, for example, we talked about this period of 2010s. One of the breakthroughs in deep learning was in 2012, the AlexNet paper, which I encourage you to go look up and read a little bit about. So the AlexNet is a type of convolutional neural net, and it introduced really the convolution as a preeminent operation on image data to be able to classify images into different categories. This network architecture using convolutions blew away the competition in the ImageNet challenge, which was a basically taking a bunch of images. So you can see here, like the training data has 1.2 million images, testing data has more, has 1.5 million images. Your goal is to categorize those images into 1,000 different categories. So think of it as like 1,000 different animals, not just cat or dog, but 1,000 different animals. And the best methods at the time, things like basic neural nets or maybe even like an XGBoost, were blown away by this convolutional net by more than 10%, which is astronomical amount in research of this at this kind of level. So this was a huge breakthrough. And what we see from there on is convolutions becoming kind of the default building block of anything working with images. So like object detection, it's all going to use convolutions. And it was all inspired by this AlexNet paper. And it was for the first time really like people realizing like, hey, these neural nets can really work on unstructured data very effectively because the methodologies to work on these images prior to this was to basically try to generate a bunch of structured features, which was not very effective. Going from like an image into a flattened vector and trying to generate features out of that to pass through like an XGBoost was the strategy, but it got surpassed immensely by this convolutional net. And then we see just an explosion of computer vision progress with people using convolutions. So one of the things we're going to study in this course is convolutions. They're really important for computer vision. If you're ever going to do anything with images, any kind of neural nets processing images is going to use convolutions in some fashion, right, in the architecture. So we'll devote some time to studying convolutions for sure. but this was a huge breakthrough at the time. And again, 2012, that's really not that long ago. It's hard to believe that this was 2012, and that is kind of a long time, somewhat, but really not really in historical terms. Yeah, please check those out. I think the AlexNet is really fascinating. Now, when you read that stuff, it may not make any sense to you right now. That's okay. It should make a lot more sense by the time we get into computer vision and start studying convolutions. I think it'll make a lot more sense. So maybe hold on to those. I encourage you to read them, but they may not make any sense right now because we haven't covered anything about neural nets really, or especially convolutions. So they probably won't make any sense to you, but um, I promise they will. They'll make a lot more sense by the time we go through and talk about convolutions. Okay. So, we'll talk about some more breakthroughs. That's just one of them. However, there are challenges that were encountered along the way. Obviously, like a lack of research funding was a big challenge. Probably bigger than that, definitely are these next two, which are data and hardware. These are the two things that stalled deep learning progress for a long time. Hardware, mostly because neural nets and their structure, this is something we're going to learn about, benefit immensely from advanced GPU hardware. It's primarily because the computations that a neural net does benefit a lot from the parallelization that a GPU can provide at the hardware level. And so only until recently have we had a lot of advancements in hardware such that GPUs are readily available. Wasn't always that case. And also it wasn't always the case that the Python code could take advantage of a GPU. But it can today pretty easily, with our frameworks like PyTorch and TensorFlow. They make it easy to take advantage of the GPU hardware. And so that's why we've seen an explosion in the last 10, 15 years because GPUs are more readily available and can be taken advantage of by the code. Same thing with data. Data is more readily available, right? So there's a lot more of it, a lot more, it's cheaper to store it, a lot easier to collect it. So it wasn't always that case. And what the case is with neural nets is you need a lot of data to train a neural net, more than what we've used so far for the structured data problems that we've dealt with. So the expensive nature of storing data and getting access to it was also prohibitive to a lot of progress in deep learning. But that's been kind of fixed, right? It's now a lot cheaper than ever, and consequently, we've seen a big explosion, right? Last 10, 15 years. Okay. All right. Any questions so far? Just some background, right? Just some background and a little historical context. Haven't gotten too much into it yet, but just again, this is the point of this first lesson, just more background information and historical context. And then we'll start studying the models of the neuron and working our way up to, more complex neural nets. Okay, let's talk about deep learning then, a little more in particular. So we just covered the fact that deep learning is really a subset of machine learning, focusing on using neural nets, and often what are going to be deep neural nets, which are going to be neural nets with a lot of layers or a lot of complex structure to it, to be able to learn from data. So learning from data is machine learning, right? But using neural nets to do that is deep learning. So that's where we're at, is using neural nets in particular, moving away from just basic machine learning into more specialization here with neural nets. So, what's nice about neural nets is that it can work with structured data, but as I've said, it can unlock the ability to work with unstructured data from many different domains, such as imagery, audio, video, text, to make predictions, usually. And this has unlocked a lot of progress in domains like computer vision, so object detection, self-driving cars, those kind of things. NLP, which is dealing with language, so language tasks like sentiment analysis, translation, text generation, even working with audio data like speech recognition. So a lot of progress in those fields. And deep learning is going to be able to surpass a lot of the machine learning techniques that we've seen because they have a very uncanny ability to learn complex patterns. Um, One of the things that gives that the ability is how complex the model is. But the other thing is it's going to use a lot of data. So it's going to have a lot of examples to go off of. It needs that in order to extract those complex patterns amongst imagery, text, audio, video, right? It's going to require a lot of data. So that's something we'll see when we start doing examples. Okay, so just to compare the two, so we're talking about deep learning and machine learning, and remember deep learning really being a subset of machine learning. Machine learning is a little bit more broad, where we have, unsupervised learning, supervised. A lot of the problems in deep learning are still supervised, meaning that there's still a label. Like if you have an image, there's still a label of what that image is. Is it a cat? Is it a dog? Is it a giraffe? Right? Or one of those thousand categories, like an ImageNet challenge. So there's still a supervised nature to a lot of these deep learning problems. It's just the model that we're using is now a deep neural net, right? Instead of a decision tree, instead of a random forest. And also, the data is inherently different, right? It's going to be imagery, it's going to be text, potentially audio, video. So we're moving away from structured data and really focusing on unstructured use cases with things like images and text. One of the things that's true that we've seen so far is, especially with machine learning course we just finished, we saw that it's really important to get those features right. We have to do some data prep to get our features correct, get rid of any null values, maybe even engineer some features like scaling it or adding two features together. It's really important to do that. What we're going to see with deep learning is it's not that important to do that. It's not that important to do feature engineering at all because the network's going to be so powerful at picking up on patterns from the original data, like the original images. We're not going to need to do a lot of manual feature engineering with deep learning. So that's going to be one kind of advantage here is not a lot of manual feature engineering. And that's actually the ImageNet challenge we just talked about with AlexNet, convolutional net winning that challenge. That was the thing everybody was doing was trying to do a lot of manual feature engineering so that they could use like a classical machine learning model like an XGBoost. But doing that wasn't as effective as just a really good neural net that can just extract patterns from the raw data very effectively using something like convolution. Okay, so deep learning, as I've said, really excels in those kind of tasks like image recognition, NLP, speech recognition. So we've talked about that. NLP, remember, is short for natural language processing. So you'll probably hear me use that word NLP, especially when we get to later on and we're studying things like transformers and RNNs. Those are just language tasks, right? So think of text, working with text, text generation, sentiment analysis, speech or language translation, I should say. So processing natural language, which is really text, right? For our use cases. Deep learning often requires really large data sets, so much more data than you see in a machine learning technique, and also more computational resources. So this is, think GPU. Most deep learning is going to benefit from using a GPU, whereas machine learning doesn't really use that at all. Like if you do a decision tree, an SVM, a logistic regression, you're not using the GPU at all. You don't need to. It'll still be pretty effective without that. And whereas deep learning, a lot of models will take forever. Just to give you some context, like the GPTs of the world, these transformers that are, neural network based, they train on data that's about the size. If you took all of the text from Wikipedia and more, so all of the text from Wikipedia, plus maybe all the text that would be in an encyclopedia collection, think of a data set that big as a prototypical training data set for something like a GPT, and think of thousands of GPUs working together. Even in that case, it can still take days to train a model. Days. Not minutes, not hours, days, because the models are so big and there's so much data being processed to train it. That is how much time it takes to train those kind of models. So there's substantial amount of resources, which is why there's so many news articles written about, NVIDIA and partnering with these generative AI companies like OpenAI and Microsoft, et cetera. So a lot of resources are needed. Now, for the networks we're going to build in the program, not so much. We'll still explore using a GPU, and we're actually going to practice using a GPU. We will have access to free GPUs in Colab, so that's really nice. Or even the Simplilearn lab environment has free access to GPUs. So we will practice using it, and it will benefit us for things like image recognition, working with imagery or RNNs or transformers even. They'll benefit us, but just as a rule of thumb, deep learning requires more data, more resources to train, computational resources. Well, so if you have a Windows machine, sure, you can use the NVIDIA GPUs. If you have a Mac, like a MacBook, even like one of the M1, M2, M3, M4 series, those have built-in GPU capabilities that we can take advantage of. So I'll share those resources with us when we get to building our models. But even if you have like one of those M1, M2, M3, M4 Macs with the silicon chips, they can use their internal GPU to train models. And I've done that before, and it's really nice. It speeds up the training a lot. We can also use Colab. So Colab offers free GPU access, which is nice. So we can use that too, and we will. So we'll practice that as when we get to it. Okay. And then finally, deep learning, we're going to be using neural nets that are potentially very deep in the sense that they have a lot of layers. So we haven't studied what a layer is yet. That's okay. Just think of a really complex model with a lot going on with it. That's going to be, way more complex than something like a decision tree or an SVM or random forest even. So that's what we're talking about here. To train deep learning, we often will use GPUs because they're going to be really effective. Most traditional machine learning methods that are not deep learning can get away with just using a CPU because they have very simple algorithms that are training that do not require using the underlying GPU resource that can really speed up deep learning. Okay. All right. So I wanted to take us through some of the successes that have been recent, some of the foundational kind of moments. And there's been growth in a lot of areas. So working with audio, computer vision, even reinforcement learning that has been powered by deep learning. Most reinforcement learning algorithms prior to deep learning were based on what are called kind of tabular methods, where they were keeping track of rewards and uh, data in a more structured format. But deep learning has since made a lot of progress in simplifying that and making it much more powerful and even in reinforcement learning. We'll talk about one of those cool moments there. So back to the AlexNet, we talked about this in 2012. This was the champion in the renowned ImageNet challenge. This is where, again, they used convolutions to really power learning imagery and being able to classify images. And this was so groundbreaking that a lot of moments in deep learning over the years have been referred to as kind of a ImageNet moment or AlexNet moment, because how big of a breakthrough this really was. So 2012, this convolutional model was kind of created. Now, we'll study this architecture later on of what this actually means, what these layers are doing, what is a convolution. We'll study all of that when we get into computer vision, but this was a huge breakthrough in working with image data. Then in 2013, we have a really important breakthrough of working with text known as the first kind of word embedding model, which is really, really important for where we are today because word embeddings play a really critical role in working with text. Because these are models that map text into numerical vectors, which is really critical for working with language modeling. And every transformer really has a word embedding at the very front of it to take raw text or tokens and essentially make those into a mathematical vector so the neural net can work with it. The very first model there that was a big breakthrough, this is 2013, was a model called Word to Vec, which you may have heard of. This was used for pre-processing text essentially to map it from raw word or tokens into vectors. So really, really critical for any kind of language model to do this. And so this has been around for a little bit longer than the language models, but this was a really important breakthrough for them for generative AI. So every generative AI like GPT, Claude, everybody has a word embedding model that's at the very front of their transformer based text generation model. So this is a huge breakthrough. Then we have the very first kind of language models known as sequence to sequence. Now, this is not using a transformer. So this is using RNNs to try to do NLP tasks like a language translation from German to English or French to English or English to French, whatever it is. And they tried to make NLP, so doing things like translation, language generation, sentiment analysis. They tried to make it a lot better, and it did. So at the time, RNNs were kind of the best language models around, and this is 2014, but they quickly get surpassed by transformers not too long after that. And that's where we are today. Everything is kind of transformer based, but at the time, RNNs were kind of the best for language. We will study RNNs later on in this course. Recurrent neural nets, RNNs, which are just a flavor of deep learning that uses a special architecture. So here it is again, just some different variations. There's a lot of different variations on the RNN architecture that attempts to predict, again, what word should be next in the sequence using the RNN. We do that very well today with transformers rather than RNNs. But at the time, these were the best around. Okay, right around the same time in the image generation field, we have GANs as a big breakthrough. So what are GANs? They are generative adversarial networks. These are models that generate images, fake images, and they do it through a competing adversarial networks that one is a generator that builds images, the other is a discriminator that's supposed to predict if that image is real or fake, and they kind of boost each other up so that the generator, by the time the training is done, is so effective at generating fake images, they kind of mirror real images. This actually led to the explosion in deep fakes. So deep fakes became a real issue. There's still issues today, but the first issue, the first time it was an issue was really when GANs were prominent. They were developed in 2014. So again, not too long ago. Most models that generate images today are actually not GANs. They're what are known as diffusion. So like Dolly and the Google Banana models that you can put in some text and generate an image. They're not GANs, but GANs were the earliest kind of image generation models that were out there and really effective. And some of them are still used today for sure, but majority of image generation models are what is known as diffusion, which we will study later on when we get into generative AI. But this was a huge breakthrough in using neural nets to generate images, right? That idea of generating images through neural nets, this was a big breakthrough here, 2014. Okay, and then on the reinforcement learning front, we have the AlphaGo developed by Google and its DeepMind team. First, kind of machine program to defeat a professional Go player. So if you've never heard of it, Go is a board game that is thought to be more complex than chess because the board is a lot bigger. It has more complex rules to it and more states in terms of the way that the pieces can be placed on the board. There's a lot more variability in the pieces in their positions on the board. So it's thought to be a more complex game, and it was mastered by reinforcement learning using deep learning. So this is the first time where deep learning really benefits a reinforcement learning model so much that it's able to beat professional Go players. This was a huge breakthrough. 2016, about 10 years ago, huge breakthrough, especially in reinforcement learning. This is where deep learning being able to be used in RL, big deal. It wasn't always that way. Okay, now to the big one, which is 2017. This is what I alluded to earlier with transformers. So this is where the very first transformer was created. We're going to study transformers later on in the course, but transformers changed everything when it came to language tasks. So I said RNNs were used prior to transformers around 2014 to do a lot of language tasks. Transformers come along a few years later and really revolutionize everything. And all of the generative models today, like ChatGPT, like Gemini, like Claude, they're all based on transformers. They are just massive extensions of the transformer idea. These large language models, these LLMs, are all based on the transformer idea. This was a huge breakthrough. I remember myself, I had just gotten into data science and machine learning in the industry right around here, like 2016. And I remember reading this paper at the time and how important it was. It was just a huge breakthrough. The attention is all you need. Highly encourage you to go and read that if you can. It's amazing. Now, it might not make sense yet by the time we get to Transformers, our lesson on Transformers later on in this course, probably make more sense, but really fascinating breakthrough. This is 2017, not that long ago, right? Really not that long ago. And not too long after this, we see the explosion in generative AI, right? Especially for text. Okay. So those are just to name a few. Obviously, there's been other advancements over the years, but those are some of the biggest. And what we've seen is deep learning has really come a long way. There's so many cool algorithms. There's also been an explosion in implementation because we have these frameworks readily available that are open source that anybody can use. So it's more and more people have access to these libraries and are able to develop their own algorithm in the community. So the research community has benefited a lot, and we've seen because of that an explosion in AI tools and AI models because of the ease of use of these deep learning frameworks and all the advancements that have come over the years. So a lot of cool libraries, a lot of efficient algorithms out there. And we're going to study those. Like we're going to study TensorFlow, we're going to study PyTorch so we can build our own networks. But the community has benefited greatly and has been part of the reason there's been an explosion recently is because of how easy it is to get access to those libraries and start building your own neural nets and trying things out. Really easy. Okay, so that brings us to an important question, which is why should we study deep learning? I said before that, it's an advanced topic. Not everybody studies it. It's a bit of a specialization within machine learning, and a lot of people just get through data science and machine learning and kind of stop there. So, what reason do we have as learners to actually study deep learning? We're going to talk about that. One of the key reasons is that deep learning, as I said before, unlocks problems across many different domains that are difficult but are necessary in those domains. So I'll give you one example is healthcare. There's so many image related examples in healthcare that are really vital that neural nets help with significantly. So think about analyzing images and image data of the body or of the brain, of potential diseases, those can be more readily analyzed with deep learning. And so healthcare has seen a lot of advancements in analyzing that kind of data with deep learning. Autonomous vehicles, of course, robotics, even like fraud detection. There's a lot of advanced methodology there, or even like time series forecasting has benefited from neural nets. So there's so many advanced use cases that neural nets can benefit because it can work with text, because it can work with image data. It just unlocks a lot of possibilities. So that's one reason is it just gives us many more problems we could potentially solve in different domains. It's worth studying it there. Another thing is we have so much more access, right? So GPUs are more readily available. Cloud environments have GPUs readily available. We're going to see that in Colab. Like we are going to be able to work with GPUs in Colab for free. But certainly, like if you're paying for it on a cloud provider like GCP, AWS, Azure, they all have GPUs that are relatively cheap, considering that we're actually using, advanced hardware there. So because of that, because it's so readily available, we have a better chance at utilizing deep learning more than ever because GPUs are so much easy to get your hands on than ever before. So it's not to say it's perfect. Like, we were joking earlier about the NVIDIA 5090. There are some physical hardware elements that are expensive and not easy to get your hands on, but like cloud resources for GPUs are readily available pretty easily. We're going to see that with Colab in particular. Another thing is, you know, GPUs. I forgot to mention this, but let me go back to this slide actually. Is one of the things that NVIDIA really powered was this CUDA framework. This is something that I mentioned a little bit earlier. This allows the Python library to interact with the GPU and be able to offload operations to it instead of having to keep everything on the CPU, which is much slower for the neural net operations that it's doing and its layers. Um, and so there was kind of this framework to interact Python with the hardware, this CUDA library. And because of that, the libraries that manage neural nets like PyTorch and TensorFlow have integrated the CUDA framework and have the ability to easily manipulate operations on the GPU, which makes working with neural nets so much easier. So you can take advantage of a GPU. That's just a long way of saying you can take advantage of GPU really, really easy with the modern frameworks. So with PyTorch, with TensorFlow, they can interact with the GPU so easily because of things like the CUDA framework. Makes it so much easier. So the CUDA is we don't ever see it. It's abstracted away with the framework like PyTorch or TensorFlow, and we're going to see that. We are going to build models in PyTorch and TensorFlow that will take advantage of the GPU. So we're going to see this directly, how easy it is to truly take advantage of that hardware, and it's going to speed up our operations a lot. It's going to make it so much faster to do that processing. Okay. So we just said GPUs play a critical role, and they're more readily available than ever. So that's another reason to kind of learn deep learning is we have access to these resources. And it's really because the GPU can do parallel math operations so efficiently, way more than a CPU. So they really we're going to see the effects of this when we do, especially working with computer vision and convolutional networks, working with a GPU then becomes almost necessary. It'll speed up operations so much. Like if we didn't use it, we'd be sitting there for minutes, maybe hour, waiting for the model to train. But if we use a GPU, it'll take seconds. It'll really speed it up a lot. Okay, one of the other reasons we've kind of hinted at this is just a low barrier to entry. So this is just to say, why not learn it? If you're going to learn machine learning, there's so many problems that use neural networks, And why not learn deep learning? Because it's never been easier to do. There's hardware available with GPUs more than ever. We talked about that. There's really extremely user-friendly frameworks like TensorFlow and PyTorch to help us build neural networks, and they're open source. So we can pip install it, get it into our environment, and start building neural nets and training them really, really easy. And we already have all the fundamentals we need to really understand model building, model training, model evaluation. We have all that fundamentals from working with Python, working with machine learning that we've already done, data science. So it's pretty easy to get into at this point. So why not? Right? It's just going to help us expand the breadth of our skills and problems that we can solve. And like I said, open sourcing these like TensorFlow and PyTorch was a big deal. It made it so much more accessible for the community to build their own neural nets. Prior to that, it was really limited to these big companies. You had to be in one of them in order to really start building neural nets. But now anybody can because these are free and open source, like TensorFlow and PyTorch. Okay. So another key reason, and you may be wondering this, especially because of generative AI taking over a lot of development these days, but still there's a need for trained deep learning experts and practitioners. So many companies still work with deep learning models and need deep learning expertise to be able to like tweak the training, set up the model, make the adjustments if the training doesn't go well, really understand the model. Even if you're using generative AI, you still need to have an understanding of how the modeling works and how it functions in order to effectively use it. So there's still a need for deep learning expertise, regardless of AI and generative AI. So it's a good opportunity. It's a good skill to have. I can say this, like beyond just having data science and machine learning experience going through this program, I think having the deep learning experience is just another really beneficial thing to have if you're trying to get into the industry. It really unlocks more potential for you, I think. And again, not everybody studies it, so you're getting a kind of advancement above the competition potentially by learning deep learning. All right, let's talk about some applications. So there's many, as I said before, there's many different fields that really benefit from deep learning and working with neural nets. So here's some of them, just a few, NLP being a huge one in terms of processing text, being able to understand human language. That's a big one. Self-driving cars using computer vision for object detection. That's something we'll talk about and study. Not only like detection of objects, but classification of them. So think of like, okay, here is an image, and inside of it, there's a pedestrian over here. There's a sign, like a stop sign. There's a tree over here. There's another car over here. Here's the road divider. So many objects that you can detect in the environment and really classify what they are, and that's all powered by deep learning. Same thing with audio processing, transforming speech to text. That's how we talked about earlier. That's how things like Alexa and those voice assistants really work. Translation of audio into text. And then manipulating images as well. So generative AI with images. So much of generative AI is all deep learning based. Transformers, diffusion models that generate images, GANs, all of these generate and manipulate images. They're all based on deep learning. So much of generative AI is deep learning based. Okay. Now, there are some limitations. One of the things to realize about deep learning, we've talked about it a lot so far, is a significant amount of data is usually required, meaning that deep learning may not be the best for tasks that have little amounts of data. And so, what is little? Usually, we're going to be dealing with in the tens of thousands, if not more. That's on the very low end of maybe images or text examples in order to train a moderately sized neural net, maybe even on the smaller end of a neural net. The bigger the neural net that we have, the more complex of a model we have, the more data we need. So this is like for the problems we've dealt with so far, throwing a neural net at it would likely be overkill and would not be effective. So it's not like we can just throw a neural net at our housing data and expect it to predict the price very effectively. It doesn't work like that. We would need a lot more data for that to be effective. Um, and we would probably need to tweak the neural net a good amount to get an effective model there. The neural nets have a tendency to overfit, so they need a lot of data to avoid that overfitting. They need a lot of examples, and that can be sometimes difficult to come by. The amount of data that's required to be collected. Generative AI like GPT requires so much data. That's why they're using people's chats to continuously build a data set so that it can keep training it. So much data is required there to train a really effective model, especially one that big. Just requires a huge data set. Let me give you an example. So consider, a model that's we've used this example before, right? Just differentiating or classifying cats and dogs. So this image is a cat, this image is a dog, and etc. In order to do this effectively, we would need many different images of cats and dogs, and likely those images would have to be of different size cats and dogs, different breeds, from different angles, potentially from different lighting and brightness of the image, many different variations on those, and they'd also have to be labeled, right? So it's still a supervised learning problem. So gathering that data set may be an expensive endeavor, may not be trivial. So that is kind of a cost burden of doing deep learning is the data. It's going to be a lot. You may need a really massive data set, and that can be difficult to acquire in some instances. Not all, but in some cases that may be difficult to acquire. So it is not a limitation so much as it is a caution that if you're going to use deep learning, you generally need a lot of data. And so you have to be prepared to collect a lot and process a lot in order to have an effective model. The other thing is hardware. We've talked about this now. It's again not necessarily a huge limitation because we do have access to GPUs, but you may need to pay for it. And you may need advanced hardware. The more complex your model is, the more you're going to benefit from, a more complex hardware like a GPU. It is more readily available than ever, but it doesn't mean that it's always going to be free and always going to be easy to acquire. So there may be some work there to use that or to acquire that hardware for a really complex model. Now, that being said, we are going to work with free GPUs for the examples we will do, but the examples we will do will be relatively moderately complex examples. They won't be massive models that would require a much more significant hardware investment to be able to run. So I used the example before, something like a ChatGPT is going to be using thousands of GPUs. That's a significant investment. If you're just using one for free from like Colab to do simple examples, that's one thing. But for a really big network, you're going to want to use a significant amount of GPU resources, which may be costly, right? So it's just something to be aware of. Okay, so one of the other limitations I mentioned earlier is that deep learning, because it's such a complex neural network, it can be susceptible to overfitting. In fact, they are very susceptible to overfitting, can easily overfit, especially if there's not a lot of training data. And that's just the nature of the neural net. It's so complex of a model that it can effectively memorize the training data very easily if you don't have guardrails in place. And that's one of the things we're going to study in that lesson on optimization of the training process. how to avoid overfitting. There's certainly things we can do, and we're going to study to prevent a neural net from overfitting, but they are very prone to it, naturally very prone to it because of their complexity, right? Remember we talked about overfitting. The more complex a model is, the more likely it is to overfit. The more basic a model is, the more likely it is to underfit. So neural nets fall in that category of being really complex. So they are very prone to overfitting. So something we have to kind of be on the lookout for. We'll study some techniques to help us overcome overfitting or prevent it. All right, another one that is very underrated and a lot of people don't think about when it comes to deep learning is the explainability of deep learning is very, very limited. So, when we studied machine learning and we did things like logistic regression or a decision tree, that was super explainable because like in logistic regression, you get coefficients on every feature, right? You get those betas. So we know exactly which features are important because they're going to have higher coefficients, right? And same thing with like a decision tree, you get an actual tree structure, so you know the path that leads to a prediction. And so they're really readily explainable. The issue with neural networks is they're often a black box. And what that means is you put data into it, you get a result out, but it's almost impossible to explain every little thing that happened that led to that prediction. Very difficult to explain with neural nets because they're such a complex model. They don't have a very natural way of having like a single coefficient. Most, to give you some context, most modern neural nets, like a GPT that's generating text, is going to have in the billions, tens of billions, hundreds of billions, if not trillion weights, which are, think of those betas. It's going to have like a trillion of those betas. So it's impossible to say what a single contribution to the prediction is. Now, this is an active area of research in the research community as people are trying to figure out good ways to break down how a neural net's making a prediction, but it still is pretty much not possible relative to other machine learning techniques. They're really complex models. You put something in, you get something out. It's hard to say what happens in between. You know the architecture, but it's hard to say what exactly contributes to that final result. It's hard to trace that back. So deep learning can be very difficult for explainability, and this actually has an effect in like regulated environments. Let's say you're in the finance industry and you're making like loan decisions based on a model. You probably don't want to use a neural net because it's going to be hard to explain how you predicted your like loan or not loan decision. You probably want to use something that is more explainable, like logistic regression or a decision tree, which would those you can directly see the contribution of their features, right? Leading to a prediction. Whereas a neural net, you're not going to be able to see that. It's just too complex of a model. Okay, so that's another kind of drawback of deep learning. Now, there on the opposite end of that, there are cases that we don't care about the explainability at all. So you think about like a self-driving car, we don't care the explanation of why this is a stop sign, why this is a pedestrian, why this object. We just want it to do that really fast. It needs to be real time, it needs to be really fast. We don't care about an explanation in that case, right? We just need it to make an accurate prediction. So there are certainly cases where we don't care about that, but in a lot of like regulated industries, you may care about that. If you're using a model to make some type of decision, you may care about the explainability of it, in which case neural nets are not ideal for that. Okay. Let's talk about some of the frameworks then that we will use. So these are going to be basically our libraries and tools to help us develop neural networks. Um, Basically, they allow us to design neural networks. They allow us to train them. They allow us to debug them, like how they're working or what kind of evaluation we're doing, if they're producing any bad results. And also for deployment. Now we won't really focus on deployment too much. That's going to be out of the scope for us a bit. We're going to focus on how to design and kind of train them. But these Python frameworks will allow us to build and train and evaluate neural networks. And this is huge. Like I said earlier, it wasn't always this case, right? You really had to be part of these large corporations that were doing this, like a Facebook or a Google, in order to have access to the tools to build neural networks. And now they're readily available, like PyTorch and TensorFlow. So the main frameworks that we're going to study are PyTorch and TensorFlow. Now, Keras is on this screen because what we're going to learn is Keras is really embedded into TensorFlow. It was actually developed by Google, the same people who made TensorFlow. It's really just a part of it. It's an interface to core TensorFlow. So when we hear the word Keras, we should really be thinking TensorFlow. It's the same thing. It's actually technically built on top of TensorFlow and allows us to interface with TensorFlow. But these were built by Google, and then PyTorch was built by Facebook, and now Meta, but at the time Facebook. And they are open source now, so they're widely available. And of course, we will learn how to use them to build neural nets and train them. They're both widely used. So both widely used in the community. Most people just have developed a preference for one or the other, just based on either what they originally learned to begin with or what they just naturally like. But the truth is, there's a lot of models out there, like even like an open source GPT that exists or Llama. They're developed in both frameworks. They have a version that's developed in PyTorch, they have a version that's developed in TensorFlow, and they do the same things. They mostly just have syntax differences. That's the only thing about it is they primarily just have syntax differences. But again, it's worth our time to study both because both are so widely used. And honestly, both are still maintained, even though they're open source. Both of these companies still maintain groups of developers that are maintaining these libraries. So there's still people within Google who actively manage TensorFlow, and there's still a group within Meta now that's actively managing PyTorch. And they do work on it all the time, but it's also open source, so contributions can come from anywhere really. But there's dedicated kind of people within each of these companies that are still maintaining these frameworks because they're so critical, right? They're so critical to doing deep learning and doing neural networks. So we're going to study them pretty deeply. So Keras, let me talk about Keras. It is going to be a interface in Python to the TensorFlow library. So TensorFlow was created first, and then Keras came along a couple years later to interact with TensorFlow. TensorFlow is kind of the underlying library that Keras is built on top of, and it's much more user friendly to manipulate and manage neural networks. So most people gravitate towards using the Keras library within TensorFlow to building. If they're going to use TensorFlow, they're going to be using Keras as the interface to TensorFlow. So it's just built on top of that by the same Google group who made TensorFlow, and it's the advantage of it rather than using the original TensorFlow is so much easier to get started with and build neural nets and so much easier to manage them. It's a really nice interface to TensorFlow. So when we build models in TensorFlow, we're really going to be using Keras, okay, as that kind of library on top of uh, TensorFlow to build neural nets. So we will study that. Is there an advantage of using Keras directly? Yeah, that's what it is. It's a really user-friendly interface. So it's designed to make building TensorFlow models so much easier. Because the truth of it is, like, the original TensorFlow is kind of ugly. It's kind of ugly and like messy to deal with. So people, when they're building TensorFlow models, gravitate towards using Keras as the interface to TensorFlow because like core TensorFlow is really messy. TensorFlow is, as we'll learn later, is basically a graph library for building like a tensor graph to mimic a neural network, a graph of computation. But Keras makes it so much easier to work with TensorFlow. So most people gravitate towards Keras. Then just usually you won't ever use the original TensorFlow unless you're maybe doing specific research that would require it. You're mostly always going to use Keras to build your models and train them. So that's what we'll do. Okay, so underlying Keras is TensorFlow, which came first from Google. It's obviously within Python. It's open source now, and this was the original library they built in-house to manipulate and manage neural networks. Keras came along as the interface to TensorFlow to make working with TensorFlow so much easier. So that's something that we'll see. And actually, TensorFlow has some really cool tools as part of it that we will work with later on. They have tools for like visualizing the training process, which is really nice. So we'll work with those. Okay. So on the other end of it is PyTorch that Facebook developed, now Meta, who still maintains it, but it has been open sourced. Same kind of thing. They were trying to work with neural networks and needed an in-house library to do that, and so they developed PyTorch at the time. And since it has been open source to the community. And it's very similar to TensorFlow, honestly. It has the same kind of features as TensorFlow. It's just a different syntax. And so that we're going to work with both. As I said, we're going to work with PyTorch and with TensorFlow in order to build models and train them. So, as I said, in the community, it's kind of a 50-50 split on which one people have a preference for. I personally like PyTorch. I actually learned TensorFlow first, but found myself liking PyTorch a little bit more. But it's preference. Honestly, it's preference, and I've seen it really just depends on what you like better, and then oftentimes like where you're working also determines. Maybe everybody has a standard for, okay, we're all going to use TensorFlow, or oh, we're all going to use PyTorch. You see things like that. But honestly, if you know one of them, you will be well versed in the other, and we are going to work with both. So we'll get exposure to both. Just syntax differences really between the two. Okay. So what I wanted to do was wrap up this introduction. So we've covered a lot in the introduction, but I wanted to wrap up specifically with the life cycle of a deep learning project, which I think we're going to see mostly overlaps with the same steps we were doing for machine learning. It's just there's going to be more, there's going to be more details that are involved here when we do training, when we do model building. But mostly the life cycle, this is the same as machine learning from a high level, right? It's mostly the same. We have some type of data collection and data prep phase, which is kind of what this is. So this is like our data prep that we do for machine learning. We're used to doing that first, usually. Now, prior to that, there may be some planning that has to be done to collect data. And in deep learning, that may actually be a significant amount of work to go out and gather a bunch of images or process a bunch of images or text data, and label it appropriately. That may actually be non-trivial, but all the examples we will do will assume we already have that data. But other than that, it's mostly the same steps in term at a high level of like once we have our data prepped, we go ahead and train, we build and train our model. Obviously, the details of doing this with a neural net are going to be much different than with a basic model like logistic regression or something. But once we train the model, we then evaluate, right? We evaluate it on some test data, evaluate and see how it performs. And the reason there's an arrow backwards is based on that evaluation, we may need to make some tweaks. So, at each one of these, it could be very iterative. In the training, like if we're underfitting, we may need to go back and revise our data. We may need to revise our model even. So it can certainly be iterative. And then after you have a model you're very satisfied with in the evaluation phase, that's where you can get into kind of deployment of it and then like monitoring it and maintaining it. These two things we're not going to be focused on too much because, again, it's going to be a little bit out of scope for us. We're mostly going to focus our attention on these two phases, training and evaluating of neural nets. Okay, but let's talk a little bit more about these steps. So the planning, as I said, this is where primarily whenever you're doing deep learning, this third bullet is really critical. So I would lean on this bullet as really critical as so planning really meaning what resources we're going to need in terms of data, what kind of data are we going to need, like images, text, what are we working with here? Not only data, but hardware. Like, can we get access to, like, are we going to need a GPU? Can we get access to that? Especially for deep learning, that's going to be really critical to know your resources ahead of time, and be able to have those available, especially the hardware, like a GPU. So usually there's some thought put into that from a planning perspective, in terms of the resources. Then there's the actual collection. So depending on the problem, this could be very different, right? We may be physically taking a bunch of images, we may be downloading a bunch of images or grabbing them from some database. We may have IoT sensors that we're collecting sensor data from, or like our self-driving cars taking a bunch of imagery, sensor data. So that could be different. Audio, audio or video, we could be collecting for examples. We need to collect that and we also need to label it, right? We need to have adequate labels and like think of the cat and dog images, right? We need to take every single image and provide a label with it, if it's a cat or it's a dog. And we also need to gather those images, right, in the first place. So there's going to be data prep that goes on here, no different than before. Okay, then we're going to talk about the training phase. So one of the things about the training phase is that's not really shown here, but is definitely a prerequisite, is we first need to build, obviously we need to build, I would say build slash architect the model, right? The neural net. So obviously we need to do that, and that will feed into the rest of the training process. Now, I will talk about this later. I'm not too concerned about these steps. These are just the steps of the training that we're going to learn. So this will really go backward and iterate through these steps. But training of a neural net is very unique. It basically involves sending a bunch of data through the network, figuring out what your error is, and then going back and updating the network. That's essentially what all these steps do. And then you iterate through that on your data over and over and over again until your network learns how to effectively make predictions. So it's a very iterative process, which is what makes it take a long time. You're going to iterate through all of your data and you're going to do that on a number of steps, which could be thousands of times that you're doing that. And it's really the same thing over and over again of, again, sending data through, computing how far off you are in the error, using that amount of error to go back and update all your model. Um, this process is where that gradient descent is going to come into play. So we kind of touched on this in the recommendations with that matrix factorization learning. We are going to study this in detail quite a bit more here in neural nets because that's really what's going to power neural net training is gradient descent. So again, these things I don't expect us to know right now. Just giving you a preview of the training is a lot more involved. There's there's a significant amount of computation involved here in like sending data through, generating predictions, computing error, updating all of our weights in our network, which could be billions and billions and billions of weights. So this backpropagation step could be significantly computationally intense in the gradient descent. And you're doing this many, many, many times in iteration across all your data. So it is significant the amount of resources that are spent in training a neural net. Okay. All right, so that's the training. And again, we're gonna have a lot more to say about these in future lessons. So let's put these terms on hold until we learn more about neural nets. We'll cover what forward propagation means, what loss means, what back propagation means. We're gonna study all of those. So a lot more to come on those. But for now, just think of the training phase as we have to iterate through having our network learn and adjust, learn and adjust, learn and adjust over and over and over again until it learns effectively. Okay. So as I said, the model goes through iterative performance evaluation essentially in terms of how much error it's generating. And so we keep an eye on that and continue to train it over the course of the training phase, which may be lots of iterations. And you can go backwards at this point. So based on the training, you may go back and adjust your model. You may go back and adjust your parameter, like your hyperparameters of the training, which is going to be a few. You may go back and adjust your data, which is what this slide's saying is that we may have to go back and collect more data. We may have to double check our labels. There could be a lot of reasons that we need to go back and make adjustments. It could be we change the architecture as well, like we actually change the model itself, the neural net. So going back to this diagram, there's a lot of iteration that happens. So, based on the training, we may go back and alter our data. We may alter our model based on the evaluation. We may go back and alter our training hyperparameters. A lot that we, may be modifying during the course of the training. So the training is going to be more intense, I think, in neural nets than what we've seen to this point. With usually what we've seen to this point is we just run a dot fit and everything happens for us, right? Especially with scikit-learn, right? We just run dot fit and boom, we have a model that's trained, like a logistic regression or a decision tree, right? Dot fit and it's done. This is not going to be as simple. There's going to be more setup, more moving parts involved, more computationally intense for sure to do the training. Okay, but either way we slice it, there's still going to be an evaluation phase, meaning that, even if we train, we still need to compute metrics to see if our model has performed well enough on the training data and on this testing data. So from a supervised learning perspective, that step will basically be the same as what we've seen before. Once we've trained the model, we're going to apply it to a holdout test set of data and decide whether or not the model is performing well. Is it overfitting? Is it underfitting? We can tell that on a test data just like we did with machine learning. That will not change. So what we're going to do is still have training data and a chunk of data that's probably smaller, but still test data that we will train the neural net on this and then apply it on this to evaluate, right? So we're still going to do that. Even we did that in machine learning, we're still going to do that here in deep learning. And the idea there is to make any adjustments that we may need based on the performance we're seeing. This is what we just said. So still an evaluation phase that's more or less the same, obviously just a different model this time. It's a neural net. Okay. Then if everything checks out there, we can deploy it. And there's many different ways to do that. Not going to get into them in this course, but suffice to say that once we have done the evaluation, it's kind of ready to go. And we would do a lot of kind of packaging up and infrastructure and things to kind of host the model. Many different ways to do that, but the goal here is to be able to actually use it to make predictions in some way, right? So maybe we're using it in like an object detection inside of a self-driving car or something. And of course, once you have that model out there, you're going to keep monitoring it and maybe make adjustments as you see the predictions coming in. So one of the goals that of even building the model in the first place is, of course, we're going to apply that to new data that has never been seen before. And that's where things can go off the rails. So you really got to monitor the performance as you are predicting on new data, right? And see how it's performing. So you may want to retrain it, make adjustments, maybe in the extreme, maybe you have to go back and change the model up. But you should be keeping an eye on the performance if you are using that model on new data. Okay. So, just to wrap up here on this introduction lesson, so that's everything we've covered so far is just background information about neural nets. So we have not talked about what a neural net is technically from like a math perspective. We haven't covered, how we train it. That's all to come. This is just background, right? So we've talked about deep learning being a specialized subset of machine learning that particularly focuses on using neural networks. We've talked about that. And we've also talked about it's really well suited for unstructured data like images, text, audio, video. So it's really, really good at that. However, it requires usually a lot of resources to function. So it requires a lot of data, a lot of computational power like a GPU to be effective. And then in terms of the life cycle, mostly follows the same steps as machine learning. It's just those steps are going to be different because we're dealing with a different kind of model, right? A neural net. Okay. All right. So we're going to start lesson three. So if you're following along, you want to go to those notes and go to lesson three. So we're going to start our study of neural nets, and particularly with the most basic kind, starting with the perceptron, really like a simple model of a neuron. And the idea is to build up from there into bigger and bigger neural nets. So what we're hoping to learn here is basically get into more of the details of how a neural net functions. So structure, functionality, including starting with the very basic perceptron and then expanding that a little bit into multi-layer perceptrons, and then talk about some of the advancements beyond there that are out there, like a deep neural net that extends that. Things like CNNs, RNNs we'll mention as well. And then talk about some of the activation functions that are present in neural nets. Now, it won't make sense this moment when I say activation functions, but they'll make more sense when we get into what's involved in a typical neural net, especially modeling a neuron. There's things like activation functions that are really critical. We'll study some of the most popular ones, like ReLU, sigmoid, softmax. And then we'll talk about some of the issues that can pop up during training in particular, things like vanishing, exploding gradients. Okay, so a lot to cover. Let's start with modeling the neuron, right? So let's start there. So obviously the models that we're going to build are networks of neurons, and we have to start with kind of the most basic model of a neuron. And it's very much inspired by the biological neuron that is within the brain. And so, not that we need to know all of these things about it from a biology perspective, but just to know that the model of the neuron is obviously based on how a biological neuron kind of functions. So from this perspective, there's inputs that are sent through. They go through the various nerve cells, and then out comes some type of output signal that flows through to the rest of the network. That's going to be very much how the neural networks will function, as there'll be kind of input data flow through this collection of neurons, and then out on the other end comes this output data. So we'll see that as we go. So in a biological neuron, there's these various components like the cell, a synapse being a connection between two cells, axons transmitting the output, dendrites receiving input. We're going to have equivalent components in the artificial neuron model that we are going to take a look at, such as the perceptron. So in the artificial neuron, we have a similar setup. Now, this is really, really critical to understand is that the artificial neuron is very much similar to a biological neuron, in which case we take all of the inputs and combine them together to generate some type of output. Now, the basic model of a neuron is going to do this really important process of taking the inputs to the neuron. So those could be, let's call them X1, X2, and X3, or more generically, however many there are, Xn, and then weighting those with different weights. Okay, weighting those with different weights, and then basically taking a weighted sum. So we have something like W1, X1 plus W2, X2 plus blah, 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 plus WN, XN. Now, what does this remind us of? Hopefully, this reminds us of something like a linear regression, right? It's very similar to that. That kind of does remind us of a linear regression. The difference is that the neuron is actually going to process this weighted sum through what's called an activation function. So every neuron is going to be activated or deactivated based on this flowing through some activation function. So you take that linear sum, you pass it through an activation, and often this activation, so this F is called an activation function, which gets its name from the biological neuron of, a neuron activating or not, like, or some people call that firing, right? A neuron fires, it activates. So this F is called an activation function, and essentially what the activation function is doing mathematically is applying some non-linear function. So it's typically the activation is going to be non-linear in nature. It's going to be some type of function that is non-linear. Okay. And it's going to it's going to be applied to that weighted sum of inputs to that neuron and then produce some sort of output, which is the activation value. It's producing some type of output. So in this case, the neuron model, this is the model of the neuron, is really just applying a activation to some weighted sum of inputs flowing into this neuron. So in this way, it's kind of like the biological neuron where we had input signals flowing in, and then some type of output signal coming out, right? It's basically that. And then what the neuron is doing a weighted sum through an activation. That's all that the neuron is doing the weighted sum, summation of weights times inputs. So you have your signals X, you generate an output, which is the weighted sum through the activation, and you get this output signal Y here. Training the model with lots of data determines. Yes, exactly. So during the course of doing the computations, the neuron will be active or not active. It's really not a matter of binary, like active or not active. It's more of what is this value that comes out of this activation function? That's the output, right? What is that value that comes out of the activation? This is this value here. It's that weighted sum of inputs through an activation is really the model of the neuron, right? So what is that output is really what we care about. The reason we care about that is because I want you to think about where this is headed in a network. So in a network of neurons, what we're going to have is a collection of these guys. So we're going to have many more neurons that would fill up a layer of neurons. So this is just one. So we'll have a lot of these guys, and each one of these neurons could produce a collection of outputs, right? They could produce a collection of outputs from their layer. And so, and then what happens is these outputs become the input to the next layer. The signals keep flowing, right? They go into the next set of neurons, right? And then what actually happens is you start to build this network. So not only does this go like this, but there's many more connections. So like this will become an input into this will be an input into this will be an input into this, and this will be an input into this. And same thing over here. Like this will be an input into this will be an input into this will be an input into this, and this would be an input into this. So everything from the previous layer, which is coming out of that neuron, all those neurons, will flow forward into the next layer of neurons and on and on and on, however many layers you might have. So you can have a significant amount of these layers of neurons in a really deep network. You might have lots and lots and lots of layers. So we're going to study that. We're going to study that as we go along, but that's really what we're building up to. Yeah, that's what we're building up to in a neural network. That's why it's called a network. It's really laid out in this structure of neurons sending data forward into the next layer of neurons and on and on and on until you eventually reach a final output. Now, I want to give you a basic use case of this neuron. I want to give you a basic use case of this output because it may be a little vague on what that output is. Most of the time for a neural network, this output will generally be a probability. So this will generally be some type of probability, especially for a classification. Probability will usually be a probability. So especially for a classification. So let's say we were predicting if an image like with a brain scan is cancer or not cancer, this would be like a probability of this would be like a probability of cancer that we generate, like in a binary case, right? Or spam or fraud, right? Generally represents some type of probability. It doesn't have to. Like if we're predicting a regression type of problem, like let's say we were predicting the price for our housing price data, this could be a price, right? This could be like a full value, some floating point number price, right? That could be possible. But it's a single output from this neuron that could represent, typically for classifications, be a probability, but could be a price like in a regression problem. Okay. So again, just to recap this, because I think this is really, really critical to understand moving forward in neural nets, is what does a neuron do in the network? Every neuron is processing a weighted sum of inputs, W2, X2, Wn, Xn. It's a weighted sum of inputs through an activation function f. That's what every neuron is doing, and that produces this output value from the neuron, which is that activated value, right? Some nonlinear function. And by the way, when we train the neural net, what we're actually learning during the training process, what gets updated during the training against real data are these weights. These weights get learned similar to when we do linear regression, right? We learn all those betas. Same thing here. We learn all of these weights. Now, do you guys see how if we have a really big network, there's going to be a lot of weights? So imagine we had a really big network with lots of neurons and they're sending data like there could take an image, which is an image could be like 1,000 by 1,000 resolution. That's so 1,000 by 1,000 is going to be our input. And then essentially what we're going to do is take those, pass them through this network and generate some type of classification of like cat or dog, some probability of like it might be cat, it might be dog, it might be giraffe. So maybe the output's actually three. So we have three final outputs, like cat probability, dog probability, or giraffe probability, but there can be a lot of weights because we're going to end up with this really massive network where everything is connected together, right? So there can be a lot of neurons, a lot of weights that are connecting layers to each other. So these networks can grow massively with the amount of weights that have to be learned. Now, in this simple model of a neuron, there's only three weights that we would have to learn. So pretty simple. But in like a chat GPT, there's 100 billion weights. That would be pretty conservative, actually. Their open source model, their transformer network open source GPT is around 20 billion weights. Okay. So just to give you an idea, there's 20 billion weights that would have to be learned. So you can see why substantial resources would be taken to train a model like that. There's going to be 20 billion of these things that have to be learned. Okay. So let me pause here. Any questions about this model of a neuron? So mathematically, model of a neuron, it's just taking a weighted sum of previous layer inputs, passing that through an activation to generate an output from a neuron. That's all it's doing. Okay, that idea is called the perceptron. That's basically the perceptron is taking a weighted sum, passing it through an activation. That's essentially the perceptron. We're going to study that next. But this is the most basic form of neural net computation you can possibly have. Just a single neuron that's taking a weighted sum of inputs and passing it through an activation. So these inputs could be features, they could be pixels in an image, right? Many different things. But you're just taking the weighted sum of those, passing it through some activation, and generating an output. One of the questions that we should have at this point is what is the activation? The activation is actually something that we can change. We can set what we want it to be depending on the problem. So some activations are going to be pretty popular in some cases. In other cases, we'll use other activations. We'll learn which activations. We'll actually talk about it later in the lesson, what this function usually looks like, in terms of taking that weighted sum, passing it through some type of function. That function might change from neuron to neuron in the network. But right now, we're just keeping it generic as some function, some nonlinear function that this weighted sum goes through. So in that case, it's different than a regression. A regression would just take this and be done with it, right? It would just take this weighted sum and that's it. That's the answer. But for a neuron, there's one extra component to that, which is taking that and passing it through a function, right? So a little bit more involved there. Okay. So everything I just said is kind of depicted here, where we are taking the weighted sum. Now there may also be a bias. I forgot to mention that. Similar to what we had in linear regression, right? There could also be a bias. So what we're really doing here is taking some function. So this may represent the function that we're doing, some step function, and generating an output, which kind of mimics the biological idea of an activation of the neuron, right? So if the signal is big enough, if it reaches some mathematical threshold, then the output signal is generated, meaning that neuron is activated, and there's some output that's generated. It's going to be the same here. We're going to be taking a weighted sum and then passing that through some activation F. So basically what we could do is think of this as some intermediate value Z is the weighted sum, and then we're taking the activation of that Z and generating an output value Y, right? Which the activation is going to be something like this. Maybe a nonlinear step function, maybe an exponential. It just depends. It depends on the situation. We're going to use different activations. So that is the artificial neuron model, weighted sum through an activation. That's actually it for the neuron. So some terminology in terms of the difference between the artificial model, weighted sum through an activation, and the actual biological model or the biological neuron. The nucleus is known as kind of the node, which is the node is just this. The node really is just like a graphical kind of node here that we could imagine as part of a network. So a network's going to have lots of nodes to it. We have our inputs, which are coming from usually a previous layer in the network. But in the case of a simple neuron like this, think of it like our features, right? Our features, like our bedrooms, bathrooms, square footage from our housing data, things like that. We have weights, which are kind of like our synapses in the biological sense, and then we have axon, which is the output. So there are kind of mirrors to the biological definitions. Okay. All right, so let's expand on this idea from a single neuron into a network of neurons. So a neural network then is just the extension of this idea where now we have interconnected layers of neurons, which is basically our computation model for the overall brain, basically a whole network of biological neurons working together. Each network consists of basically an input layer and an output layer, and then a bunch of potential layers in between. So you can have as many hidden layers. These layers between the input and output are known as hidden layers, and there might be many of them, potentially many of them. It depends on how deep the network is. A really deep network, depth is really based on how many hidden layers you have. So if you have very few of them, it's going to be a shallow network. If you have a lot of them, that's going to be a deep network. So this, each one of these blue circles is a neuron. So this is a neuron, and you have many neurons connected together, but every neuron's doing the same thing. It's taking this weighted sum of inputs and passing it through some activation and generating an output, right? That goes into the next layer. Does the activation of a neuron depend, need the inputs to be above a certain threshold? Biologically, yes, but in the neural network model, no. We just activation really just means taking the function and applying it to the weighted sum. That's all we mean. So it's not required to be above a certain threshold to be activated. We don't really care from a biological perspective, like activated or not. We care more about what is the output, which is this quantity. We care about this output, right? The weighted sum through the activation. It's a function. Yeah, the activation is really just a non-linear function. We care about the output. Exactly. We care about the output that's coming out of that neuron. Because what comes out of, does it make sense that what comes out of that neuron is really important for the future layers, right? Because like what comes out of that neuron is going to influence in the network, right? What we produce, because what we produce here flows into the next layer and on and on and on and on, right? So whatever we produce from one layer becomes the input to the next layer in the network. So it really matters what comes out of a neuron because that's going to be an input to the next layer. Really, really matters what the output is of every neuron. Yeah. Okay, so just to go back to this definition, again, the network is this whole thing. So it's all of these neurons connected together and a collection of neurons that are kind of forming an input prior to another layer. This is basically one layer, right? This is a layer of neurons, and when we build our networks, we can actually control how big that layer is. So how many neurons are in there? We can actually specify that when we architect our network. That's something we'll be able to do. And how many outputs do we want? So the outputs are usually going to be relative to how many classes are we predicting or how many outputs do we generally want. So in like let's say we're predicting between is this image a cat or a dog, we would only have these two outputs. So this would be probability of dog and this would be probability of cat, let's say. Or if it was like if we had a giraffe, then that would be a third member of the output layer. So I would need to generate a third for a giraffe, right? Or in the case of ImageNet, they needed, like in the ImageNet, remember they're predicting 1,000 different categories of items. So they need an output layer that has 1,000 neurons in it. So they need 1,000 neurons in the output because they're predicting 1,000 potential categories of images, right? So that output layer should match what your final prediction is going to be. So if you're predicting 10 categories, you need an output layer that has 10 neurons, which are going to represent the probabilities of each class. If you're predicting a regression, you only need one output, like the price or the temperature or whatever it is, right? You only need that one output. Or if it's binary, like fraud, not fraud, cancer, not cancer, you may only have one output, which is the probability of the like cancer or fraud or whatever it is. Okay. So how does a neural network process data and make a prediction? So it's kind of what I've been saying. Inputs go through the very beginning layer, and then every neuron that's in that layer receives inputs, assigns a weight, passes that through an activation to generate an output. So every neuron generates an output. And the outputs from that first layer are then forwarded to the second layer for processing in the same exact way. So you take a weighted sum of all those inputs from that layer, generate an output, pass that along to the next layer, and on and on and on. So this network, could have many, many, many layers. So there could be another layer here. That's another, what we would call hidden layer, which is anything between the input and output. And what we should realize is there's going to be contributions from every neuron that flow into each one of these neurons, right? So there's a lot of connections there. Every connection is weighted, right? There's a weight. Every connection contributes some weight to that neuron, and we process, as usual, we process a weighted sum through an activation of all of these guys. It's just that their inputs are going to come from this previous layer. Hopefully that makes sense. The inputs are going to come from the outputs of those neurons from the previous layer and on and on and on. So in this way, data we would say is kind of flowing forward or what we would call forward propagation. We forward propagate because it's literally like a propagation, like a signal propagation. So forward prop or forward propagation, because data is flowing from input all the way to the output, going through all these neurons. So that's how we make a prediction is we forward propagate inputs through the network and generate an output, right? So that's known as forward propagation, is sending data through, generating a prediction, which could be a prediction, could be probabilities, right? There's 80% probability this image is a cat, 20% probability this image is a dog. So therefore, our final prediction is cat, for instance. So this could be zero point 0.8, this could be zero point 0.2, and this would be zero point 0.8 probability it's a cat, and zero point 0.2 probability it's a dog, right? Something like that. And we're generating that by taking our image and flowing it through, forward propagating it through this network, generating these probabilities. That's just an example. Okay. Okay. So where we're going to start with, in terms of these networks, the very first one that we've actually already been studying is the perceptron. So the perceptron is exactly what we've been studying. It's just a model of a neuron, of a single neuron. We will graduate from that into multi-layers of neurons. So multi-layer perceptron. So more than one layer, more than one neuron for sure, but potentially more than one layer. And then we'll graduate from that into deeper networks that have many layers to them. And then once we do that, we'll be in a good position, especially once we learn how to train these guys. We'll spend a lot of effort on training these and optimizing that training process and building it within our code. like PyTorch or TensorFlow, we will then start to apply variations on these architectures that involve convolutions. So the neurons will go from simple weighted sum through an activation to a completely different type of computation that the neurons are doing, which would be like a convolution. So in the just to go back a step to put this in perspective, in this picture we're doing what we would call perceptron style calculations right now, meaning we're just taking a weighted sum, passing it through an activation, and sending that forward through the network. When we get into computer vision and working with text and RNNs, these neurons will now be way more advanced. The neurons will do things like convolve or do convolutions, which will be a very sophisticated computational operation that will require a GPU or else will take forever to train any models. So we will graduate from these very basic neurons. So right now we're just talking about a basic neuron that's doing this, weighted sum through an activation, and we'll graduate into convolutions, and then we'll graduate into RNNs, so doing recurrent calculations, which mimic kind of sequence memory for learning how to work with text sequences like sentences. So a lot to cover, obviously, before we get there. But right now, we're starting with the most basic model of a neuron, which is this perceptron kind of style calculation, just sending a weighted sum through an activation. That's it. But eventually, these neurons will become more and more complex, like doing convolutions for image data or doing RNNs for text data, and eventually transformers. So these neurons will do even more advanced things like attention in a transformer. Okay, it's a lot of exciting stuff. Talk about the the perceptron being the simplest type of network. That's where we're going to start. It's mainly used for binary prediction. So because like we can just produce that one output, which could represent a probability. So the perceptron was the simple model of the neuron, and it was originally used for binary classification problems. So that's where we'll start. Is the same thing, kind of for binary. And the perceptron's really only good if your data is linearly separable. We'll talk about what that means and why that's really only the case. Otherwise, we need to go to more advanced, like more layers. So the perceptron is going to be kind of limited in the sense that it's a single neuron. It's not a network. So it's not going to model too many problems that well. But it is the foundation for building on that and generating many, many layers of neurons that we will see for larger networks. So, and that's where we go with the MLP, which is multi-layer perceptron. Basically, multiple layers of these perceptrons, of these neuron models, and it can handle a little bit more complexity by learning nonlinear things because it has multiple layers, passing those inputs through these nonlinear activations, it can learn more effective. However, the MLP is not necessarily a deep network. So it's not going to have that many layers of perceptrons, maybe only a handful. It's not going to be that deep of a network. So itself will be kind of limited and it especially won't work well for like images or text. But for maybe certain problems like our housing data might work okay. But we'll certainly graduate from perceptron to multi-layer perceptron as a little bit bigger of a network. Okay. And then we'll work our way up to deep neural networks, which are going to have many hidden layers. So this we've had this image before. Here it is again, where a deep network's going to have this is the depth here. How many hidden layers do you have? A deep network's going to have many, many, many layers. Okay. So again, like modern generative AI neural networks are going to have thousands of layers, thousands of these hidden layers here. And notice how they're all connected because, the inputs the outputs of one layer become the inputs to the next layer. So you can see connections from each of these contributing to that neuron. This neuron is taking a weighted sum of those and then generating an output. And then there's connections from that output to every other neuron and on and on and on, right? So this big network, you get a certain number of outputs, that mimic what you're trying to predict. So again, there's like this could be 1,000 for the ImageNet problem. Let's say we're doing cat, dog, or giraffe. This would only be three. We're sending an image through, forward propagating it, generating these probabilities, which is our prediction. That's kind of how it works. Is it always left to right or can it bounce back? So it is left to right for the networks that we're talking about. The only time you get the circle-like is a recurrent neural net in RNN. That is so the circle you're describing is the essence of a recurrent connection. So it has the ability to do this, which is kind of like mimicking a memory of a sequence, sort of like going back and remembering what our previous inputs were. Otherwise, it's going to flow forward. It's going to be forward propagation left to right. But in an RNN, you would get connections like this, like you're thinking about. I think that's what you're talking about. Those recurrent connections. We would get those in an RNN. Yeah. So not, yeah, we won't have those yet, not until we get to RNNs later in the lessons. So, and then we're going to study this. We're going to work our way up to this. And then, as I said, once we learn how to build these guys, these deep neural networks, and really work with them in PyTorch and TensorFlow, we'll graduate to CNNs, the convolutional neural nets, which was this was motivated by mimicking kind of like the visual reception of the eyes and the cortex, using the convolutions to accomplish that. Convolution being a type of computation will basically replace those neurons with more advanced computation. And the visual reception is kind of mimicked by the convolution, allowing us inside of images to pick out things like objects, things like shapes, edges, lines, human features like faces, allowing us to learn those features of an image. So the convolutional net, again, this was that AlexNet 2012, really revolutionized being able to learn how to predict on image data. So we will learn about CNNs after we cover deep neural nets. IT stands for, I'm not sure what it means in this case, actually. Not 100% sure. Yeah, not 100% sure. I'd have to look that up. I think they're just different sections of the brain. I think they're short for like different sections that process like visuals. Okay. There we go. Yeah, they were different regions. Inferior temporal cortex. Nice. Okay. That makes sense to me. Okay. Okay, so then talking about RNNs really quick. So RNNs are a lot, networks that we're going to study later on in one of our lessons after we cover deep networks that will handle sequential data, right? So this is going to be things like language, because as I said, that's a sequence of words, one after the other in a sequence. So we will handle text with RNNs. Also, a very popular use case for RNNs, especially these days, is like forecasting. So time series data like sales or revenue day by day by day, you can build forecast with neural RNNs, because they're really effective at sequence learning, mainly because they allow for these recurrent connections. So they kind of have this short-term memory, which is effective for some language tasks and for forecasting. Unfortunately, that short-term memory is too short. It's not able to learn the type of context that we see in like a ChatGPT, for instance, with a very long prompt or a lot of text, which is what we see in transformers. So RNNs is kind of limited relative to transformers on language tasks. mainly because that short-term memory is just not nearly what it needs to be to generate text or do effective translations, things like that. So we're going to learn about that when we cover RNNs. One of the things that I mentioned that's certainly true is when we work with neural nets, we will be able to customize basically everything about that network. How many layers there are, how many neurons are within each layer, what those activation functions are. So you can think of like, this is going to be completely customizable from, it's same with input and output. How many inputs are there? How many outputs should there be? Like if I'm predicting 3 or 10 classes, or maybe two, or maybe just one in a binary case. Basically, everything about this is going to be customizable when we build our models. And that's just what we would call the architecture of the network, right? How many layers there are, how many neurons there are within each layer. And you can see that like when you have a deeper network with a lot of different layers here, so like this example on the right, you can see this is going to have a lot more, this has a lot more weights to it that have to be learned. So it's going to take more data. It's going to take longer to train a model like this because there's so many more connections, right? There's so many more weights that have to be learned during this process than if you had fewer layers. So that's a trade-off, right? Maybe you need more and more layers to learn a really complex problem. That may be necessary, but you're going to pay the price when it comes to computation because there's just going to be more weights that you have to keep track of, right? And learn. So this is something we'll see when we get into TensorFlow and PyTorch. We're going to see how do we build this? What's the code that generates this kind of network? That's something we need to learn, right? What's the code that does this? That's something we're going to learn. It's actually going to be relatively easy inside of TensorFlow and PyTorch. They make it easy because those libraries are so good at building it. So not only that, like we'll control the architecture, but we'll also control the training and the evaluation. So all of that we'll be able to set up inside of our PyTorch or TensorFlow when we get to that. Okay. So one of the things that's true about neural nets is they typically require more data, and there's that's kind of a graphic here to show that like if you have even a small neural network that's very shallow, so small being like number of hidden layers, it can still outperform traditional machine learning. So think of like logistic regression, decision tree, random forest, XGBoost. It can still outperform all of those. It's just going to require more data. And the larger the model, the more data that you're going to need. So you can kind of see that on this graph, right? The large neural network has a lot of potential to perform really, really well, but it needs the most data. The larger that the network is, the more data it needs to function properly. Now, these are relatively close, so just a shallow network isn't, and especially in the small data down here, it's not until this point that the even the shallow neural network kind of surpasses traditional machine learning. So again, for small data, it may be desirable to just continue to use traditional techniques like what we've studied. But as we get larger and larger data size, if we're working especially with unstructured like images, text, we're going to need neural nets. And, usually we'll start small and work our way up to larger neural networks if we need them, in terms of the architecture, which is how many layers do we have, how many neurons do we have, those kind of things. Okay. So the depth of the network, like how many layers we have, is often relative to the task. So if we're doing, working with images, like in an image classification or like object detection, or like in a transformer for a generative AI use case, that's going to be a much bigger network than maybe a simpler modeling task like predicting the price on our housing data where it's very structured, has a certain number of features to it, we may not need as deep of a network. So this is again where we will, you know, practice building networks and seeing when that makes a difference, like how much we change that architecture, how big of a difference does that make on our modeling problems. We're going to see that as we get into it. But here's a good, this is a good picture here on this one has two layers and it produces two outputs. So it takes four input features, produces two outputs, which could be probabilities, let's say. And you can see like these symbols are exactly what I've been describing as you take a weighted sum and you pass it through an activation. That's what the sigma and the F is. So the sigma is like the weighted sum of the inputs to that neuron. Every one of these circles is a neuron, right? So this is a neuron, this is a neuron, this is a neuron, 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 neuron. And technically, all these other circles are neurons as well. These are just output neurons, and these are input neurons. So they're not really doing much. They're just processing the input or holding the output. But they're going to be a weighted sum through an activation for all these neurons, right? Weighted sum through an activation. That's exactly what this is meant to represent. Sigma weighted sum through the F, through the activation. So let's talk about the perceptron as a model that is based on that neuron that we've studied so far, basically one and the same. So what do we mean by perceptron exactly? So I've been using the word perceptron a little bit. Let's actually define what it is. Essentially, it is a very basic neural network that is designed for binary classification. So think spam, not spam, right? Fraud, not fraud. So it has only two choices. And essentially, what it is the neuron such that it has a very simple activation. This is the activation right here, which is that you get a classification of one if your weighted sum times your inputs plus your bias is positive. So this has an activation function like this, which is basically just checking is your weighted sum uh, is your weighted sum times your inputs or weighted sum with your inputs greater than zero. So if it's greater than zero, we're going to output for that neuron a one. If it's negative or equal to zero, we're going to output zero. So it's in that way, it's just taking that model of the neuron. So you're taking all of your inputs, your x, x1, x2, x3, xn, however many you have, and you're feeding all of them into the single neuron, which is taking a weighted sum and taking a weighted sum of those inputs and then passing it through an activation, which is going to produce a zero or a one, right? A y, which is zero or one, depending on this activation, which is was it positive or was it zero or negative, right? Is essentially what this activation is. So it's a very simple model used for binary classification that's basically just a neuron, just a single neuron, taking that weighted sum, passing it through the activation. This is the activation function here, which is basically just checking, is it positive? You get a one output. Is it negative or zero? You get a zero output, right? For the neuron. That's all it is. So Perceptron, a very simple model that is based on this neuron calculation. The thing that's unique about the perceptron is it's just using this particular activation to see, do we get a one or a zero for a binary classification? So what's interesting about the perceptron is, it's using the basic idea of a neuron in every sense. It's taking a weighted sum through an activation. And what gets learned in this perceptron is the same thing that we've talked about learning in any neural network, which are these weights, right? These weights are going to be what gets updated through the training of the perceptrons. We need to talk about how does that happen? What kind of adjustments do you make? But essentially, the algorithm is going to learn those weights of that neuron, so that it can produce good outputs for your data, right? You want high quality predictions that line up to your like spam, not spam, fraud, not fraud kind of uh, predictions. So it's exactly like this picture. It's just the output again is going to be a binary 0 or a 1, and that activation is going to be particularly checking if it's positive or if it's negative or zero. So it's exactly this picture we just talked about from earlier with the neuron. For that reason, the weighted sum through an activation is often just referred to as a perceptron style computation, because that's essentially what it is. The perceptron is just using that particular activation of seeing if that weighted sum is positive. So it's that very particular activation. Again, I'll draw it here. We do this weighted sum, and we're passing it through the activation, and the activation is such that if this weighted sum is positive, then you get a one. If it's uh, else, basically you get a zero as the output, right? That's the activation function there. So the things that need to be updated and learned to have an effective perceptron is obviously these weights. These play a really critical role in determining what the output is going to be in any prediction. So again, what does this look like? It's very much similar to linear regression. We talked about this earlier. And for that reason, this model only works really effectively when the data is basically what we would call linearly separable. So if our classes, like let's say we just had two features, x1 and x2, if we had, let's say these red points belong to one class, and then these blue points, or let me draw them in green, belong to a different class over here. If we could draw a straight line through here and say everything on this side belongs to yes, and everything on this side belongs to no, those binary classes, then this model would be effective because it's essentially going to find that line and compare it to zero, essentially as if we shifted this line to be kind of at the origin, and we're checking like, does this result end up positive, meaning it's on this side of the line, or does it end up negative, meaning it's kind of on this side of the line, which would be a zero. So the perceptron's really only good to be used because it's so simple, just a single neuron. It's really only good in these situations where the data is kind of what we would call linearly separable, which is not always the case, right? That's typically not the case, which is why this model, we need to expand this to have many neurons with non-linear activations to model like real world problems, right? So again, the perceptron, we get a 0 or 1. We're going to adjust the weights during the training process. They get updated kind of in a gradient descent style calculation that happens to adjust those according to the error. And the perceptron really only works well when the data is linear separable, as we just talked about. Okay, so it's everything here that we just talked about, weighted sum through an activation. It's just this prediction is now, we know what it is for a perceptron. We know that this is going to be a 0 or a 1, and we know what this activation is going to be. It's the, checking if that weighted sum is positive or negative or zero. Okay. So we know what these components are now for the perceptron. So everything we've talked about is here. Nothing really changes except a particular activation for this binary case. And it's just a single neuron. So that's the other thing. We've been talking about a network of neurons. The perceptron is so basic, it's just a single neuron. All right, just a single one. It doesn't have a layer of multiple neurons. It's just a single one. So very basic. So the components there are, again, what we've been talking about. We have a set of inputs, we have a set of weights, we have a bias using for shifting which is important for checking relative to zero. We have a summation function that just takes the weighted sum, and then we have an activation, which is exactly what's producing our zero or one, right? The activation. So everything is there that we typically will have in any neuron, and certainly in a network of neurons, we're going to have lots of these guys. Okay. So the perceptron is a good model of a single neuron, in the sense that it takes a weighted sum, takes an activation, and produces an output. Now, what would happen with that output in a larger network is we know that data would flow forward to the next layer, right? We know that in a larger network. But in the perceptron, we really only just have this, right? We just have some weighted inputs going into that single neuron. But typically that data would flow forward in what we've said is forward propagation. Another word for this type of network where data only flows forward in a forward propagation manner is sometimes known as a feed forward network. So feed forward is basically just a network of perceptron neurons, right? That the perceptron being their computation is just a weighted sum through an activation, and it's just flowing forward. The output goes into the next layer, that output goes into the next layer, and on and on. So this is sometimes known as just a feed forward network because we do later on when we have RNNs, we'll have the ability to have a recurrent connection that goes backwards. But right now, these, especially with perceptron style calculations in these neurons, everything here is just what we call feed forward. Everything just forward propagates. Nothing has a kind of feedback connection yet until we get to RNNs. So this is another term you may hear is what we call a feed forward network. It's really just whenever you hear the word feed forward network, you should think of perceptron style computations that just flow forward, weighted sum through an activation going forward. That's all. Passing their output as the input to the next layer. So some of the features of this is that information only goes one way. It goes forward propagated through, never touches a node twice. It has no memory of the input, which is what we would have in an RNN. We would have memory because we care about sequences. We care about data that's prior to our current value that we're processing in the sequence. So the feed forward network, which is the most basic type, that perceptron style computation, data just flowing forward, basically has no ordering, no sequential memory, nothing like that, because it cannot go backwards. It's just all the data is flowing forward. Okay. So what we're going to do now is just look at the extension of the perceptron. So given that we have a perceptron, remember the perceptron is just a single neuron that has inputs. So we have inputs flowing into a single neuron, which is generating a single output. Right, that's perceptron, is just this. It's not even a network really. It's just inputs, weighted some of those going forward into an output. However, if we stack together multiple layers of these guys in terms of these neurons, we can generate what's called a multi-layer perceptron, which is starting to be a very basic network, right? It's not a full deep network in the sense there's not many layers, there's not many neurons. It's very limited. So multi-layer perceptron is designed to be pretty limited in terms of its structure. It's not a huge network. It's mainly just a small collection of maybe two, three, maybe four at most perceptron layers. And we generate an output which could be one or two or three outputs, depends on what we're trying to predict. But think of just stacking these neurons together in a simple collection of layers, and we're starting to build a network that is the multi-layer perceptron. Now, every neuron in the MLP, sometimes this is known as MLP, multi-layer perceptron. Every layer in this multi-layer perceptron is just the simple weighted sum through an activation. So this is still every single neuron still functions the same, weighted sum through the activation, right? It truly is that weighted sum through an activation. So nothing really changes there. Every neuron is like that. Okay, and all the data still feeds forward. It's just now we have multiple neurons and multiple layers, maybe two or three or four of them. Okay, so a perceptron is decent, except it fails at the separable things that are not linearly separable. So a very basic example people like to give of where the neuron model of a perceptron really falls apart is like a simple what's called an XOR, which is the exclusive OR operation between like two binary values, like -1 and 1, -1 and -1. If you take the exclusive OR between the two, you can see what their values are. Like the exclusive OR between -1 and -1 is still -1. The exclusive OR between -1 and 1 is 1. And then what's interesting is, this is not separable. You would have to, in order to separate these two classes, you would actually need two lines or basically something nonlinear, because you would basically need to draw something uh, kind of like this. Um, in order to separate the two, and say like everything on this side is belongs to one class and everything on this side belongs to another class. And that's highly nonlinear. So, and this is just one example of a function that would break the. You can think of many more. Like you could have, like let's say, going back to the example, we could draw circles here and here, and then draw the red ones. Like this one could be on this side, and this one could be on this side. And again, this makes it really difficult to draw a single line. Like you can't draw a single line through there and say, well, I can perfectly separate everything on this side and everything on this side. That's not going to be possible with a function like this, with data that's like this. Um, so that's just to say the perceptron is not perfect. It's going to struggle on data that is not linearly separable, which is what this means, meaning you can draw a perfect line or a hyperplane and all the data is on one side of it and all the other classes are on the other side of it for a binary classification. You most likely need a multi-layer perceptron because you need non-linearity, right? You need this kind of picture here in order to better separate it, which is non-linear. Okay. So that's just to say a single neuron by itself is kind of limited. That's where you need layers of neurons to more effectively model problems. That's all we're saying here. Okay, so I have a demo for you guys, and this is just going to use, so it turns out that perceptron, a single neuron, is actually available within scikit-learn. So we don't even need to use TensorFlow yet or PyTorch yet in order to just work with perceptron. So there's actually, just to show you that quickly, there is a demo. So this 3.04 demo inside of lesson 3 here, which let me go over to that and show you. So we'll do this demo. There should be a couple in lesson 3. We're going to do this 3.04. I'll give you a moment to pull it up. It should be in your lesson 3 materials. And there's also I believe a data set that you're going to need, which is the spam-based data set, which comes in the lesson 3 data sets. I can upload it here. But do you have this notebook from the lesson 3? You might need to download it from your reference materials. Okay, great. Okay. So let's practice building just a perceptron. Now again, would we typically use a perceptron? No, we would typically use a neural net that has more than just a perceptron, which is a single neuron. So, but the perceptron is an important building block to larger and deeper networks because that fundamental idea of taking a weighted sum through an activation is really critical and it shows up in a lot of networks. So It is an important building block, but by itself is not necessarily an effective model, especially in those cases we just saw where it's not linearly separable. But let's see how we use the perceptron here. What you can see is look at where it comes from. It's from scikit-learn in the linear model family. Now we've seen other things from there too, like the logistic regression, right? We've also seen linear regression there, but for classification, we've seen logistic regression from that linear model. Here is perceptron. It's considered to be in this linear model family because we're taking that weighted sum, which is linear, but then passing it through an activation, which is checking if it's positive or negative, right? So let's run that to do our imports. Okay. Let's load our data. So we're going to load that spam-based data. I do need to put it in here. Okay. So that's loaded, and we can check the head of it to see the first 5 rows, of course. So you can see there's some data. Now the spam is whether or not the email was spam or not. So it's all a bunch of data about the email. And then it has a classification category of spam, which is the last column, which is a 1 or a 0 for not spam, right? So this is a classification problem, and this data is just a bunch of features about different words. So for instance, this is a word frequency of the word all, the word address, the word make, the word hour, over, remove. So it's got a bunch of word frequency features, and then it's got some capitalization features, characters like the frequency of the pound symbol, frequency of the dollar symbol, frequency of exclamation point, um, parentheses. So it's got a bunch of features about text within the email. Okay. All right. So what we're going to do is just have a simple check here. If there are any nulls, we're just going to fill those with zeros. So obviously we could do a more robust check here. In fact, let's check. We know how to do data dot is null and then dot sum, so we can see that across all the columns. If we have any, doesn't look like we have any. So yeah, it looks like we don't have any nulls. So this should be relatively this shouldn't do anything essentially because this should fail. There are none, so this should be false. It shouldn't have to fill in anything. So that's fine. That's just going to produce our data. All right. And then this is the important part. This is the important part of grabbing our features and our labels, right? So this is grabbing our features and our labels, right? Features and labels. So this is grabbing every row and every column but the last one. That's what iloc does, right? Do you guys remember that? Iloc. For our data frame, this is grabbing every single row, but then every column but the last. So everything up until the last, which is the -1 index, that is all of our features. And this is grabbing the very last column, all rows, that's what the colon means, all rows, and then only the last column, that's the label, right? This is the spam label column is the last. And we saw that in this head of the data frame, right? Spam is the last one. Every other column before it is a feature. So we are just separating those out. Pretty typical. Separating those out. And then we're doing what we usually do with that is train test split, right? Pretty standard where we pass in our features and our labels and we do a train test split. And we can choose whatever test size. I think zero point 0.4 is a little big. We could lower that to maybe 0.3 or 0.25 or zero point 0.2. But I'll just leave it for that for now. Um, but this is our usual train test split. So nothing that interesting here, just generating our training data and our testing data. It's pretty standard, right? Nothing that out of the ordinary there for a supervised problem, which this certainly is, even though we're using Perceptron, which is just a neuron model to do it, still supervised. Let's scale our data. So we're going to scale all of our features. That's still something we're going to do here using this Perceptron, scaling all of our features here. So scaling our training features, scaling our test features. So we train both of those, or sorry, use both of those. And then we can fit our perceptron. So look how easy it is to initialize a perceptron. And basically the perceptron is just a single neuron model, right? So that's all it is. And it's going to use it's going to train. So this dot fit, I should call this out. This dot fit is going to train the neuron, which is just the perceptron, it's just a single neuron. It's going to train this by learning the weights through a gradient descent algorithm. So it's going to run a gradient descent in the background to learn what those optimal weights are. Now, we haven't studied gradient descent in detail. We will as part of like when we get to the part on coming up shortly on learning how to train neural nets. We're going to learn a lot about this because every single neural net trains through gradient descent algorithm, one way or the other. It does gradient descent. So it's not going to be any different for the perceptron because it is just a neuron. It's a very basic, it's not a network per se, but it is a neuron. The network is just a huge collection of neurons. So they're all going to train through gradient descent. So we'll learn more about that as we go. But this dot fit is going to run gradient descent on our features and our labels here for the training data. And the perceptron is going to adjust all of its weights according to this data. Okay, so we get a perceptron that has been fit. And then we can make predictions. So we can pass in our training data to get a collection of predictions for our training set. And then more importantly, we want to evaluate that on our test set. So we pass in our test features to our model and do dot predict. So far, this is just behaving like any other scikit-learn model, right? Nothing that interesting. But it is cool that the perceptron exists inside of scikit-learn as kind of like any other model. Okay, so we can see the accuracy here on our data, and we get about an 89% accuracy on the training and about an 88% on the test. So pretty decent. That's not too bad using that perceptron. So pretty cool. That works out, and that's just a simple neuron. It's not, this is a very basic model. It's just that single neuron. Of course, where we're going with all this is to build up our own neural network. That's going to be a huge collection of these neurons, right? That are going to be organized into layers that are connected into other layers, and so on and so on and so on. So we're going to build up to that. And one of the things we're going to have to learn is how to construct that in like PyTorch or TensorFlow. So that's going to be more involved. And we're also going to learn how to set up this training algorithm, this gradient descent. We need to learn more about that. So that'll be upcoming as well. Okay. And we covered this, but I just wanted to start here with kind of a review of what we had talked about in terms of neural networks, right? So just to refresh ourselves, we're dealing with neural networks in general, and we know that those are comprised of kind of a network of neurons, right? And these are organized into layers, where every layer has a different number of neurons potentially that we could specify how many there's going to be. But the idea is that the data that we pass in will kind of flow forward through this network, and every neuron is really doing something like this. Remember, this is the equation that we kind of had for a perceptron. which is that we take a weighted sum times the input. And so this W star X is really meant to be kind of a dot product, like a weighted sum times inputs, right? So we have weights times inputs, and then we might add a bias in there as well, which is what the B is here. So adding in a bias, which is just another weight, really. And but the important thing is passing that weighted sum of inputs through an activation, which is this F, right? So we pass that through some type of activation, which generates the output for that neuron. And what happens in the network is these outputs just flow into the next layer. So whatever is output from this neuron becomes the input into this next neuron. It also becomes the input into this neuron and this one, really all the neurons that are in the next layer. And of course, those have different weights associated to them. So there'll be a weight here, a weight here, a weight here that dictates how much of that input from that neuron gets contributed to this neuron's output. And same with this guy, like this guy's going to contribute a certain amount to this guy's going to contribute a certain amount to this, and there's going to be some type of weighted sum through an activation. And that goes from every layer to every layer, right? So that's what we've kind of learned so far. The things that we need to study a little bit, and we will coming up next, are what are these activations in particular, and when do we use certain activations? So in certain situations, certain activation will make more sense because they can, if you look at the activation from a math perspective, they really control what the output of this is allowed to be from a range perspective, right? Because you're taking an input, passing it through this function and generating an output. So depending on what that activation function is, kind of controls what you can possibly get out of there. If you're predicting things like in a probability sense, you probably want some type of activation that's going to limit your range to a probability, like between 0 to 1. That makes sense. If you're doing a regression, you don't want to do that. You usually want it to be just any real number value, right? To mimic like a price or temperature or something like that you're doing a regression with. So this activation is really important, and we're going to talk about some very common activation functions that are out there. But this is what we're talking about with neurons, right? Weighted sum through an activation, and we're doing this in this network of neurons that are kind of spread out amongst these layers, passing data forward throughout, and you finally get to some output. And even the output, remember the output, when we get into larger and larger complex use cases, the output is going to be different depending on what kind of problem we're solving. So if we're just predicting like a binary output, that's going to be just kind of a single output that's a probability, right? Between 0 to 1, kind of like what we saw for logistic regression for like a, you know, spam, not spam, fraud, not fraud kind of use case. But if we're predicting, maybe we're predicting between three different kind of image categories, like this is an image of a cat, this is a dog, this is a giraffe. We would likely have three outputs, right? We'd have probability of dog, probability of cat, and probability of giraffe. Or in, if we had 10, then we'd have 10 outputs here. So our output layer should kind of match how many outputs we're trying to produce. That makes sense. And so we're going to see that with different use cases. Want to set up those output layers to contain the right number of outputs and also, actually be probabilities, which is going to be hugely dictated by this activation, right? We want the activation to generate probabilities for those neurons. Okay, so this is a little bit of a recap. And if you guys remember, Perceptron is a special type of neuron that is just a single neuron that has an activation function that produces a 0 or 1, right? It's like a step function that produces a 0 or 1, depending on if this weighted sum is positive, this is going to produce a 1. If it's negative, it'll produce a 0. So that's what we meant by the perceptron model. It's just a single neuron that does this activation. Hopefully that rings a bell from last week. And what we're really interested in doing with bigger and bigger neural networks is basically having mini perceptrons, which are basically all of these models of neurons here. So you have lots of perceptron style calculations, and that's where we graduate from just a single neuron to multiple layers of perceptrons, which is this MLP model, multi-layer perceptron model here. So that's kind of where we're headed, and then this is going to keep expanding. So we're going to have even more layers, even more neurons, and then eventually even more complex computations there that are not just weighted sum through an activation, but things like convolution, things like recurrent layers. So we're going to work our way up there in the future, but that's where we're headed with all this. So just wanted to recap that a little bit, and pick it up from there, especially the activations. I think that'll we'll talk about that next. So we ended on this demo last time, which was kind of going into scikit-learn. If you remember, we did this demo, went into scikit-learn, and scikit-learn actually has the basic perceptron model. But of course, when we build a more complicated neural network, it's going to be in TensorFlow or PyTorch. But scikit-learn itself does have a perceptron, because it's a very basic model of a neuron, but it's not really a network, right? It's not like a full network. It's just kind of a single neuron. Okay. So before we go into activations, we really want to pick it up here, and talk more about what actually happens with these activations and what are some good examples of activations. Let's talk about activations then. So we know what the definition is, in terms of it is a function that we're going to apply to that inputs that are generated for the neuron, where we have that weighted sum with weights times inputs, and that generates this value that we're going to pass through this function, calling that function the activation function, which gets the name activation function. It really comes from biology and kind of the actual workings of a neuron, which gets activated if there's enough kind of energy there. So same kind of thing here. If the input is enough, we run that through a function and we kind of generate this output of it through this activation function. And so that's where it gets kind of its name. Now, in terms of the perceptron, we know what the activation function is. It's actually a very simple function which looks at this weighted sum of inputs. So it takes this weighted sum. So you can see here's like an input one, input two, all the way up to input n. We weight those. So there's a corresponding weight for every one of those inputs. We know that. We total that up and maybe even add in a bias. So you can think of an extra term here. There's a bias that contributes to the sum typically. And then this goes through this f, right? This f of x activation, which is taking the f of that weighted sum, uh, that is all of these guys, right? So this activation function is being applied to those. And really in the perceptron, it's a simple function. The f really says that the f is such that it has a definition such that like if this weighted sum is positive, then we produce if this sum is positive, then we produce one, else we produce zero. Else being, it's negative, or zero, then we produce zero, right? So the activation for the perceptron is really, really simple, but that's not the only activation that's out there. And in fact, when we start building our own neural networks, there's going to be many different activations we can choose from. Some of them are going to be more popular than others, and some of them have very particular use cases. As I said, one thing you want to pay attention to is this activation really helping us kind of narrow down the range of what the output of that neuron could possibly be. So, like in the perceptron case, the output's only allowed to be a binary one or a zero, which is good for certain problems, right? It's good for like a spam, not spam, cancer, not cancer, but it's not very good for regression at all, right? It wouldn't be useful at all for regression, wouldn't be useful at all for generating a probability, even because it's still structured to just zero or one. And it certainly wouldn't be good for multi-class where we have maybe 10 different categories of things we're predicting. So the perceptron activation is very limited. But we're going to explore some other ones that are found in a lot more general neural networks than just a perceptron. But you see what its purpose is, really to produce the output of a neuron, passing in those inputs through this activation function. So it has that capability of kind of mapping those to a particular range, which is important in terms of what are we trying to get out of the neural net, especially as you get towards the output layers, right? Then you really care about what your final output is. Okay. So if you think about it, if like what would happen if we did not have an activation function? So just think about that for a second. If we didn't have that, then in theory, depending on what those inputs are, we really could get anything from this weighted sum with weights and inputs, right? They could be any real number. That's all that's saying is like you get kind of an infinite range of possibilities. It's not really limited to anything, which is fine for some problems, like a regression, that's okay. But that is very open-ended and not very good for other problems. Like if we want to generate a probability, this is really bad because we don't want things to be really large or really big. We actually want it to be confined to be between zero or one, right? Coming out of the kind of final neuron. So having an activation helps us kind of bound that output coming out of a neuron. Because if you think about it, this weighted sum could be anything. Yeah, and actually, even in a regression, it's probably not good that it could be anything negative or positive. Like if you're predicting a price, you probably want that to be positive. So even minus infinity, infinity is probably not even good enough. You probably want it to be restricted to between zero and infinity at the very least. So that's where the activation comes in. We apply a function to this, and that helps us kind of map that to a potential range. Like maybe we map it to zero to infinity. So for like a regression, that'd probably be good for things like price, temperature, whatever. Or maybe we map that to zero to one for like a probability. That would be good for that case. So it just depends. It just depends on what problem we're solving. It also depends where we are in the network. Usually for things towards the end, we want to make sure we're using an activation that lines up the output to be in the appropriate range. Like if we're producing probabilities, we want that to be between zero and one, not, all over the place, like negatives, positives, which just the weighted sometimes inputs could be anything, right? Could be anything. And again, that's where the activation function kind of comes into play. It's applied to this and allows us to kind of map this to get a certain output from the output range, at least for that neuron. Okay, so hopefully that makes sense. So for that reason, activations play a really critical role in any neural network. And as I said, especially towards the end of the network, the example I always go back to is if we're predicting like three different things like dog, cat, and giraffe, we don't want those numbers to be all over the place. We really want them to be probabilities that add up to one, actually. So across this kind of out, let's imagine this was our output layer. We would want to make sure that these are all probabilities that are between like zero, so probabilities in zero to one in this range. So we'd certainly want that to happen. We'd also want all of these to total up to one. We want them to be normalized in some sense, right? So each one of these outputs should total across the output should equal one, right? That should happen if they're probabilities. So that's something we're going to be interested in doing. And what we would hope is there's an activation we can apply across this entire layer, really, such that all of these are probabilities, certainly in zero, one, and total up to one for those kind of cases. So we're going to see activations that actually will do that for us, be able to normalize that for us, which is good. All right. Okay. So, and the other thing about the activation function as well is the activation function actually also serves a really important part of the model, because it basically allows us to introduce non-linearity. Because if you think about it, like if we just had, let me go back a couple slides to this. If we just had this, this is basically a linear model, right? Just like this. This is a linear model, which we've seen before. It's just a linear, this is just a linear regression. Linear regression, right? That's actually all that is. It's just weights times inputs plus a bias. We've seen that before, right? That's all that is. So without activations, we essentially have just a huge collection of linear regressions that are um, connected together. So activations actually play a really important role in introducing nonlinearity, which is really, really important for a neural network to be able to learn complex patterns. So activations are actually really critical. So it's having this F here, this activation, allows us to learn more general patterns than just linear ones. Because if we didn't have that, that's all that we would have is just linear relationships all over the place, right, throughout the network. But having an activation function here that, and the activation function will generally be non-linear. It will generally be non-linear. We're going to get into some examples, but like some of them are going to be like the sigmoid, like from logistic regression, like a logistic function. Some of them will be hyperbolic tangent is a popular one. These are all, highly non-linear functions. There's also exponentials that are possible. So different types of functions that are all non-linear, that's actually a really big key because we want to introduce that in the learning process is the ability to kind of learn nonlinear relationships. So that's another reason why they're important. They limit our range, but they also introduce nonlinearity so that our network can learn those nonlinear patterns, which is really important. Okay. All right, so let's talk about some of the most popular activations. Now, by no means is this going to be an exhaustive list. There's definitely more than what's just on this list, but I'm going to go through these because these are going to be the most popular that we deal with in this course for sure. There are other ones that are out there that are more advanced, but I would say they rarely show up for the use cases that we care about. The ones that we care about are mostly going to be what's on this list. And I'm going to explain what all of these are and kind of what they look like. The thing that these all have in common, by the way, is they are all non-linear functions, all of them. So that's a really important attribute of an activation is generally non-linear. And again, we're going to have these spread out, across all the neurons. And so in that way, we're kind of like stitching together all these nonlinear relationships, which is how we learn complex patterns. But let me go through these. So these are some popular ones. We've actually already looked at this one a little bit, but we're gonna start with that one, and then we'll talk about these other three, the sigmoid, ReLU, and softmax. We'll talk about all those. So these are some popular activations. We've actually already looked this up. That's the one that's involved in the perceptron. Let's start there. So the reason this is called a step function is because it has one step up from a 0 to a 1. So if you look at it on a graph, which I'll do on the next slide, it's a function that goes from 0 up to 1, and it's just a single step up, 1 unit from 0 to 1. Now, this activation is kind of special to the perceptron algorithm because that's just the way it's designed, right? Is that whenever that weighted sum of inputs that is being activated, right? That data that's that weighted sum going into this function, whenever that is positive, we get a 1 as our result. Otherwise, we get a 0 whenever that weighted sum is negative or 0. So we get 0. So in that way, let me show you. It's kind of a step function that looks like this. So this is inspired by activating a neuron, right? So if you have a single neuron, it gets kind of activated when there's enough energy. In other words, it's bigger than 0. And this is why it's called a step function, is you can see on the graph, it literally looks like a step, on the stairs, right? It goes up and then over. So what this graph represents is, this axis is the input and the y-axis is the output, of course. And what you're looking at is for any time the input is negative, so you're on this side of the x-axis, you get 0 as your output, right? You're down here. You always get 0 no matter what that is. The moment you have something positive, meaning you're on this side, you get a one, right? You get a one for all those, no matter what that is. As soon as it's positive, you get a one. So you get that step up to one, and that neuron is essentially activated, right? And we get a one as a result. So this activation function kind of looks like this. Now that is nonlinear for sure, but what we also see is the range of this is very limited to 0 to 1. So this step function activation is really only useful for this perceptron when we are doing a binary classification that's going to be 0 or 1, right? Really only useful for that because we're not able to produce any other value in between, right? We only get a 0 or 1. We also, like for regression, we'd be out of luck because we can't produce anything else. So definitely wouldn't be a good fit for any of those kind of problems, right? So that's the step function. Again, this one's only going to be used for the traditional perceptron. That's the only time it's really ever used is in that case. So let's talk about the sigmoid. Now, this is one that we have seen before, and it's actually the same function that we have seen with logistic regression. Exactly the same function with logistic regression. So the sigmoid produces a probability between 0 to 1, which also makes it useful for binary classification. So just like the step function, this is helpful for binary classification. The difference is the sigmoid allows us to produce a probability that could be anything actually between 0 to 1, right? So in that way, we're actually generating a more direct probability rather than just either a 0 or a 1 final result, which we know from logistic regression, we did the same thing, right? We produced a probability. And what we did is we said, okay, if that probability is big enough, meaning it's above zero point 0.5, we categorize that as a 1. If it was down here, we categorized it as a 0. So we did that, but the sigmoid activation allows us to produce a probability between 0 and 1 as the output of a neuron. So remember, we're still applying this function to a weighted sum of inputs plus a bias maybe. And now this function is the sigmoid, is what we're saying is called the sigmoid. Um, and this is going to map whatever this is to between 0 to 1. Some probability. We interpret that as kind of a probability between 0 to 1. So where is this useful? This activation function is mostly used for binary classification as the output neuron. So if you're in the network, and so let's draw the network. So let's say we have this network, and maybe we have a hidden layer here, and then we kind of produce one final output. What we would, if we're doing binary classification, like spam, not spam, or cancer, not cancer, what we would really like this activation to be is a sigmoid. This guy should probably be a sigmoid because what we want to do is basically produce a probability from this weighted sum of these guys coming into this, right? So we're going to take this weighted sum and generate a probability out of that. Um, so we want this final result to be a sigmoid. Now, these others in the network don't have to be sigmoid activation to produce their output. That's fine. We're going to look at other activations that are more typical for kind of the middle of the network that produces a general value. But sigmoid is really, really often seen at the very end when you want to produce a 0 or 1. Generally, you don't want to produce a 0 or 1 kind of in the middle because that limits your range, right? That limits because like then this neuron would be very limited to a probability. This neuron would be kind of limited. This would be limited. We don't really want to do that in the hidden layers of the network. We don't want to limit ourselves because then we're not going to learn very effectively. But as a final output for a binary classification problem, yes, we want that to be a probability between 0 and 1. So sigmoid works great. Remember the function for a sigmoid is what we saw in logistic regression. It's this fraction that looks like this. So it's definitely nonlinear, right? Definitely nonlinear. You can see it from the graph, but certainly, this produces values between 0 and 1. When x gets really big negative, this fraction in the bottom kind of grows exponentially big. When x goes this way, it grows the fraction grows exponentially big in the bottom and makes it 1 over something really huge, which is basically 0. So that's why it decreases down this way as the x gets more and more negative. And then kind of the other way around is like if x gets really big positive and you go this way, you get closer to 1 because this term basically decreases down to 0, the larger x gets. So you get 1 over 1. So you get something closer to 1. So hopefully that graph makes sense, like based on that function. But that's what the activation is. And again, this is the same that this is called the sigmoid. Sometimes you'll hear it called the logistic function. Logistic function. It's the same one that's kind of used in logistic regression. In logistic regression, remember it's basically this, but um, we have something like this beta. We had our beta I xi. We were doing that. So we essentially have that same thing for this, activating that neuron. Okay, any questions about the sigmoid? So when you use it is generally the last neuron in a binary classification. If you're building a network for binary classification, it should be the activation on the final neuron. That's what it should be to produce a probability between 0 and 1. We generally won't use it in the interior of like the earlier neurons because we don't want to limit the output of those earlier neurons prematurely, right? That will basically collapse the learning and it won't be as effective. But we do, like if we're doing binary classification, we do want to produce a probability as kind of that final output of the network. So that's why you'll usually see it as the last activation here. Okay. So sigmoid we'll sometimes see. Now let me show you the most popular activation. And the reason this is the most popular is because it's the one that's used almost exclusively in the hidden layers of a network. The reason is because it does not really restrict the values. In fact, what this activation will just basically return back to you the input, assuming that it's positive. So as long as it's positive, it's just going to give you back what you put in. So see how this function gives you the maximum between 0 and x. So what that really means is like as long as x is positive, what's the max going to be between 0 and anything positive? It's going to be what that positive number is, right? So this will always just return to you what you put in as long as it's positive. However, this is a non-linear function because it has this piece right here, which is really critical. This piece is saying like whenever we have something negative, it's actually going to chop that off and just give us 0. So this is actually discouraging negative outputs. It's always going to give us something that's either 0 or positive, right? So this activation function is known as a rectified linear unit, because this y equals x is a perfect linear line, with a slope of 1, but we're rectifying that with this kind of nonlinear piece, which is this flattening of anything negative to 0. Because a true line would continue this way. For anything negative, that would be the true line, right? It would be anything negative would just give us that value back in return, but we're actually chopping that off in favor of making it just 0. So rectify it that way. The way you pronounce this is called ReLU. So ReLU, ReLU. Usually how you'll hear that pronounced, ReLU. This activation is the one that's most often used in the interior of that network, those hidden layers, because it allows us to basically generate the outputs that we care about, as long as they're positive. So it doesn't limit us down to a specific range like 0 or 1. It does limit us to a bit wider of a range than that, like 0 to infinity essentially. But in this case, like these guys would likely be all ReLU activated. And then like this one would probably be a sigmoid for a binary classification. Doesn't choosing the max of the range skew the model in terms of prediction? We're not really choosing the max. We're choosing the minimum because nothing can be negative, so it's always going to be capped at zero. Yeah. So y- in theory, yes, I think that's a really good question. But in reality, no, because we're going to have many of these neurons, typically in the hundreds of these per layer. And basically, what we're going to do is adjust the weights enough to make up for that. So remember, there's a bunch of weights here, and we're just going to make enough weight adjustments so that we can always produce something that carries forward into the next layer. So the weights, hopefully that makes sense. Like the weights really help us learn because we're going to adjust those weights accordingly to produce the right outputs. That's actually all of what training a neural network is making the right weight adjustments. And that's what we're going to talk about coming up soon. So not really. We just have to adjust the weights appropriately to generate the right outputs. And that's something that gets learned during the training process. So we'll talk about that. Okay. But this ReLU is probably the most popular activation. We're going to use it quite a bit. It's used all over the place in most networks. ReLU is very, very popular activation. It's kind of a very simple non-linear function if you think about it. It's because it's almost always linear, except in this case. This makes it nonlinear, right? Is this piece of it kind of makes it nonlinear, but otherwise it's mostly linear. Now, what a good thing about this activation as well is like if we were producing a regression value for like a price, this would be a good one to have at the end, right? Because you can generate anything that's not negative. So this would be a good regression candidate to use as an activation sort of towards the end, right? To basically make sure that you're getting something that's positive. So that would be like realistic. Okay. So this is a popular activation. We're going to use it quite a bit. And of course, like in our code, we'll be able to use this as one of our activations. And like I said, where you'll mostly, when you would use this one is pretty much in any hidden layer, your default is going to be ReLU. There's very few reasons you should not use a ReLU in your hidden layers, unless you have a good reason not to. Most like 90% of the time, you're going to see ReLU used as a activation on the hidden layers. The output layer is where you'll see those differences. You can see a sigmoid, you can see that step function in the perceptron, and then we'll talk about the next one, which is softmax, which will be used for probabilities as well. But most of the time, we'll see ReLU show up in those hidden layers between the input and the output. ReLU is very, very popular. It's a very effective activation. It's a very effective nonlinear function that kind of just keeps things moving forward as long as they're positive. Okay, so what's the difference between the sigmoid and the ReLU that we've looked at so far? Well, the sigmoid has it's a little bit more complex of a function. It's that exponential, that logistic. And one of the issues with the sigmoid is it can be susceptible to what's called a vanishing gradient, which we'll talk about later. Essentially, this is a consequence of the sigmoid always being between 0 to 1. So the issue with that is it's a fraction, right? A sigmoid is going to produce a fraction that's between 0 to 1. The issue with that is when we're doing the gradient descent learning process, if we're carrying around a lot of fractions, this is why you'll never see sigmoids in those interior layers, is because if you're carrying a lot of fractions, they multiply together with the because they become the inputs to the next layer. They multiply together with the weights of the next layer and really decrease that and really limit your learning ability because you have such small fractional values. Whereas ReLU can avoid that because it is generally just going to give you what you put in. So it's going to have a wider range, right? It's not going to limit you to 0, 1. But it's still nonlinear. So it can help you learn those kind of complex relationships still with the help of kind of the weights and the training process. So this is just to say you should generally be using a sigmoid in your output if you're producing a binary classification output. You should avoid using sigmoids kind of in the hidden layers if you can, because it's going to make learning more challenging. It's going to make training the neural net more challenging. And we'll study a little bit more the details of why that's the case, but it's mostly due to its range. It's producing the sigmoid produces fractions which carry throughout the network, and it kind of compounds. Like if everything is a fraction, things are going to compound really quickly and make small values that are very difficult to learn from. Okay. So that's why you typically see ReLU in those hidden layers, because it makes sense. You don't want to have these small fractions kind of all over the place. Does that make sense? Like if I go, I actually let me just illustrate that real quick. Is like you can imagine if we had going into a neuron, if all of these guys were fractions coming out of a sigmoid from other neurons in the layer, that's just going to compound, right? Like if this is one third, and then this is like one half, and then you have maybe another neuron that's connecting to it that has like a one fourth. Then you just have a bunch of fractions that are being weighted, and they're always going to reduce these values and limit your range and kind of compound things. So you don't usually see those sigmoids in the hidden layers. You'll see them at the end if you want this to particularly be a fraction. You'll see that. Okay. So ReLU, nonlinear, it's just the maximum between 0 and x, whatever's going into that activation. And you'll typically see these in the hidden layers in between the input and output. All right, I want to cover one more activation because it's also going to be really popular, especially it's really popular, especially as the output, using it in the output layer for multi-class classification. So the softmax actually just extends the sigmoid. It's like a multi-dimensional sigmoid essentially. So the softmax produces values between 0 and 1, just like the sigmoid does. It produces probabilities. The difference is that the softmax is useful for generating multiple probabilities that add up to one. So what you'll typically see the softmax used for is the activation across the final layer in the output if it has multiple neurons in that final layer. So let's say we had three. So we have a neural network that kind of looks like this, and then we just have maybe a hidden layer of four, and then our final output is three because we're predicting dog, cat, and giraffe, right? Those three animals. What we would use for this activation in this layer is the softmax. We would use the softmax for each one of these. And what that's going to do is produce probabilities that such that all of these are between 0 to 1, and they actually are normalized such that they total up to 1. So softmax is really, really great, as you'll see it in kind of your final layer if you're doing multi-class classification, right? So you're predicting amongst 1,000 things, then you'll have 1,000 probabilities that total up to 1. In this case, we only have three. So you have three probabilities, all that are bounded between 0 and 1, that total up to 1. So you'll typically see this in the output layer, especially for like image classification. You'll see that, or it could be, multi-class classification. You'll see this softmax. Another place you see softmax is in like an LLM, like a large language model will use a softmax as its final layer because it needs to produce probabilities across every token that's possible, right? So, and the reason is because the model, like a GPT, is going to predict what is the most likely next token. And so that'll be represented by one of these probabilities, right? What's the highest probability as kind of the most likely next token? So softmax, incredibly useful for anything that's multi-class classification, and it should be it should be in the output layer, right? It's going to be the activation that's used on the output neurons in the final layer to normalize them between 0 and 1 and get them to add up to 1, more importantly. So, it's a really critical function. The softmax function, if you're curious what it is mathematically, is sort of like the sigmoid, except it's more of an exponential. So it's kind of like across a summation of these. So you actually apply the softmax to individual components, and then you sum that up over all the components. And so this normalizes it to be between 0 and 1 and make sure that the total of it is 1 effectively. So it's a function that looks kind of like this. And you apply it to a component in the layer. So every neuron in this layer is going to get this function applied to it. Okay. So just to recap that, sigmoid, it should be your activation on your final neuron in a binary classification. ReLU will be in your hidden layers in the middle. It's the maximum between 0 and X. Usually just returns X as long as it's positive. And then softmax is going to be in your final layer for multi-class classification to produce probabilities that total up to 1. And by the way, these are all these activations are built into TensorFlow and PyTorch. So we'll be able to use them really easily inside of our code. They'll be built into those libraries. So it'll be really straightforward when we declare a layer of neurons, what activations do we want to use? It'll be really straightforward to set that all up when we start building our own networks. So all of that will be readily available. And there's really good documentation in both of those libraries on kind of what activations are available. Like I said, there's more than this. There are other ones like some popular ones are like hyperbolic tangent is a popular one, especially with some image problems. You'll see this tanh be used, hyperbolic tangent. That's a popular one. There's variations on ReLU. There's one called GelU. There's one called leaky ReLU. There's actually a lot of them, but the ones that we've covered on this list are the ones that we'll primarily stick to as we go through our examples. Okay. So that's a little bit about activations. So just saying that there are, definitely multiple of them, and which one we use depends on really the situation. All right. So I wanted to do a little bit of a demo here to show you an example with some activations and kind of how the activation is applied. Let me jump over to that. Okay, so we're going to look at this notebook. Do you guys have this one? This is the 3.06, taking a look at neural networks and activations. Hopefully you have this one. You want to follow along. Okay, great. Okay. So what we're going to do, the purpose of, thank you for sharing that. The purpose of doing this demo is mainly to see how we can build essentially a simple neural network from scratch. So not using TensorFlow or PyTorch, but see how we can use like a weighted sum through an activation and see that actually work in code, which I think will be really interesting to see. And really start to put the pieces together of a what a neural network looks like. So we can kind of get a feel for the different components of it without yet going into our frameworks that are going to handle that more in depth, like TensorFlow and PyTorch. So let's see. So first of all, we're going to import some things from NumPy. So some functions we might need, like the dot product, random value initialization, because we're going to build our own neural net that has those weights. So we're going to start out with random weights. So we need some randomization here, and we'll have some various like exponential function and dot product things that we may need from NumPy to do this. Okay, so what we're going to do is essentially we're going to start by building a neural network, a fake neural network. I say fake because, it's not going to use our frameworks that we're going to learn about, but it's going to show you the basically from scratch some of the components that you would see in a typical neural network, including the activation, which is really important. And what we're going to do is basically build a perceptron neural network. So it's gonna take three inputs essentially, an input that's a size 3 vector, basically a 3 by 1 matrix. And it's going to use this particular activation. We're actually going to use the hyperbolic tangent activation and produce an output, which would be kind of like a regression almost. But just to show you the different components of this network so you can see what's really involved with it. Okay, so to show you what's going on with this fake network, so we're going to build our kind of network from the ground up, which is going to be kind of like a perceptron. What you're going to see is we need some weights. And we have these weights which are generated randomly. And this ensures that their range is between -1 and 1 because this numpy.random.random generates a random value between 0 to 1. Okay, so if we multiply something between 0 to 1 and multiply that by 2 and subtract 1, kind of the range that we limit ourselves to is between -1 to 1 in terms of those weights. So these are just going to be randomized weights that live somewhere between -1 to 1. They're going to be random though. And the reason we're doing that is just to start out with randomized weights. This is actually how a network usually works, is when you initialize the network, it has random weights to start with. What needs to happen is you have to train your network so it learns those weights during the course of the training process. But this is pretty standard. This is pretty standard that this is going to be randomized to begin with. And when we start building our own networks in our frameworks like PyTorch, TensorFlow, those will also be random to kind of start with, and then they get trained, right? How is this plural? Because there's three of them. This random 3, 1 generates kind of a vector of size 3. Technically, it's a matrix that's 3 rows in 1 column. So there's multiple weights. Yeah, that's why it's synaptic weights, because there's three of them that are just kind of in this like 3 by 1 matrix, which is just basically a vector, right? With three weights. Okay. All right, so then we have our activation function here, which is going to be hyperbolic tangent. Now, all we're doing is when we give an input to this hyperbolic tangent, we're just going to apply the NumPy hyperbolic tangent to that input. Now, what this is actually going to be our activation. Now, we could use any activation we want. This is just an example. We could use ReLU. We could use sigmoid. This is just an example of declaring an activation and using it in our network. So I'm going to show you what that looks like. But if it was ReLU, then that would be it'd be like max between 0 and x would be the ReLU. But in this case, we're doing MP tanh, which is hyperbolic tangent, applied to x. Okay, that's just a function, just an activation function. Okay, now, the other thing we have here, which is I'm not too concerned with right now because we haven't learned, we're going to in the later notes in this lesson, we haven't quite learned it, is the gradient descent process for training a neural network. We're going to learn all about that coming up shortly. But one of the things you need in order to do gradient descent is the gradient of the activation, which is this. So the derivative or the gradient of the hyperbolic tangent is this function here. That's just a mathematical function that involves that hyperbolic tangent. So the reason we need this is the reason we need this is for training gradient descent. And again, I'm going to go into detail on what gradient descent is coming up shortly in the notes, but it's just here in this example for an example of how you would train this thing. Okay, so we have the activation derivative, which will be useful in the training for gradient descent. Okay, and then we have a function called train. So this function is called train and takes the training inputs, training outputs, which are kind of like the labels, and then a number of training iterations. Again, this here is going to be this is going to be gradient descent training process, which we haven't learned about yet. So I'm not too concerned with this digesting all of this moment. But just so we kind of preview what's to come, essentially what we're doing here is an iterative process through our data. So we basically iterate a certain number of times, which is configurable, this number of training iterations. We basically do this, we iterate this many number of times through this descent process, which is to say, we basically produce the output given our inputs. So we do a forward propagation. So that's what this is we do a forward propagation to produce outputs. And why do we do that? It's because we want to see how far off our network currently is. So if we produce outputs, what we can do is actually compare that to our labels, which are these guys, and we can compare our output to that and see how far off we truly are, which is what's called our error or sometimes called the loss. So this part here is computing the loss, which is how bad our network is currently. So we're just gathering up how bad we are currently. Now, why do we do that? It's because we use that quantity to make an adjustment to our weights. That's the key thing, is we actually want to make an adjustment to our weights to basically shift our network to perform better. Our goal is to minimize this error. I should write that down. The goal is to minimize this error. So essentially what we're doing is measuring our current error and then using that quantity along with the derivative of the activation, which is here, the derivative of the activation. We basically use that amount multiplied by that derivative. We basically use this amount to figure out how much we should adjust our weight. So this is a numerical calculation that's driven by this gradient. So that's why it's called gradient descent. Is we essentially want to make an adjustment that that will lower our error over the course of the iteration. So as we iterate a certain number of times, we should be getting better and better and better at making predictions using our network. And you can see here, like we make adjustments. So you see how we take our weight, we take whatever our weights currently are, and we add in an adjustment. So this makes a tweak. Think of it like turning a knob. So we essentially turn the knob, and the adjustment is telling us how much should we turn that knob? Should we turn it a lot? Should we turn it a little? We're figuring out how much we should make that adjustment to get better outputs of the network. So this is turning the knob so the network can predict better, right? So it can make the right adjustment and predict better in the future. So this in a nutshell is how any neural network's going to train. Now, this process will generally be handled by the framework. So by PyTorch or TensorFlow will manage this for us because it turns out when you have a pretty big network, that computing this adjustment is incredibly intensive on a big network. Computing what that adjustment should be is actually very computationally intense, and it's called back propagation. So basically, doing the weight adjustment and figuring out how much you should adjust, and then actually turning all those knobs. You can imagine, like for a very large network, that's going to be an expensive operation. Just to give you some context, like modern LLMs have hundreds of billions of these guys, hundreds of billions of weights. So you need to compute an adjustment for every single one of them, hundreds of billions of weights, right? And you actually need to do that every iteration. So you're imagine training for thousands of iterations and you have hundreds of billions of weights that you need to adjust. That's why they take forever to train. They're massive networks. They take forever. That's why. Because of this computation right here it can be very expensive, because this derivative can be very computationally intense to compute. it depends on your activations, it depends on how big your network is, but generally those large networks like an LLM, uh, it's going to take a while. That's where you benefit from a GPU, by the way, is to try to make this computation faster. So we'll actually see that. Like when we build our computer vision networks, we'll do a similar training process and we'll utilize a GPU there to make this faster. Okay. By the way, I forgot to mention this forward propagation when we produce the output. We call it think mainly because we are, it's like sending data through our network. So it's like all of our neurons are thinking together in this network. So thinking, what is thinking? It's really, this is doing our weighted sum through an activation. That's all it is. So it's like our weighted sum through an activation. That's all it's doing, right? Weighted sum through an activation. So you can even see that here. Notice how we apply the activation, the tanh, to this weighted sum. Now, why is it a weighted sum? It's because you're taking the dot product between your inputs and your weights. So that literally, now what does dot product do? Remember, dot product adds together the product of these guys as vectors, right? So that's taking our weighted sum and then does that make sense? This is taking our weighted sum and passing it through this activation. So that's this think is just computing that neuron essentially, right? Computing that neuron. All right, so just to finish out the demo, that's the network. So that's kind of our fake network. It's got three weights. It does it thinks by doing a weighted sum of those inputs through. So it has three inputs, three weights, take that weighted sum, pass it through a tanh activation. And again, the activation is kind of arbitrary. We could really have it be whatever we wanted. It could be a sigmoid if we were producing a probability. Here it's just producing a tanh, which is going to be tanh has its outputs are actually between -1 and 1. So we're always going to get something between there. So then we can run this code here, which is going to take a random set of inputs and then the labels for each one of those. So these are all like different labels. Like, so we have four different input sequences. Notice that every input is size 3, which is what it should be. So here's one input, here's one input, here's one input, here's one input. These are more or less random, just to show you how it works. And then here's a label for each one of these. So this guy is labeled 0. This guy's labeled 1, this guy's labeled 1, and this guy's labeled 0. So we have four labels here corresponding to each one of these sets of three inputs. So here's our random weights to start with, is this vector. So we're printing that out just so we see what our random weights are. Now, when we go through the training process, we're just going to have 10,000 steps and use those random inputs and outputs. Look at what the weights are after we do this. The weights are now completely adjusted and we can actually put in a new input and see what the output would be. The output, which is just running think on this input, it produces a label of 1. Okay, so the network functions as we would expect. And the big thing is to take away here is to see how those weights actually get adjusted. You see how far off they are from what they started as. So here they started as these really random numbers between -1 and 1. And here they get updated through the training process. So those weights actually get, changed, which is the objective of the training. Okay. Hopefully that makes sense. I think this is a good preview of what's to come in terms of the training process and kind of how we think about how this stuff actually learns. But you see all of the pieces that we've talked about so far, things like an activation, things like a weighted sum, going through the activation. It's mostly just the components. I don't think you're not supposed to glean anything from these outputs. These outputs aren't very meaningful because it's kind of a random input and a random activation. So it's not a realistic example, but the point of it is to see kind of the inner workings of this network, to see the different pieces of it. Like typically, what's going to be involved in building a network is setting up an activations, doing forward propagation, backward propagation, train it, like this training. You kind of see what goes on in the training. It's mostly so we see that inner working. prior to us building our own using the frameworks. Mostly just so we get exposed to that. Okay, so let's talk more about those terms we just used, mainly forward and backward propagation in our neural nets, particularly just thinking about it from a neuron perspective, data going in, and then making those weight adjustments. We'll talk more about that. So training any neural net really involves two particular phases, and we just saw those in the code really involved in that training function, right? And those two phases have a name which is known as forward propagation and backward propagation. We're going to break down what each of those really means. But it's kind of what the name suggests generally is that forward propagation is going to be all about sending data through to produce outputs. That's mainly what you want to do. And in fact, once you're done training and you're just using the neural net to make predictions, that's actually all you're doing is just putting data forward through it to produce an output, which is sometimes why that is called inference, because you're just making a prediction at that point. Now, the backward propagation is what makes those adjustments to all the weights across the whole network. And so when you have a very deep network, you need to be able to adjust all the weights across the whole network. And back propagation is going to be the algorithm that kind of does that and manages that weight update. And it's all going to be driven by this gradient descent that's dictating how much of an adjustment should we make to these weights. And then we basically need to propagate those adjustments throughout the network, which is going to be what backwards propagation is actually going to do. And so you really only do backward propagation in the course of training. But it is an iteration of doing forward propagation to generate predictions to see ultimately to see how far off you are in those predictions from an error perspective. And then you basically do backward propagation to go back and adjust all your weights. And then you just keep iterating, doing these over and over and over until you make enough adjustments to kind of have a solid network that makes predictions really well. So training is really just an iteration of these two things. So we're gonna dive deeper into what these two things are, but that's basically the summary of it. So I think forward propagation is the easiest one to understand of the two, and I think it's because it's really straightforward. It's essentially it's called forward propagation because when we have this network of neurons, data flows kind of forward through all of the layers, right? It goes, we have inputs that go into our first layer that generates some output, which becomes the input to the next layer, and on and on and on. And eventually we reach that output. So in a perceptron, which is a very basic, obviously a very basic network, basically just one neuron. It's not even really a network, but just a single neuron. We think of that as forward propagation really as just producing the output. And we know what does that. What produces the output is the weighted sum through an activation, right? That's really what produces the output is this typical, what we've been calling weighted sum through an activation. And so this produces the output. Data flows forward in this process. So forward propagation is just generating the output through weighted sum through an activation. Now, obviously, when we have a more sophisticated network, so if we were to draw multiple neurons in the input and then maybe some hidden layers, and maybe multiple hidden layers, and then like a final output, let's say that's a probability. The forward propagation is going to be a little bit more involved because we're going to have, I can even draw this in a different color. We're going to have contributions from all of these that are going to be weighted, and then contributions here, right? Contributions here, contributions here. So it's this much more involved network. And then data is going to flow like this. And then data is going to flow like this. So much more sophisticated um, flow. But forward propagation is generally moving this way, right? We're sending data in, generating an output. That's the forward propagation, really producing that output. Okay, so for the perceptron, we know that the output is either 0 or 1, right? Because the activation for the perceptron is basically this, right? So if that weighted sum is positive, we get an output of 1. That's the activation that gives us the final output. If that weighted sum is negative or 0, then we get 0, right? That's just the activation function. Now, what needs to be learned are these weights, and that's true of any neural net. All of those weights are really what need to be actually learned during the training process. So that's kind of what we saw in that demo is we need to make adjustments to those weights to basically have the best network structure that we can have. We want to make adjustments to those weights so that we accurately predict one or a zero or accurately predict the probability for our labeled data. So we can't forget that training a neural net is still like a supervised learning problem, right? We still have labels like on our, like think about images. We have all these images of cats, dogs, giraffes. Every one of those images has a label associated with it so that we know if we're getting an error or not. And that can inform us making an adjustment to all of our weights. So ultimately, we need to find the best weights, which is what the training process will do. It will make adjustments to those based on the error that we're producing. We can only really calculate that error if we're doing forward propagation, right? Because we need to know what our network thinks is the right answer. That's again kind of in that demo we saw it was called think, is really the forward propagation, the weighted sum through an activation. That's what forward propagation does. It produces those outputs. Okay, so we have forward propagation, just the simple act of sending data through our network, producing an output, which we know is really just this series of weighted sum through activations. Even if we have a big network, it's still going to be this collection of weighted sum through activations over and over and over again to produce some type of output. Okay, so that's forward propagation. Now let's talk about the error function that we saw like in that demo, right? So we need some way of evaluating where our network is currently. If we're producing results, in order to make the right weight adjustments, we need to know how far off our network is from the true labels. And that's where something like a loss function comes into play. We've actually seen loss functions in machine learning quite a bit. Remember, we had mean squared error, we had cross entropy for classification, like with logistic regression. So loss functions are not new to us, but in the context of neural networks, they are a little bit new, and we're going to break down kind of how they're used. But this idea of a loss function should not entirely be new to us, right? We've seen it before in machine learning, especially with things like linear regression. You guys remember we had the mean squared error loss function that told us how far off our regression was from the true value. It was kind of that distance, right? So in terms of neural networks, it's actually the same kind of concept. We need some way to measure how far off our output that we get from forward propagation is from the true value. And this is really, really important because this is going to inform how much of a weight adjustment we should make. Should we make a really big one? Should we make a tiny one? That's that notion of turning the knob. Should we turn the knob a lot? Maybe just a little bit. That's all informed by how much error we have when we do forward propagation compared to the true label. Okay, so that's just the general idea of the loss. So in neural network terminology, we usually think of this error, we usually call it a loss function, which is some type of function that computes what that error is between the label and what our network is producing. We usually call that a loss function. And the goal of the training is to actually minimize that error, minimize that loss function over the course of the training, but how much loss we have influences how much of a weight adjustment we make to the network. That's a really key idea in the training that we should kind of understand intuitively. If we're really far off, we need to make more of an adjustment to our weights. If we're doing pretty good and we're not that far off, then it's a smaller adjustment we have to make to our weights. So it is proportional to that loss or that error. And we'll see exactly how proportional in the gradient descent formula. Okay, so just to give you an example, we've seen the mean squared error loss function before from something like linear regression, right? So we know like this value here would come from the prediction of the model in a linear regression. That was our typical like beta times our features, right? Beta one times feature one, beta two, feature two, and we added those up, and we generate a regression value, and we see how far off we are from this in terms of the distance, right? That's the mean squared error. We've seen this loss function before. This is just an example of one that we see in machine learning generally. When it comes to neural networks, we're basically going to have the same kind of setup. We're going to have some type of loss function we use that is supposed to quantify this amount of error. So, kind of what is our average error across our data? That's what this is getting at, right? Because this is averaging our distances from all of our predictions to the labels. And we want the same thing in the neural nets is to be able to average this amount of error so we, again, can know how badly we're doing and use that to influence what type of update do I need to make to my network in terms of the weights. So the loss function, by the way, the loss function sometimes goes by different names. You'll mostly hear me call it a loss function, but in like literature or in other places, you may hear it called cost function or objective function, or sometimes we just call it the error. It's kind of all meaning the same thing, but I think the proper terminology is truly a loss function. And again, that's going to be something, the loss function is going to be something that's quantifying that error. And there's different functions out there for different problems. So like this is a really good loss function for regression, right? Because we're measuring the distance between our prediction and what the true value is. That makes sense to do for regression. For something like a classification, we have different loss functions, like in our logistic regression, right? We had the entropy, the binary cross entropy loss function, which was a different loss function that, but it's meant to do the same thing as kind of penalize those mistakes, right? When you're making a mistake, you want that to show up in your error. So this function is a way of quantifying that. Okay, so we have a loss function. Uh, and so, we've seen this picture visually for the mean squared error before. The difference between what our prediction and actual value is captured in that mean squared error metric. And obviously, the greater that is, that means on average, the farther away our prediction is from the true value. So, like in a linear regression, the predictions are always on this line, right? So the predictions are like here and here, here. They're always on this line, and you can kind of compute this distance between this line and here. Okay. So why do we care about the cost function? It's mainly so that we can do gradient descent. So I've used this word before, but we're going to talk about that coming up in the next few slides. We mainly need that to again compute how much of an adjustment we should make to our weights to make our model better. We can only do that if we know how bad we currently are. So if we go back to linear regression where we had a model that kind of looked like this to make our predictions, that's actually how under the hood, like in scikit-learn when we call model.fit, these betas were learned. Remember, these were betas times all of our features. These betas were learned, and the bias were learned actually through a gradient descent process, which would find out what those are based on this error and kind of a formula that takes into account that error to make an adjustment to these betas. It's actually going to be the same exact thing for neural networks. It's just a little bit more complicated of a formula to compute that adjustment because we have a more complicated model in the neural net than just a basic linear regression. But that's going to be the idea is we want to adjust our weights of our network and we're going to use the loss function to help facilitate that, like how much of an adjustment we should make. So it's really important. The loss function is really, really important in the training process of finding those weights of the network. Really important. Okay. So again, like the gradient descent process in a linear regression sense would basically find the best fit parameters, those betas, in order to minimize that error. We're going to do the same thing with the neural net. We're going to find the weights that minimize that error through a gradient descent algorithm. Any questions on this picture or kind of let me slow down and say, are there any questions about what the loss function is and kind of what its purpose is? Hopefully that makes sense. We're going to use it quite a bit as we go through setting up the training and executing the training of our own neural nets when we build them. And truly, like the loss function will actually be something built into the framework. So they'll be built into TensorFlow and PyTorch. So, we don't need to do it manually, but it's good to have that intuition understanding of what they are doing and why we need it. So again, it's capturing that error so that we can make adjustments to our weights, and that's how the neural network learns and makes itself better, is by doing those weight adjustments. Okay. So let's talk about that weight adjustment. So far, what we have in the training process is forward propagation, which sends data through and generates an output. What we can do with that output is then measure through a loss function how much error are we producing because we have generated those outputs. So actually, let me go back and mention that like this prediction here, I should call out is what we're producing from the forward prop, right? This is what we are actually producing in our network when we put data through, is we're generating a prediction. And so that's why forward propagation is first. It generates those outputs. Then we compare that to the true label through the loss function, right? And so this kind of tallies up and keeps track of how bad are we doing or what is our error in terms of our current network setup. And again, the point is to use this quantity that we're measuring to influence weight adjustments to get a better network the next time in the next iteration. So let's talk about that weight adjustment. That's going to be the back propagation part of this. The forward prop is producing the outputs. We have a loss function measuring how far off those outputs are from the true labels. Now we need something to actually make the adjustments, which is going to be the back propagation. So let's talk about that. So essentially, what the back propagation is going to do is systematically make adjustments to all the weights in the network. So of course, the deeper the network, the more weights that you have. So you can kind of take a look at this picture here. This is going to have a lot more weights involved in it than just a single perceptron, which is just a single neuron and it only has a handful of weights depending on the inputs. But essentially what we need to do is make adjustments to these weights that can make our network better. That's really how it learns. It makes those weight adjustments. It's almost like it's turning all the knobs to configure itself so that it can effectively predict on the data, right? It can effectively predict if this image is a cat, a dog, or a giraffe. And so just to summarize how this is going to play out, the forward propagation produces so the forward prop, let me just label that here. Forward prop produces the output, or I should say the prediction, which is, the output of the network. So it produces the prediction. The prediction goes into the loss function, and we generate predictions against all of the data in our training set. And we can take our prediction, we can take our labels as well and inject those into our loss function to figure out how far off we are. That's the whole point. Now, this loss function produces basically a weight adjustment, which is what we saw in our code for that demo, right? We're generating some type of weight adjustment through this error. And the weight adjustment is a formula. It's a formula that's given by gradient descent. So it's actually a formula that's computed based on the gradient of this loss function, and it's directly influences how much that adjustment should be. We're going to learn about that. But the back where back propagation comes into play is now that we know the adjustment, we need to propagate that out to all of the weights. We need to systematically update all the weights. And it turns out that it's not trivial to do that because, and let me tell you why. It's because to update a weight that's earlier in the network. So let's say we want to update this weight on this connection, this weight here. So I'm just singling out that weight. Let's call it W. If I want to update that weight, the update there actually depends on the updates in the further layers down in the network. So the adjustment here actually is dependent on the adjustments to all of these guys. So to everything after it, it's dependent on in order to update this guy that's earlier. So for that reason, we actually work backwards. We work back to front, which is why this is called backward propagation. We need to start here and figure out what are all the weight adjustments I need to make from here. And then we can use that to then update all the weight adjustments in the next layer, and then in the next layer, and then in the next layer, and then in the next layer. So this is why it's called back propagation or back propagation. And the reason there's a dependency there is all about calculus. It's very, I don't want to get into the math of it too much, but it's all about calculus. Essentially, it's because the gradient of a weight earlier on in the network is dependent on gradients that follow it later on in the network this way. So, in order to compute earlier updates, we need to compute updates that are further down the network. So algorithmically, it makes sense to start here on the end. And then once you know those updates, you just work your way backwards and you can use those to compute the updates here. Then you use these guys to compute the updates here, and it works its way backward. Okay? So this is actually the essence of training. You do forward propagation, produce a prediction, use that prediction to generate some loss. That loss is used to compute a weight adjustment for every weight. So the weight adjustment is a formula that's utilizing the derivative or the gradient of the loss with respect to every weight, and you start with weights towards the end of the network, and then you back prop towards the front of the network to make all those adjustments. Ultimately, you're going to adjust every weight in the network, but you're just going to do it starting from back to front. Backward propagation. That's what that does. Okay. It sounds complicated, but in reality, like we will not manage this process manually, of course. So this is the beauty of TensorFlow and PyTorch. This is why they exist, because they manage this network propagation for us. They manage all of this for us. So that's really why they were created, was to make this so much easier of a process, to manage the flow of data through this network, whether it's forward or backward with the gradients and all that. It's complicated. I agree. It is complex. Like training a neural net is not trivial. It is a complex process, but the frameworks that we're going to learn with in Python, the TensorFlow and PyTorch, make this relatively easy. They make this relatively easy, but that's the beauty of them, is they do make it easier on us. But I think it helps to understand these steps. Forward propagation, figure out how bad you're doing with the loss function, compute your weight adjustment, which is based on the derivative of that loss. That's the gradient. And then you propagate that back uh, from back to front because earlier weight adjustments depend on later weight adjustments. So it makes sense. You cannot do earlier ones without knowing the later ones. So you really have to go back to front. You have no other choice because you can't just jump straight to the front and update these guys. You would, in order to update this, you need to know this. In order to know this, you need to know this. In order to know this, you need to know this. So you have to start from the back and go to the front. You really have no other choice to do the adjustments. Okay. And again, that's why I said this stuff is not trivial. It's definitely advanced. But really glad you guys are, you know, trying to learn it because I think it's well worth it to understand how to work with neural nets. As I said, one of the preeminent examples of neural nets are like generative AI. Neural nets are all over the place, so it'll help to understand, you know, that how those work as well. And we're going to cover those later on, things like transformers. Okay. So to recap that process, what we're doing here is everything I just said. We're basically setting up our network with the initial weights. So when you first build your network, you're going to have random weights. And we saw that in our code in that demo. Everything has random weights. The goal is to learn what those weights should be over the course of training. So in order to do that, we're going to do forward propagation, which is what this first step is. So this is forward prop because we are producing the output. Calculate the output just means forward propagation, right? Send your data through, generate an output. Then you do your update on the weights, which is through back propagation, right? So back prop because we're going to compute a weight adjustment. Now, this is saying that the weight adjustment that you should make, we're going to learn this and when we talk about gradient descent a little more, the weight adjustment that you should make is based on the previous weight plus this amount here. And this is just saying it's proportional to your error or your loss. Because this is your loss in a simplified way, right? It's saying here's what your label is, which is D. Here's what your predicted output is. Here's what the predicted output is Y, and the gradient of this is typically proportional to the input X, and then there's also some learning rate that's involved, and this is just the gradient descent formula. That's all that this is. So we'll learn a little bit more about that coming up, especially in lesson 4, or maybe in the end of lesson 3. But this is the gradient descent formula. All it's saying is this is how much I should adjust my weight, and look at what it's proportional to. It's the error. It's really proportional to that error, not only the error, but the derivative of that error, which again, we don't have to compute manually. PyTorch or TensorFlow would compute that for us. They will keep track of that and compute what that adjustment should be. But under the hood, we should realize it's coming from this gradient descent algorithm, which is basically saying in order to make an adjustment, I need to take some proportion of my error, in particular the derivative of the error. Okay. And then we iterate. So essentially, we iterate these steps over and over again. So iterate these steps over and over again until you've completed all your steps, which is basically convergence. Maybe you do 10 steps, maybe you do 100, maybe you do 1,000. That's actually configurable as how many steps do you want to take. And we'll see. Sometimes we need to take more, sometimes we need to take less. Depends on the situation. But we continue to do that. And every time we do it, we're adjusting these weights. And the thought is like the next time around, these weights should be a little bit better. So our error should hopefully decrease. One of the things we should look for is the error should be steadily decreasing. That's what should happen, right? Because we're making an adjustment. As long as we're making a solid adjustment, which we should be because we're doing gradient descent, we should be getting better. So the next time we do this and do forward prop and then measure our error, it should be better and we should have less error. And therefore, we need to make less of an adjustment. So over the course of the training, we should be getting better, right? And hopefully by the time we've done all of our steps, we're really good. Our network is performing even better than it did at the beginning, obviously. What is T? So T is not really a true variable. T is just it's like a step. So it's like an iteration count. So all this is saying is like if I want to update the ith weight for the next step. So T plus one is just saying like on the next iteration, You just take the weight at the previous iteration, so what it currently is, t, so like time t, plus this adjustment. That's all it's saying is you take what it currently is at this time and add this adjustment to it. So this is just saying in order to update the weight, you take what it currently is and add this adjustment. So think of t like a step, an iteration. So the weight at iteration. So if you were to plug in like the beginning, like t equals 0, this is saying the weight on the so like on the first iteration, t equals 0, if I want to make an adjustment, the weight will now become what it was at when I started. So the weight at t0 plus this adjustment. And this formula is going to be different. By the way, it's not always going to be that, but it depends on how complicated your network is. But that this generally is the formula. Yes, t is the iteration. Yes. So the by the way, the back propagation is this step here that I wrote down. This is the back propagation. And again, it's called that because this formula cannot be applied for earlier weights unless I know the value of later weights. Because generally this formula will involve weight updates of weights that are further down in the network. So for anything earlier, it's going to require knowing what the weights are, in particular the derivatives of the weights for later adjustments. It's just a calculus fact that is basically known as the chain rule. So if you're curious more about that, you could look up backpropagation and chain rule and see if you want some more like math intuition behind that. But that's the reason. The chain rule from calculus, why we have to do backpropagation. So I wanted to, take a look at what the error, like a typical error function might look like in terms of the some of the square differences. So basically like the mean squared error over the course, different weight adjustments. So obviously what we're looking for is to minimize that loss. And the goal is to make weight adjustments enough so we end up down here at these kind of minimum loss values. We would love to end up here or here. We would love to make enough weight adjustments to end up there. What makes this tricky is that in terms of like a minimization, you can the gradient descent can kind of get tricked in some cases to believing it has found a minimum in these kind of valley spots. So like here, it kind of looks like a minimum, right? Even here, and certainly even here, it looks like we've bottomed out in terms of the error. And so what can happen is you can think that you've bottomed out and you can basically get stuck. You can get stuck here in these error positions where your error, you believe you've hit a minimum, and so your weight adjustment is not going to be that much. You're basically going to be flat and at it like an equilibrium, and you're not going to be able to make a weight adjustment and climb out of that to climb out of it and hopefully find a better minimum. So like ideally, you're finding a really low minimum of the error, and that's what you want. But you can get unlucky in certain situations where you can kind of get stuck. And we're actually going to talk about things that help prevent this. So there are certain algorithms that are out there that have been around for a while that basically propel you beyond these valleys and help you search for the lowest minimum you can in the error. Because what you don't want to happen is, again, you don't want to get stuck here, in which case you haven't truly minimized your error. You think you have, because when you look around, this is a classic like local versus global problem, is when you look around from this perspective, it looks like you've hit a valley. It looks like you've hit a minimum because everything around you is increasing. So it looks like you've hit a valley and you can't get any better. But truly, there's, more of a minimum down here or down here. So where you really want to end up is one of these guys. And so luckily, the training algorithm that we're going to use is going to help propel us to these minimums of the loss and help us avoid getting stuck. in these kind of fake minimums. Okay. So from a perceptron perspective, computing the error is actually really easy if we just take the difference, because what you can see is that like if you imagine what our prediction is going to be 0 or a 1, and the label is going to be a 0 or a 1 in terms of a binary classification. So we could always compare we can compute the error relatively easily with just a simple difference. So we could say like, okay, here's our prediction, which is 1, and here's the actual label, which is 1. So we had no error. It's kind of like a true positive, right? We got that one right, so there's no error. But we predicted 1 and it was actually a 0. So that's an error. So that's an error of 1. So that contributes an error of 1 if we take the difference there. Now, that's a very simple error function. In a lot of cases, we actually want something better than that, a more sophisticated error function, because in a lot of problems, we're not going to produce just a 0 1. We'll actually produce a probability. So that's where things like the entropy will come into play, in a little bit more advanced of an error calculation. But you could think of this as one simple way to tally up that error, which is kind of like, predicting, this is kind of like a false negative. So actually, sorry, this is like a false positive. We predicted 1, but actually it was 0. That's an error. Okay, so this is just going through everything I said. Once we know that error, so that's an example error calculation. Of course, the true like loss functions that we will use will typically be more advanced than that. They'll typically be like maybe a mean squared error and a regression, but in a classification, it typically will be something else. The reason being is because those lend themselves better to working with probabilities, which is generally what we'll produce for most neural networks for classification is a probability rather than just a 0 or a 1. But once we compute that error, now we know we need to adjust our weight. So this is talking all about backpropagation, which is just the term we're giving to going back and traversing back to front and making all of our weight adjustments to all the weights throughout the network. And ideally, we get better at this as we go along. That's what I was saying is we make adjustments and then we iterate, make adjustments, iterate, make adjustments, iterate, and we should be getting better each time. Our loss should be reducing over the course of these iterations, right? So everything we've been saying, just kind of summarized here. Okay, so the weight adjustments are according to formulas like this. Now these formulas are coming from gradient descent. So they're not out of thin air. These formulas are relative to your loss function and really like the derivative of the loss function. So they're not always going to be this simple. In fact, they're usually more complicated, but generally the formula is something along the lines of your new weight is equal to your old weight plus some learning rate times the gradient of the loss function. Okay, times the gradient of the loss function. So this is more generally the formula. It's just when you're using a simple loss function, it turns out to just be this is the gradient, just this quantity. But we're going to learn more generally that it's more of an update like this, generally, is the gradient descent. One thing to realize is instead of making an adjustment 100% related to the gradient, there's actually a what's called a learning rate here, which is a parameter that we have control over. It's actually a hyperparameter. And what this thing is doing is preventing us from taking way too large of a step. So when we make this adjustment, we don't want to make an adjustment that's completely governed by the gradient of the loss. I'll tell you why, like the intuition behind that is mainly due to this picture. Let me draw a picture to kind of explain why. And this actually basically explains gradient descent is this picture. So imagine this is our loss function, right? And we're trying to reach the minimum of the loss. So we're trying to get down here. And what we can evaluate on every iteration is where we currently are on this loss function, right? We know from forward propagation, we can compare that to our labels, and we can compute where we currently are. Let's say it's right here. We know we're somewhere on this loss function graph. Let's say it's right here. Our goal is to move towards the minimum. We want to make weight adjustments that move us towards the bottom, right? Now, let me turn this to an analogy of hiking. Imagine we were working our way down a mountain. We want to reach the bottom of that mountain. One of the things we want to avoid is taking a gigantic step, right? And we risk kind of like tripping and maybe traveling way too far. If we go too far in any one direction, what can happen, and if going back to this graph, if we take too big of a step, we can actually end up over here, which would be bad. So the idea is imagine working our way down a mountain kind of in the dark. Let's take small steps so that we guarantee we don't overshoot. Because if we take huge steps, we might overshoot. You might come all the way over here and overshoot. So let's take small proportions of that step. So that's what this learning rate is. It's a fraction that controls taking a small step towards the minimum. And by the way, this is why it's called descent, is we want to make an adjustment to our weights so that we descend down this loss function landscape and end up at the minimum of the loss function. But we don't want to take such a huge step that we just skip over the minimum entirely. So the learning rate controls how big of a step do we take. And usually you want that to be not incredibly tiny, but not too big. Because does it make sense that like the tinier it is, the longer it's going to take to hike down the mountain? It's going to take us forever. If it's a really tiny proportion, right? We're going to take baby steps and barely make any progress. We don't want to do that, but at the same time, we don't want to risk taking way too big of a step and then jumping over the minimum, and then we haven't minimized the loss. So gradient descent basically is governing. We should take a step towards the bottom. And by the way, what's the bottom? It's in a decreasing slope. So and that's the gradient. The gradient represents kind of the slope of this loss function. So we want to take a step in the direction of the gradient of this loss. That's why it's called gradient descent. Okay. And again, we don't want to take way too big of a step because then we'll jump over that minimum. So we're going to take gradual kind of steps governed by this learning rate. By the way, a typical value of the learning rate is something like 0.01 or zero point zero zero 0.001. But and that seems small, but it's really not. This has been proven to be a pretty good value for the learning rate for most examples. These have been proven to be pretty good fractions of the error, so that your step is a meaningful step, but it doesn't risk going way too big. Okay. So this is gradient descent in a nutshell. It's a gradient descent is an optimization procedure. It's an optimization algorithm that says in order to find your way towards the bottom of a loss function, which is what we want to do. We want to make our way towards the bottom of the error. In order to do that, let's take a step in the direction of the gradient of the loss. That's because the gradient is the slope of this guy. So no matter what side we're on, we want to take a step in the gradient direction because that's going to bring us towards the bottom of the mountain, right? And we want to control that step by some amount so we don't overshoot it. We want to take a controlled step in that direction. All right. I know this might be a little complex, but hopefully that helps a little bit on gradient descent and kind of what it's doing and why the formula is like this. The formula is like this again because we're taking a step, we're updating our weight in the direction of the gradient. This here is just it's the gradient of the loss. That's all it is. More generally, it's the gradient of the loss function. So we're taking how far off we are and using kind of the rate of change of that to figure out what direction we should adjust our weight. or how much we should adjust our weight. Okay. So I have an example of backpropagation that I will go through. It's kind of an in-depth example. So what I think we'll do is take a little bit longer of a break now, and then we'll come back and go through an example of backpropagation just so you can see kind of the flow of the data going back through and see truly why we have to go back to front in order to make all those weight adjustments according to that gradient descent formula. So we'll do that. Okay, so I just wanted to walk through a backpropagation example to mainly show you how the weights get adjusted back to front through a simple example. There's now, as a disclaimer, there's going to be quite a bit of math involved with it, and I'm not too concerned with the math, but more the process, just so you can see how there's kind of a gradient descent update that's relies on weights later on in the network to update weights that are earlier in the network, which really is what the backpropagation is all about. Computing those later ones, then using that to update those earlier ones. But the goal of backpropagation is to have all of our weights be updated according to our adjustment formula. And so that's how we learn, right? That's how the neural network learns and trains is it makes those adjustments each iteration. So as an example, we just have some kind of fake values in here just to put some numbers to things so we can see kind of a typical like network setup. So this is a very small network, of course. It only has a couple of inputs, and then it has a couple of hidden layer neurons. So it just has these two neurons right here as in the hidden layer, and then it produces two outputs, which are basically like probabilities essentially in the output layer. So this would be a good example of something that's kind of like softmax here in this output layer to produce kind of two probabilities that add up to one. But what you can see in this network structure is there are weights that have these green values associated with them. And obviously, in the beginning, those are random. So there's really no special reason why they're those numbers. Every network starts out with kind of random values there for those weights. And as we keep saying, the goal is to adjust those weights over and over until we really learn and make predictions effectively with this network setup. And so the initial input values that we have are 0.05 for input one and 0.10 for input two. So those are the two inputs that we have to start with. And of course, we have all these other weights initialized to kind of random values that are going to be adjusted in the backpropagation process. So this is the setting just for this is just a random example. Okay. And the purpose of the example is to kind of walk through over the course of the next several slides how we would adjust all these weights. And as I said before, one thing that I really want us to pay attention to is the fact that we cannot update this weight or this weight or this weight or this weight or this bias. We can't update any of these guys without knowing the update for this, without knowing the update for this, without knowing the update for this, and without knowing the update for this. These are required in order to update these based on the gradient calculation. It's required to know ones that are later down the line in the network. So that's why backpropagation goes this way, because you need to know these in order to update these earlier ones. And you're going to see that directly in the formulas that we're going to show in the upcoming slides. Okay. So that's something to be on the lookout for. Again, there's going to be quite a bit of math. I wouldn't get too caught up in the math, but it's important to see the backpropagation kind of in action in this example. Okay. So let's see how we can use backpropagation to kind of make adjustments to these weights. Okay, so we have those two neurons we just said, we have biases, we have weights, they're all initialized here, and that's fine. So nothing that special. And then we have two outputs which we see their current values of 0.01 and 0.99. So we have those two outputs, suppose, right? Suppose we generate those as the forward propagation outputs. Okay, so the forward propagation would generate would generate the output of each neuron throughout the layers. So for hidden layer one, let's take a look at hidden layers one's input. So if we go back to the screen, H1, let's just focus our attention on this. Let's look at forward propagating through the network, right? H1 has contributions from this from both inputs. It has weight one times input one, right? And it has weight three times input two, and it has a contribution from bias one. So what we should be doing in order to compute this neuron is we should be doing that weighted sum through an activation. Okay, weighted sum through an activation. Now let's go back. Let's take a look at that. So going forward, this is our computation, right? It's the weighted sum. The weighted sum looks like this. It's weight one times input one, weight three, input two, and then bias. Technically times one, but really it's just plus the bias, right? So if we were to compute that, we get this value as the input. And what we should be doing for H1 is really doing an activation to this quantity, right? This is the quantity we would be passing into an activation, whatever activation we had there. So for example, if that activation was ReLU, it would actually just leave this as it is. Because remember, the ReLU is just the maximum between 0 and this input. So even if we applied F as the ReLU, it's still just going to equal this quantity. So do we see how the ReLU would kind of function there on that weighted sum? We get 0.3775. Even if we applied ReLU to it, it would still be 0.3775 because that's what the maximum is. It's just that value. Okay. So that's for H1. And actually so I guess it wasn't mentioned there, but the activation that they are actually using, it looks like is the sigmoid. So just as an example, so we're not actually using the ReLU, it looks like we're using the sigmoid. I spoke too soon. So it's using the sigmoid as the activation. So here we get 0.59326 and carrying out the same process for H2. So if I go back to the picture, H2, what contributes to H2? What contributes to H2 is weight 2 times input 1, and then weight 4 times input 2, and then plus the bias, right? So those things should contribute to this. We should be doing that weighted sum and then passing that through the activation, which is the sigmoid, and that's how we produce those quantities. So that's how we produce these two values. Okay, so far just forward prop, nothing that interesting going on besides just a weighted sum through an activation. So we're just doing forward propagation at this point. Okay, so then what we're going to do is the same exact process to compute the output neuron. So if you look at the output neuron, let me go, I have to keep going back to this. We're going to compute the output one. So essentially what the output one is going to be is taking the weighted sum, right? So we do a weighted sum of this guy from H1 input, and then a weighted sum of this guy times H2's input, and then plus this bias should all contribute to output one. And we should be passing that through the activation, which I think is going to be another sigmoid to generate output one. So let's see. Yep, so there it's another sigmoid. So we have this here. So we generate weight 5 plus weight 7 times this plus the bias, and we generate this quantity, and then we pass that through the activation and we produce this value for output O1. Now we do the exact same thing for output 2, which would be, again, going back to the picture. So for output 2, what contributes to that would be should be this amount here times H2, and then it should be this amount here times H1, and then plus bias 2, and then we pass that through the activation, right? So those are the contributions for H2, or sorry, for output 2. And we generate we generate this output here. Okay, so just forward propagation. That's all we're doing so far is just showing you an explicit example of forward propagation. Hopefully that makes sense. The weighted sum through the activations, and these are what we get for those two neurons in the output. So that's what we have so far, right? That's what we have so far in our diagram. We have not made any adjustments to the weights. This is just forward propagation with the given inputs and just taking the weighted sums through the activations. So we get these two values currently, right? Now, let's compute the mean squared error. So we have labels on these guys. That was the original values here. So these blue numbers here for O1 and O2 are the labels for what these two should be. Okay, these are the labels for what those two should be. Let's compute the error so that we can do backpropagation and update all of our weights. So we should be able to do that, and we're going to use a mean squared error to compute the error. So, not that different than what we've done before with like linear regression, for example. So what we can do is compute the two errors individually. So we have basically we have error one is target O1 minus output O1 squared. So we have this quantity, which was the 0.01 minus this squared, and we take a half of that, which is this. And then error two is, we have basically the same thing, but for target O2 and output O2, we generate error O2. So we have both of those errors, and we should be able to total those together to get the total error. Okay, so this is just computing our loss value so far. So if we take the total of that, we have a total error of 0.3038. So that's our total error. Okay. So error one was this amount, error two was this amount as the mean squared error between this and 0.01, and then this and 0.99, right? We were comparing those two values, generating our error. Okay. So just computing the error. What we need to do is use this error with our backpropagation and gradient descent formula in order to make adjustments to all these weights now that we know what that error quantity is. We're going to use it to make all the adjustments according to the gradient descent formula. Okay. So again, this is where we do forward, and now we're going to do backward to adjust all our weights now that we know what the error is. Okay, so we're going through this process step by step just so you can see it. Okay, so let's do our adjustment to do backpropagation. So this is where we want to do our gradient descent formula. Oh, there was a question. Sorry. How it calculated error two. Oh, so error two is from it is doing this formula again. So it's 1/2 of the target of output two minus the actual output of neuron O2 squared. So it's the mean squared error between those two guys. So remember, this had a value, a label of 0.99 from the beginning, and then this had a value of whatever it was, 0.77, or I think it was 0.79, something like that. And so we're computing this mean squared error between the two and then squaring that. Does that make sense? So it's the same formula. Yeah, it's the same mean squared error. It's just from like or it was 0.76. Sorry, it was 0.76 because we computed these from forward propagation. We know what those outputs should be, and they originally had labels from the data. They originally had a label like output one had 0.01, output two at 0.99. So we're updating those, or we're computing those errors, and we're going to use those to do backpropagation with. Okay. So this is where kind of the math kicks in that I've talked about before is in order to do the gradient descent of updating weight number five. Yeah, there was a lot of error. Yeah, no, definitely. There was a lot of error. So what should make sense is we're going to need to make some adjustments. We're going to have to make quite a bit of adjustments because we got a pretty significant error there. But what I want to zoom in on now is let's update this weight. Okay, let's take a look at updating this weight. And when we're going back propagation, we do have to start with these back weights. We do again, we cannot start with these because mathematically we would not be able to compute those until we know what these updates are these adjustments in terms of the gradient. So what we want to do is make an adjustment to this according to the gradient of the loss with respect to this weight. So something we need to do is compute the gradient of the loss with respect to weight five. If we want to update that, we need to do it with respect to weight five. So the formula for doing that is here. So the gradient, which is the derivative essentially, which is shown by this quantity, this delta, delta E with respect to delta 5 is mathematically the derivative is this by what's called the chain rule of calculus. Again, I don't think it's that important that we know all that specifically. But in order to get to it, we take the derivative of the error with respect to output one times the derivative of output one with respect to the H1 essentially the hidden layer O1 and then the H1 with respect to weight five. So this is all like a chain rule kind of update. But the thing to notice here is that the this quantity is what drives this is the quantity we use in gradient descent to figure out how much of an adjustment should we make. It's totally related to this quantity here because basically weight five is going to be adjusted. The new weight five is going to be adjusted by the old one minus the learning rate times this quantity, this gradient here. Okay. So we need to compute what this is, which is we're going to do that now. We're going to compute what that is. Okay. So this is all about computing the gradient so that we can do the backpropagation. Now, in order to do that, we're just going to work our way kind of backwards through this chain rule. So that's why it is kind of a backward propagation. We know the total error is error one plus error two. Error one is exactly this amount. And so the output O1 is exactly given by this activation. So that's that. And then this is computed. This is computed by this weighted sum here. So hopefully it makes sense that like taking the update with respect to five actually involves an update with respect to another weight because every weight contributes to computing the outputs of those neurons. So that's why you cannot do earlier ones without doing later ones because they all depend on each other as inputs flowing throughout from layer to layer, right? So this is just unraveling the formula a bit on what this error actually is so we can take its gradient. Again, not too concerned with us knowing all that math, but mainly just wanted us to see how those different weights enter into the picture, right? Because those we just know from the way the network is structured, in order to compute like in order to compute anything that involves this guy, it sorry, mouse is just going crazy. Anything that involves this guy is going to involve contributions from this and contributions from this. So in order to figure out what the gradient is with respect to this, there's going to be contributions from multiple areas of the network, and that actually flows. Like if I want to know what the gradient is with respect to this, there's contributions from contributions at this level from this weight, and ultimately contributions that I'm going to need from these and these later on in the network to kind of figure out what is coming out of H1 or H2. So that's why backpropagation has to go this way. It has to. Mathematically, it has to, because as I keep saying, you cannot update these without knowing what the rate of change of these are. Just mathematically, you can't do it. And it's because of these gradients. Okay, so unraveling all of this, we're just filling out this formula for our gradient descent update. Now, something I should keep in mind is, will we have to do this manually each time? Absolutely not. This is something that TensorFlow and PyTorch will manage for us. So that's one of the beautiful things about those packages is it knows how to compute these gradient descent updates based on the graph, based on the network graph. It can do all these calculations. But this is just to show you everything that's involved so we can gain an appreciation for basically everything that goes into doing a back propagation update, which is a lot. There's a lot that's involved there, which is why it usually takes time to train a neural net because these calculations are not trivial, but the network framework like PyTorch or TensorFlow manages all that for us. Okay, so plugging in everything, our error is this, which makes sense. It's one half of this distance plus another half of this distance. So it's just the sum of both of those. So in order to calculate our derivative, we're going to do piece by piece by piece. So we're going to compute this derivative, and then this derivative. So we're just doing all of those pieces. So if you take this error and do it with respect to the output one, it comes out to be this quantity. So we can plug in all those values and compute this first, then we can compute this, then we can compute this, which is going to have those contributions. So we have, so then we can compute this piece. So we've done this. We can compute this piece next, which is the output is this quantity from the softmax, or sorry, from the sigmoid. So the derivative of it with respect to the H1, we can easily compute, which is going to be this with the exponential. So it just equals this. So it's this amount. So this is all derivative calculations. Again, do we need to know these derivatives? No. TensorFlow and PyTorch will manage it for us, but just showing you how that's broken down. So this is this quantity. Okay. And then that last quantity comes from the contributions from both of those weights, from that part of the network. So this quantity, we put everything together. So like this is how we get H1. We know it's that weighted sum that goes through to activation. How we take the rate of change of that with respect to weight 5 is that's actually just this coefficient, which is just this amount. We know that we've computed that earlier. We have that value. And so we can multiply all of those together and we get this as our total rate of change for the error with respect to weight 5 is this amount. So what that means is this should be used as our in our gradient descent adjustment of weight 5. So that's going to be an important part of our gradient descent adjustment for weight 5. So we can compute that if we, and now this is the formula I just wrote down a little bit earlier, is we take the current value of weight 5 and we adjust it by doing the learning rate times that gradient we just computed. So the original value of the weight was zero point 0.4 and we subtract off this amount. Our learning rate is a little bit high. It's 0.5. Typically, it won't be that high. usually be a fraction like 0.01. But so that's a pretty significant learning rate. But just as an example in the calculation, it just takes half of this. And so our new weight is down here. Now, this is the gradient descent formula. This is a gradient descent formula for adjusting that weight. It'll be a similar formula for weight six, weight seven, weight eight, which would be weight six would be whatever it used to be minus the learning rate times the gradient of the loss. You see why the loss is so important. It's the gradient of the loss with respect to weight six this time. So these slightly different calculations, but we could go through all of those and figure out what the adjustments are for all of those weights. So in reality, the back propagation is going to start with all of these weights towards the back of the network. So it's going to start with all of these guys being adjusted according to that gradient descent formula. Okay, all of those guys getting adjusted. And once we do that, now we can start propagating forward, or I should say backwards, and updating all of these guys. Should be able to do that. So we can compute the weight adjustment for weight one, weight two, weight three, weight four. We should be able to do all of those. You can see that it's going to be a similar formula. It's going to be the gradient of the error with respect to weight one. Now, what's really interesting about this is, again, these are actually going to utilize the weight adjustments that we made in the later layers. So like this formula is going to involve an adjustment we already computed according to output H1. We've already actually done that computation, so we can kind of reuse it, which under the hood, when we use these frameworks, they are going to, as much as they can, efficiently reuse calculations in the back propagation. They're going to reuse those adjustments that they've already been computing in order to work our way back and make all of these weight updates. We ultimately want to update every single weight. So again, we're going to start towards the end and work our way backward to adjust all these weights because those adjustments are going to reuse calculations we've already done. Okay. Okay, so we are computing. So like when we do this gradient of the error with respect to output one, it's actually the gradient of error O1 times the gradient of O2 with respect to output one. And we can see that there's we're going to be reusing weight five. It turns out that this calculation here actually just equals weight five, which we've already computed. We've already computed this as our weight five adjustment. This is why it's so critical to, update. It's so critical to figure out what those updates are and then use them to update earlier weights. So if you do the math on this gradient, it actually just evens out to weight five by itself because that's this coefficient attached to this. So the derivative of it is just this. Um, and so we're just reusing stuff we've already calculated, which is great. That's what's so efficient about the back propagation. It tries to reuse stuff if it's already been computed later down in the network. So we just did weight five, so we already know what that should be. Okay, so plugging everything in, we get the weight five value, and then we compute just a bunch of gradients, continuing along like the gradient of error O2 with respect to output H1, and this gives us our total, which is just this quantity here. So that's just one piece of the puzzle. In order to update weight one is this. In order to update weight one, we need this quantity here. Okay, so we just computed that guy. So this part is done. And then we just need to go through and compute these two, which shouldn't be too bad. So they're going to look similar to before. We can do the gradient. So this guy is particularly the sigmoid, which is this. So it shouldn't be too bad to compute its gradient. And then this is the weighted sum, which shouldn't be too bad to compute its gradient. And then we can make, therefore, our total adjustment for weight one is this, which is actually very, very small. It's a very, very small adjustment or loss for weight one, or I should say, derivative of loss with respect to weight one is very, very small. So it's going to be a relatively small adjustment that's going to be made to update weight one. Okay. So weight one can be updated. So we just go through and now hopefully you're seeing some patterns emerge here in the sense of look at this formula. It's our usual gradient descent formula we've been using this whole time. It's the weight one minus the learning rate times this loss function gradient with respect to that weight. So it turns out to be a very, very small adjustment because this is a very small number. So 0.15 minus this really small number is still pretty close to 0.15. So weight one actually didn't change that much. Weight five did. Weight five, six, seven, eight actually did change a good amount. Weight one actually doesn't change too much. It didn't get adjusted by that much. And similarly, so we could go through and do all those gradient calculations and update weight two, weight three, weight four, all in the same way. Okay. So we can make all those adjustments all in the same way. All right. So what we have, so the takeaway from this is not the math. I don't want us to be worried too much about the gradients and all that because that's going to be handled by our framework. That they're going to manage all that math for us, and we don't have to worry about that at all. What I really wanted us to see is this aspect of backpropagation, where in order to update these guys, we really rely on updates that we've made previously, right? From the later on layers down in the network. We try to reuse as much of those calculations as possible, and we will, mainly because of how the calculus chain rule works. It requires us to reuse those calculations in order to update these guys. So that's why we start backwards and work our way forward. It's so much more efficient because in order to calculate this, we would need to know this calculation anyway, but we're going to do that calculation as part of the updates later down in the network. So what's great about the frameworks is they kind of store that information and reuse it in all these gradient calculations. That's one of the beautiful things about PyTorch and TensorFlow is they are so effective at these gradient that's actually one of the fundamental aspects of those libraries is being able to manage backpropagation. They do it really, really well. All these weight adjustments of these networks. Okay. Okay, so let me talk about a couple of things that can go wrong during the backpropagation. So one of the things we saw is that we're computing these derivatives, right? And what can happen is you can get these derivatives that can be very, very small and close to zero. So, and that can be an issue. So, like when you have, let me go back to this. Like this is a good example of a derivative, a gradient of the error or the loss with respect to a weight that is pretty small. This is a very small amount. And so what that's saying is I'm going to adjust my weight by a very tiny, minuscule amount. And that can make training slow down significantly because you're not making that big of an adjustment. And so the next time around, you're probably not going to make that different of a prediction and you're just going to get stuck in making very small progress because your gradient's really small. Now, one of the things that contributed to this really small gradient in this example, I'll tell you the main culprit. The main culprit of producing these really small values is this, the fact that we were using a sigmoid as our activation. That's the sigmoid is purposely going to squash things into fractions, which is going to make our update values pretty small when we do these, because look at what we're multiplying together. We're multiplying this times this, and we just get a tiny fraction. So again, this sigmoid being there in kind of our hidden layer is not, this was just a dummy example, but it really causes this issue with these small gradients. And small gradients can be a big problem because they can slow down our training quite a bit. So whenever you're using gradient descent, which every neural net training does, that's something we have to be on the lookout for is really tiny gradients. And one of the things like we'll be able to visualize this during our training progress is that you would see your loss basically stall out. So one of the things you would see is in an equivalent graph, if you were to graph your loss over the course of your iterations, you would see like a stalling out essentially because your loss isn't going to change that much if your gradient is really tiny, right? Because you're not changing your weights by that much. So you're pretty much going to get stuck there. So this is very indicative of vanishing gradients. Um, so vanishing gradient just means really tiny descent update, and it causes you to get stuck. Now, we're gonna have ways to combat this. I'll talk about those later as we architect our network. One of the ways to combat this is to stay away from sigmoid and like softmax in the hidden layers of your network. You don't want to have those because you don't want to make your values smaller in a small range on purpose. So that can be a huge contribution to that. So that'll be one way to combat against it. We'll see some others as we go along, but that's just one issue that can happen during the course of training is those gradients can become tiny, which lead to very little, if any, weight updates, and you're kind of stuck. So I want to avoid that. Now, on the reverse side, you can have gradients that blow up and get out of hand. And when that happens, you basically have weight updates that are humongous. And you'll notice that too with your loss. Because what'll happen with the loss is maybe initially it starts decreasing, which is a good sign. That means it's learning, it's getting better. But then if your gradients are getting really huge and you're making bad updates to your weights, it can start to explode. So exploding gradients is also a bad thing. And usually what we see there is the you get really large weight updates, which creates a lot of instability in the training. So you'll usually see that in your loss just becoming exponentially big because your weight adjustments are just so big. You're getting a really huge gradient update. You're adjusting your weights so much, and you start to explode in your error. So that can be bad, obviously, and so we want a way to control that as well. Luckily, we have ways to mitigate against both of these, primarily in the gradient descent algorithm that we'll use to train our network. We'll actually have a really effective way to kind of manage both of these. I'll talk about that probably in lesson 4 when we get to it. Okay, so let's talk about gradient descent. So this is the algorithm that is used to minimize our loss function, particularly to tell us how much we should adjust our weights in order to minimize that loss function. And it works by deriving this kind of formula, right, which says I should be taking a step in the direction of the gradient of the loss function in order to minimize that loss function. So we've kind of seen that. And the picture that I think makes the most sense for descent is thinking about our loss function as kind of a parabola like this, and we're trying to work our way towards the minimum of it. And we do that by taking steps in the direction of the slope, right? The descent of the slope. So we're taking steps this way. That slope is represented by the gradient, and we're taking our steps down towards the minimum, hopefully reaching that minimum. Now, one of the issues that can happen with gradient descent is that the loss function is not a perfect parabola. We would love it to be that way, but it's not always that way. It can be jagged and kind of have multiple peaks and valleys, which can create a challenge, like I talked about earlier, where you can kind of get stuck thinking that you've reached a minimum, but you haven't reached the true minimum of the loss. So your model is not as good as it could be. That's something that can happen with gradient descent, especially if you have a complex loss function. You can kind of get stuck. But we'll talk about how to kind of mitigate against that as well. Okay, so let's talk about gradient descent in the context of linear regression. So you guys remember linear regression? It's just finding a simple model like this. Maybe it only has one feature, so it only has one weight and a bias. This would be the most basic linear regression there is. And we're trying to find the best fit model, right? We're trying to find out what these parameters should be, the M and the C, in order to get that best fit line through our data points, right? That was linear regression. So linear regression, is used to train, or sorry, gradient descent is used to train linear regression actually behind the scenes because there you can iteratively go through and find out what those weights should be through a gradient descent update on those weights in the exact same way we just did gradient descent for the neural net. It's just not as complicated because there's only a couple of parameters, the slope and the intercept in this case, and I don't need to do back propagation to update them because it's just a simple derivative. Um, so it's actually really easy to do that. So if our loss function is MSE, the mean squared error, it's actually really easy to find the minimum of that loss function by taking steps down this parabola. So exactly the picture I had before, we are going to descend and take steps towards the minimum until we reach the minimum and find the best parameters that minimize this loss function. Okay, the mean squared error. Okay, so that's the goal of the training, and we know that's what it's doing, right? It's trying to find the best betas or the C and the M, and that's actually exactly the same thing that we're doing with neural nets. We're trying to find the best weights that minimize this loss function, and we're going to take steps towards the bottom by taking the gradient of this loss function, because the gradient is the slope. We want to move in the direction of that decreasing slope here to get towards the bottom. We want to take steps towards that. So gradient descent in a nutshell is an algorithm. It's an optimization algorithm that iteratively updates weights to minimize the loss. That's the goal, minimize the loss. So we should see it decreasing over the course of the training. And we want to move in that direction of that slope, that gradient. So we update the weight. We know there's a formula there that updates the weight by taking a step proportional to the gradient, which is really nice. That allows us to kind of make our way in steps towards the minimum of the loss. And along the way of doing that, we're making these weight adjustments so that our model is getting better and better and better and producing less loss each time. That's the goal. So like I said before, the issue that can happen is the loss can be a complex function, and not as straightforward as like a mean squared error. And so it can be difficult to find our way towards the best optimum minimum, which is a challenge with gradient descent in general, is you're not necessarily guaranteed to find the lowest minimum, so you may find what looks like a good minimum, but it may not always be the optimal minimum, which can be a risk. But again, we're going to have ways to kind of combat that and try to find the optimal minimum as best as we can. So now think about it from the opposite perspective of finding a maximum. So if we were looking for a maximum, we would actually do what's called gradient ascent, meaning we would work our way up. Like if we were trying to reach the top of the mountain, we would take steps that slope us upward, right? We would want to go upward. So it's kind of the same. Like if you want to maximize a function, you actually do gradient ascent, which should go upwards towards a peak. That's what you would want to find, right? Is a peak. If you're trying to do gradient descent, you're trying to go down because you're minimizing something, which is usually what we're doing with a loss function, is minimizing that loss. But this is just a call out, like gradient descent actually could be used to maximize something by taking a step towards the in kind of towards the slope, going upward. We could do that. Okay. So you can see we're kind of now the question is like when do we converge? Essentially, the convergence is once we've done enough steps. So now we'll be able to actually have other ending or stopping criteria which will say like, okay, yes, we want to converge if we reach a certain number of steps in our descent, but we could also converge if we start to see that our loss is diverging away from where we want it to be. So like if our loss is decreasing at a good rate and then it starts to turn upward, maybe we want to say, okay, let's cut it off here because it looks like it's getting worse. So that's something we'll do later on is see how we can set that up as kind of like a convergence criteria. So maybe we want to keep going, keep going, keep going, keep going, and maybe it starts to get a little worse. That's where we can kind of cut it off and stop. Or we could just reach a maximum number of steps and stop then. So, but we'll be able to evaluate that visually, which will be really nice during the training process using TensorFlow or PyTorch. They have built-in ways of kind of evaluating your progress during the training and controlling that optimization. Okay. So again, in the neural network land, what we're trying to do is change our weights. And usually we're using gradient descent because we want to find the minimum of a loss function. So we're evaluating our loss, taking a step that is going to decrease it, right? Taking a step in the direction of that slope that decreases the loss function. So it's this picture. I've been using this picture quite a bit, but here it is again that the learning rate enters the picture in the gradient descent to kind of control how much of a step should we take in the direction of the gradient. So the gradient gives us generally we should be going downwards in this direction of the gradient, but the learning rate says, well, we should take a proportion of that gradient value and go, this amount down, and then take another step this amount down and keep doing it that way so that we don't risk overshooting the minimum and jumping all the way over here. And then if we take too big of a step, we could jump back and forth and just keep jumping back and forth over and over and over again, and we'll never actually reach the minimum. So the learning rate is a really important parameter in gradient descent. It's typically chosen to be something small, like zero point zero 0.01 is a very industry standard value, or even something smaller like zero point zero 0.001. Another thing to realize about learning rate is it doesn't have to be constant during the whole training. It can actually be changed. So there are some strategies, and we'll learn about this later on. There are some strategies that basically give us a schedule over the course of the iterations to say, okay, maybe the learning rate starts off high in the initial first handful of iterations, and then later on it actually slows down and the learning rate becomes smaller and smaller and smaller. And the idea behind that is maybe initially, like when your error is bound to be the highest because you have random weights, you're willing to take a larger step, right? So initially, you're willing to take a pretty big step and you're willing to take big steps initially. But then as you do enough steps, you start to slow down and take much smaller steps. So there are things like that we'll study. Um, that it can be variable. It can be like you can do like a decay, an exponential decay, essentially to say like, okay, if I've taken enough steps, I'm going to start decaying this so I encourage smaller steps as I've taken more and more and more. So we'll study that later on. All right, so just to wrap up, well, first of all, are there any questions on gradient descent? So just to recap that, gradient descent is our algorithm for training a neural net. It's what is going to optimize our weights. The thing that does the weight adjustment is the backpropagation. The thing that tells us how much we should adjust is gradient descent, right? It's what's telling us, it's giving us that formula so we know how much we should adjust those weights. Okay. So just to recap on the perceptron before we move on to lesson 4, the perceptron is a really simple algorithm, right? It has a single neuron that takes a weighted sum through an activation and produces a 0 or a 1 based on that activation. So it's limited. It can only produce a 0 or 1. It cannot produce a probability, which is bad for a lot of situations, right? It can only produce a 0 or 1, so it's not going to be useful in multi-class classification for sure. Um, but It is kind of the most basic neural net that there is in the sense of it's modeling a single neuron, taking a weighted sum through an activation. The other thing is, we saw this before, the perceptron only works with linear data. So as a model, the perceptron is very limited in what it can actually model. So whenever the classes are kind of arranged in a non-linear separable way, you tend to produce a lot of error. So what this is signaling is you really need a more complex network of neurons, right? You need that network so you can learn non-linear relationships. That's what you really need beyond just a basic perceptron. So, like, not every situation is going to line up perfectly like this, which is, where, okay, everything can be separated by this line. And so everything on this side of it's one class, everything on this side's the other class. And essentially what this line is this dot product and seeing if you're bigger than zero, you're on this side. If you're less than zero, you're on this side. And that's exactly what the perceptron's doing in terms of its activation. So, but not everything is like this, right? In fact, most data is not. And so that's where you need a neural network with more layers and more neurons to pick up on those nonlinear patterns. So, basic perceptron, very limited, but what I'm hoping we got out of this lesson is it serves as the inspiration for bigger networks where we can take weighted sums through activations and stitch together many, many neurons and learn non-linear relationships very effectively. So again, the perceptron fails to be optimized, fails to converge. Usually, basically, you end up with an endless cycle of weight updates because you're never going to converge unless you have a fixed set of steps. But even then, your model is not going to be very great whenever the data is not linearly separable, which is most of the time. Okay, so for this lesson, what we studied was the perceptron, which is our basic building block for neural nets because it models a neuron. It takes inputs, takes a weighted sum, passes through an activation. We are going to build off of that with larger and larger and larger networks. What we're seeing is we really need that power of those big networks in order to learn nonlinear relationships. So perceptron's just not going to cut it for most problems because it's so limited, but it's really good inspiration because we want that style of computation to persist in a larger network, but just with more activations, right? More nonlinear relationships. Okay. So what are we hoping to get out of lesson four? Well, we want to just expand our knowledge about perceptrons to larger and larger networks. So we're going to talk more about the things that we need to do to get there, including setting up our loss functions. So see what kind of different loss functions that we'll use. We've kind of already studied like mean squared error we know is there, but just want to review like for classification, what kind of loss functions would we use, which are normally going to be along the lines of those cross entropy ones that we've used in logistic regression. So very similar. And then we'll talk about the forward and backward propagation that occurs in deep neural networks and see kind of what the difference is to what we've been talking about. Really no difference except now the network is bigger and so there's more neurons at play, more activations, more gradients that have to be computed, those kind of things. So just expanding everything we've done to deeper networks here. And the point of this lesson too is to prepare us for putting all this together and building our own neural nets, which will be in lesson 5 and 6. So lesson 5 and 6 will be all about TensorFlow and PyTorch. So probably on Wednesday, we'll finish up this lesson and then move on into lesson 5, where we'll build our own neural network inside of TensorFlow. We'll get a good feel for that and do a lot of examples there. So Wednesday will be pretty good for building our own. Okay. So talking about the deep networks here. Now, this is just a referral to the how big the network is in terms of its hidden layers. So if it's got a lot of hidden layers, that means it's a deeper network than having very few, which would kind of be a shallow network. So the deep neural networks are going to have a lot more neurons, they're going to have a lot more layers, they're going to have a lot more weights. And one of the consequences of that is they're going to be more intensive to train because there's going to be a lot more weights to learn, the more hidden layers that we have, where things are connected together in this network structure. We have a lot more weights to deal with and a lot more weights to update. Okay. So on the flip side of that, though, the deeper the network, the more powerful it can potentially learn patterns. So, we want things to be reasonably deep for the problem at hand. So, like when we get into computer vision, for example, those are going to require somewhat sophisticated deep networks because learning how to do things like object detection or image recognition are difficult problems. Same thing with text and things like text generation and generative AI in transformers. Those have to be deep networks because they're representing really complex relationships, kind of like what we see with language understanding in a GPT, right? They're very complex networks, so they're very deep networks, have lots of layers, lots of weights. As I said, modern transformers are pushing into the hundreds of billions of weights. So it's a really massive network, really deep network. So going back to computer vision, we may be looking at images of different dog breeds, and we may want to predict which dog it is. So if there were three different breeds that we were choosing from, there may be, three probabilities that are produced. And that's an example where we may have a really sophisticated deep network, but in the final layer of it, there's going to be three neurons, and it's likely going to be a soft max output in terms of the activation because we want to produce three probabilities for three different breeds, and we want to produce probabilities generally that add up to one. So this is probably a typo, and this one here should be something like zero point 0.2. Sorry, no, zero point 0.3, which is what it is. Sorry, I read that as zero point 0.2. This is a zero point 0.3, so this should total up to one, um, which it does. So this should total up to one, and they should be probabilities between 0 and 1 if we were doing that kind of example. So again, it could be a really sophisticated network, but the final layer is something like a softmax activation that's producing these probabilities for our classes. Um, and we'll see that when we get into computer vision. We may have audio, so we may have a deep network that's analyzing sound data, so like signals, like waves, and those could be categorized into different, like music could be put into different genres, it could be put into different sound types. And again, this would probably be a very sophisticated, deep network, and it would be very difficult to pull something like this off without a deep network. So we've talked about this before. Neural nets give us this, they unlocked capability to work with this, advanced data like audio, images, text, video, things like that. So deep networks are present in so many areas like self-driving cars, image voice recognition, chatbots, voice assistants, online translation. I just gave an example, of the chatbots, where we're going to learn about that later on. The transformer network, those are very deep networks that have enabled, generative AI in the most recent years and really amazing networks. But they're very complex. They're very complex. They have a lot of layers to them. And the other thing is with some of these deep networks is they involve different types of computation than what we've studied so far. So what we see in like computer vision is convolutional layers, which are advanced types of computations that are beyond just doing a weighted sum through an activation. That is, in a lot of ways, that's the most basic type of computation a neural network can do. Just a weighted sum through an activation, which is what we've studied to this point, right? But there's going to be a lot more advanced types of calculations. Like in a transformer, there's attention layers, which are doing an advanced calculation to determine how words should be related to each other so we can understand context and meaning. So a lot to come, but these are all powered by kind of deep neural nets. All right, so when we start to put together our own deep nets, one of the things we're going to need to do is define our loss function so that we can train it, right? So we can, of course, we'll build the architecture of them. We'll learn how to do that in TensorFlow and PyTorch. But in order to train it, we will need to specify a loss function. So we'll need to understand how to do that. And so we're going to go through some examples of loss functions here. Now we just wrapped up talking about loss functions, so I don't really need to spend a lot of time on what it is. We kind of know that it's measuring the error. What we want to do is find the minimum of that through gradient descent, right? And minimize that error during the training process. So we've talked about that. And what we're going to do is talk about different types of loss functions that we typically see in training of deep networks. Now, one example we've used before is, you could, one very simple loss function is just take the difference between take the difference between like the probability, let's say, and what the label is. So in this example, that's just a simple difference. But this is not a very good loss function for training. So we're gonna learn like what a better loss function would be for doing classification. So just subtracting like 0 or 1, not the most effective. We're going to use something more advanced than that that lends itself to a better like gradient descent update than just taking a difference. So we'll see that in coming up shortly. But generally, we know the loss function is capturing the error between our model, our network's output, and what the true label is, right? That's what the loss function is doing. So generally, the loss function can be broken down into the loss that we use for a regression problem versus the loss that we use for classification. And we've already looked at the regression loss for the most part, but where we're going to focus our attention on is mostly on classification loss because a lot of deep learning problems actually are more classification than they are regression, like object detection or predicting what word should be next when we're generating text from a LLM or something like that. Most of it is class. Mean squared error as a really effective regression loss function. We know all about that. We've been studying that before, so nothing really new to say there. Again, it's measuring most of the time, it's measuring that distance, right? It's measuring the distance from the label to our predicted point. That's what these regression loss functions tend to do. And the ones that are most commonly used for regression are mean squared error and mean absolute error. Now, we've looked at both of these before, and again, they show up here in deep learning because we need some type of loss function to measure our error, use that to make a gradient descent adjustment to our weights. But these are the two options that are primarily used in deep learning as well. We've seen these before with things like linear regression. Not much of a difference here. We can either use mean squared error or mean absolute error. So the mean absolute error as a function kind of looks like this, where it's taking the average of these distances. Now the distances are computed a little bit different than taking the square distance. They're using just the absolute value difference. So that's a little bit different than doing the squared, which is more of a natural kind of distance calculation there. So that's the primary difference really is doing the absolute value of those rather than the square. So we get that for our loss function, kind of that average distance in terms of absolute value. And so if we were doing an example, we could compute the average error by just taking the difference between the what our network says the value should be, which would be like these predicted values, and what the actual value is for each of these examples. We take the absolute value of their difference, and then we average those together, and we get like a mean absolute error of 0.88, which is pretty good. I mean, it's pretty low. But that'll be up to us if we were doing a regression, which loss function we would want to use. We could use this, we could use mean squared error. In code, it would kind of look like this. Now, when we use this in TensorFlow or in PyTorch, it's going to be much different. we'll be able to specify that loss function as part of our training code when we get to that point. So, but this is just to show you, like, if we were to do this in NumPy, it would just be taking the absolute value and then taking the average of those absolute errors. Now, the mean squared error, and this is a typo, this should be parentheses here. Not really a big deal because it's, going to pretty much be the same. But this should be a parentheses here. Now, this is the mean squared error we've been using all along. So we take the squared distance between our actual target and our predicted value from our network, and this gives us our loss function, which we average this across all of our data. And so this is a very standard loss function regression. So this one is more widely used. Probably 99% of the time, mean squared error is going to be used for a regression problem. Uh, Absolute error is rarely used. The only time you would use it is if you're very certain that you have a lot of outliers for some reason. Like you have a lot of outliers and you don't want those outliers to be amplified as much in the mean squared error. You could use mean absolute error. But for the most part, I think the mean squared error is a very common loss function for regression. So obviously what we do is we find the distances. That's all we're doing. This is, we've talked about this over and over again, is like we take the distances here and we square them, and then we just average those. So for that same data, our mean squared error is actually a little bit higher. And that makes sense. That's because the errors are kind of amplified when we square them rather than just taking the single absolute value. So here, like if we were to do this manually in code, just in NumPy, it would kind of look like this, where we take the actual minus predicted, we square that, which is in Python, remember that's star star two is squaring it. And then we take the average of those squared errors. So that makes sense. Again, like when we define our loss function in our TensorFlow or PyTorch, it'll look much different than this. This is just to kind of explain the calculation. Okay, so you can see the errors are a little bit more amplified. Now, from a training perspective of the neural net, that's not actually a bad thing. Like that would actually be preferred because that's going to encourage us to make better adjustments, potentially better adjustments on our weights. We have a little bit more error to go off of in the squared case. So that's actually fine in that situation. But you can see, like, if you have an outlier, the square is really going to amplify it. So this is an extreme case where we change the predicted value, and so we change the actual value to something much bigger. So this 31.5 is likely an outlier compared to the rest of the data. So when you have an outlier label like that, your prediction can be significantly amplified in terms of its error. So this produces just a humongous MSE, whereas it doesn't affect the MAE quite as much. So again, like if you suspect there's a lot of outliers in the data, that's where the MAE may be, better as a loss function, wouldn't amplify those as much. Okay. So just kind of showing like for data without, if we have data that doesn't have outliers, like on the right, MSE is going to be our preferred loss function for any kind of regression problem. We're going to lean towards MSE. It's a very, one of the reasons, by the way, one of the reasons mean squared error is preferred. If we go back to the formula for it, this square is very desirable from a gradient perspective. If you think about like, because a square is like a parabola, right? So having this square is actually really powerful from a loss perspective. So our loss function kind of looks like this. It's much easier to take steps towards the minimum and basically guarantee we only have one minimum there. So it's desirable to have that square. Okay. So again, this is why mean squared error, if you're trying to train a neural net for regression, mean squared error is going to be your preferred loss function. One of the reasons is it's so effective in backpropagation for that reason that the square is really nice. The square makes the gradients really easy. The absolute value actually is a difficult gradient to do, because it technically doesn't have a gradient in certain places, mathematically. So This is a much easier function to work with under the hood for computing like those gradient updates. So the squared is actually preferred in the loss function. Okay. So that leads us into classification. So we talked about regression. If we're doing regression and we're training a neural net, we want to use mean squared error as our loss function. That'll make training it really easy. Or not, I shouldn't say really easy, but much better than if we did mean absolute error. Let's talk about classification and kind of talk about what the difference is with the loss function there. So let's start with the most basic case of binary, and then we can work our way up to multi-class. So with a binary classification, we are checking, we're trying to compute our error where the classification is going to be into only one of two options, right? It's going to be a cancer, not cancer, fraud, not fraud. It's going to be a one or a zero, and it's only one of those two options, right? So in a binary classification, those are the only two options we have. But in multi-class, we know it's more complex than that. So in a multi-class, there could be more than two. We could be doing apples, bananas, grapes, or the example I've always used is with images like cats, dogs, giraffes. But it could be many, many categories that we have. And what we do in multi-class classification is usually predict the probability of belonging to each class, right? So that's where that softmax comes in the end of the network to kind of see what is the probability of each class. So the reason to mention this is that's going to dictate what kind of loss function we use for classification if we're doing binary or if we're doing multi-class. There's going to be a slightly different loss function for each of these. Honestly, the multi-class is just really a multi-dimensional extension of the binary case. So binary case is really easy, and the multi-class is just an extension of that in terms of the loss function. Okay. So for classification, we have two kind of main categories of loss functions. And these are going to be really important because these are where when we do training of neural networks, especially for classification, we are going to need to define this um, in order to train it, like what loss function we want to use to compute our error, and then that dictates what kind of adjustments we should be making to our weights, right? So the two options that we have are going to be cross entropy and hinge loss. We're going to actually focus our attention on cross entropy because this is the one that's most widely used in classification. Hinge loss is rarely used. I haven't really seen it used too much, but we'll talk about what it is and how it's a little bit different. But we'll focus our attention mainly on cross entropy because that's the one that's most widely used for classification. All right. So, won't be able to finish this today because we only have about a minute left. But where we're headed with this is we need some way of keeping track of our error when we're producing probabilities. This is where we need a special function to kind of penalize us putting probability on the wrong result. So we know, like, just to wrap this up, we know that for a classification, especially multi-class, it's only going to be one of these three options as the actual label. So it's either going to be Samsung, Apple, or LG as the category of phone. Let's say we were analyzing a picture of a phone and putting into one of these three uh, products, Samsung, Apple, or LG. It's only going to be one of those three. But our model is going to produce a probability for each one of those. And so what we need to do is have some type of function that can compute the error if we know the actual category and we know the probability. So, and what we want to do is penalize situations where we're putting our probability, like a high probability, on the wrong class. So let's say we put a really high probability on LG, like a zero point 0.9, and it actually was an apple. So it was a 100 as the class, right, for Apple. And we had a zero point 0.9. We had a really low probability for Apple, like maybe we had zero point 0.07, and then we had zero point 0.03. And so we would want to penalize a situation like this, and we need some type of function to do that. Okay, so to get an intuition for cross entropy loss, now this is again going to be a loss function to measure our error. And the way we're going to capture this error on classification is to basically look at the difference in probability. Our model is going to be producing a probability more often than not, especially in the very typical multi-class classification where we're predicting amongst potentially many categories, right? So in that situation, our model produces something like this on the in the orange on the right. It produces something like this, which is basically a distribution, right? To say, okay, I've produced some probability of this class, let's say it's Samsung, some probability of this class, let's say it's Apple, and then some probability of this class, which is LG. And those need to add up to one. And of course, these are all fractions between 0 and 1. And we generate this from our network, right? And usually this gets generated from a softmax activation that's in the kind of final layer, right? And so this is a pretty typical situation. Maybe it's three categories, we produce three probabilities. That's pretty typical. So in order to measure our error, we want to compare this to the true distribution. The true distribution is going to be where there's 100% probability on the actual class. So if it's like a Samsung phone, then what I should get for the true, so for the label, let's say, or the ground truth, whatever you want to call that, the label is going to be a distribution as well, but it's going to have ones and zeros, right? So like if it's actually a Samsung, there should be 100% probability there, and then zero for the other guys. That would be a pretty typical like label distribution, right? Would be something like that. And what the cross entropy is going to do is measure kind of the difference between these two distributions, almost like a distance. It's gonna measure the difference between these two and generate a penalty whenever we have our probabilities that are different than this true label. Because what would be a perfect prediction is if our output was 100% Samsung, 0% Apple, 0% LG. That would be a perfect prediction. It's something that's very close to that might be something like where we have 90% of our probability on Samsung and then like 5% on Apple and another 5% on LG. That might be a prediction, which is pretty good. I mean, that's saying we're pretty confident this is a Samsung. And in the real world, whenever we want to generate a prediction, we take the maximum probability. So zero point 0.9 is by far the maximum, right? So we would predict Samsung for this. But this gives us a way to kind of measure our error, the cross entropy. It's going to measure mathematically the difference between this prediction in terms of probabilities and this true label distribution. That's the goal of the cross entropy. So it's kind of like mean squared error in terms of measuring a distance. It's just measuring like probability distances. So think of it that way. Okay. So I'm gonna show you the formula coming up, but that's the intuition is the fact that we need a way to measure how far off our probabilities are in our prediction. Right? That's kind of the goal of the cross entropy. Okay. So with that in mind, let's go forward. So again, the actual labels would look something like these guys, right, on the right. So these would be pretty typical for our data where we have our labels, and their probabilities would look something like this, depending on which class that example is. So if it's like an image and it's a Samsung phone in the image, it should be a 100% probability, like we just said. If it's an Apple, it should be 100% on the second entry. If it's an LG, it'd be 100% on the third. And we're going to produce these probabilities in this output and kind of measure that distance from this to these kind of labels. That's going to be the goal, is to kind of measure that distance there. Okay. So here's an example again where now in this example, we're not quite as confident. So let's say it's actually an LG. So therefore there's 100% probability in this third slot, 0 and 0 here, which makes sense. This is the label, right? This is the label here. Let's say in this example, that was the label. but our model predicted 60% LG, 30% Apple, 10% Samsung, right? These were the probabilities that came out of our prediction. Now, from a prediction perspective, we would get it right because technically, if we take the maximum of this, we would still predict LG. But what we're really after is how good is our model, because that's going to dictate adjusting our weights. Because what we would love is to get this very confidently correct. We barely get it correct because this 0.6 is just enough to be more than the others. So yes, we would predict LG and realistically, but we want a true kind of mathematical distance there between these two, like our prediction and our label, just like what we do with regression, but we're doing it with our probabilities this time, right? Hopefully that makes sense when you see it this way. And so the intuition should be that there should be a decent penalty for this because yes, we're getting it right, but not confidently correct. So there should be some level of penalty for this versus if we had way more confidence in LG. Like let's say we had even more confidence, like 0.99. So we had that, and then maybe we had 1% on Apple and then 0% on Samsung. Let's say we had that. The intuition should be that this setup should be penalized much less because we are very, very confident it's LG. The model's doing a pretty good job. It's 99% confident that the prediction should be LG. So it's put all of its probability, nearly all of the probability on LG. That's a pretty good prediction. This would be desirable, and this should be penalized less than a situation like this with the 0.6, 0.3, 0.1 because it's not as confident. There's some level of probability that's assigned to the other labels, and it's only 60% on LG. This should be a higher penalty than 0.99, 0.01, and 0, which is a pretty good prediction. It's nearly perfect, right? Nearly perfect. So to mathematically capture this, we compute the cross entropy. So in terms of a formula, it looks like this. It's actually a very simple formula, which is to multiply the labels times the logarithm of the probabilities for those labels. So if we have, uh, let's say we had, by the way, this formula is here. And you might be wondering, why is there a negative in front of all this? The reason there's a negative there is because these values here are all of our probabilities, right? And so they're going to be fractions that are less than one. Anytime you take a logarithm of a fraction, it's actually going to be a negative number. So these are all going to be negatives. These are all going to be negatives because they're logarithms of fractions. And so you're gonna basically take the negative of a bunch of negatives, which is going to make a positive loss, which makes sense. There should be a positive error, kind of like a distance, right? There should be a positive distance there. And what you can also see from this calculation is this calculation actually simplifies quite a bit. If you think about it, what's going to happen in the label is only one of these guys is going to be one. We saw that with our LG, Apple, Samsung example, right? Only one of these guys is going to be a one. The others are going to be zero. So what you're going to see in this formula is it actually reduces down quite a bit because the things that are zero are essentially going to be canceled out, right? So like if the true label was a one for the first class and then zero and then zero and then zero for all the other classes, that's essentially going to wipe out all of these terms, right? And so you're really only going to get a contribution you're only going to get a contribution from this term, from this probability, which is why you would really like that probability to be high. The closer that probability is to one, the logarithm of exactly one is zero. So if this were one as well, and we had 100% probability on this, then the error would actually be zero because it would just be one times zero. But something that's really close to one, like a 0.99, if you take the logarithm of 0.99, that's going to be pretty close to zero, a very small number. So it's going to be a small penalty. If you get it way off, so let's say it's the class is one, but you predicted a very low probability for that. That'd be a mistake. That'd be a pretty bad mistake, right? So let's say you only predicted a 0.1 probability for that, and you had all your other probabilities on these other classes, right? And the true label was a one, and then zero, 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 etc. The issue with that is, yes, all of these guys are zero, but if you look at this term, this is a one, but the logarithm of this really small fraction, like point, if you have a low probability there, is going to be a big error. The logarithm of that's going to be a pretty big negative number. The smaller it is, it's a larger negative number. And so then you get a much bigger contribution to your error, to your loss. Okay. So mathematically, that's why you have logarithm there, is because you want, whenever you have a small probability, you want that contribution to be more for the target, right? You would like this to line up so that most of your probability is lined up to your target, and that's a very small contribution to the cross entropy. Okay, great. So that's the formula for that. Now, will we need to calculate this by ourselves? Of course not. This will be handled by TensorFlow or PyTorch, but this is just the intuition for, why we use this formula under the hood to do our training. Remember, this is our loss function. So this is the function that's going to be used during the gradient descent training of our neural network. And this is particularly useful for classification, right? We had mean squared error, which is very natural for regression. But in this setting of classification, we need to use this loss function cross entropy. Okay. So here's an example calculation. If we go back to that setup we had before, where the actual label was LG, and we had these probabilities where we had zero point 0.6, zero point 0.3, and zero point 0.1. If we were to calculate this cross entropy, it looks a lot like this. So we have, again, like I said, really only the contribution from this term, that where the label is on the LG. And so these other terms don't contribute anything because they have a zero there. But what we can see is the logarithm of zero point 0.6 is going to be a negative number. And therefore, when we take the negative of this negative number, we get a positive error contribution, which makes sense. There is some level of error there. And that error is going to be more than if we had 0.99 sitting here, because the logarithm of 0.99 is going to be a number that's much closer to zero. Okay. In case you're wondering, the logarithm graph kind of looks like this. And it crosses this axis right here at 1. So 0.99, 0.99 is going to be a very tiny value that's very close to zero. Whereas zero point 0.6 is going to be somewhere down here, that's going to contribute more error. Okay. So, given that we've talked about cross entropy, the cross entropy actually can be thought of in two different ways. The one that we just studied is the categorical cross entropy loss, which is used for multi-class classification. There's a simpler version of it whenever you have a binary, meaning you only have one probability, which is for between two classes, like a spam, not spam, or cancer, not cancer. It actually reduces even further into a simpler formula. But the one we just studied is very much related to categorical cross entropy, which is mainly for the multi-class. So the reason it's called categorical is because it's for multiple categories. So this is the one that would be used most of the time for multi-class classification. And the binary cross entropy is going to be a reduced, simpler version that's going to be only in the case of binary classification. So we only have two classes and we produce a single probability. and the label is only going to be a 0 or a 1, right? There's only two options. So the one we just did is where there's, we have a multi-class classification, so there's multiple probabilities at play. So that's going to be this one. Okay, so let's study those. So if we were to look at some various cases, I want you to, this is kind of getting at what we were just talking about earlier. So if we're looking at all of our data, so let's say we went through every single example, every picture that we had, in order to compute the loss for that iteration, we're going to basically average those errors together. So that's what's actually going to happen with the categorical cross entropy is we're basically going to average all those cross entropies together. So if you look at this table, you can see some scenarios where there's much higher error in some cases. I want to pinpoint a couple of cases that kind of jump out to us based on what we were just talking about. Look at this case here where we produce a 2.3 error. That's a significant error. Why did we produce that? If you look at this example, the true label was Apple. So there's a 1 here in the second slot. That's an Apple prediction, right? An Apple label. There's a 1 there in that second slot. But what did we predict? We would have gotten this wrong and we would have predicted Samsung, right? Because the most of the probability here for this that our model might have produced would have been here on the 0.6. We only had a probability of 0.1 for Apple, which is a mistake, right? That's a very low probability for the actual result. And so we get penalized for that pretty heavily, right? We get a 2.3 penalty in the cross entropy, which is contributed from this term, right, in the cross entropy calculation. So that should make some sense. We get a very low error right here because in this situation, which aligns to what we just talked about, we have most of our probability is on Samsung, and that is the true label. There's a 1 in that first slot. So this is a much smaller contribution to our error. There's still some error because it's only 90% probability. Ideally, we would have 100% probability on that, and then our error would be 0, right? Because the logarithm of 1 is going to be 0. But we still have some error, but it's much smaller, right? Much smaller than the others. But all we have to do is basically take all of these guys and average them together in order to produce the actual cross entropy loss quantity. It's just an average. Okay. An average amongst these guys. I think there's a typo here, by the way. I don't think it's 4.76. That seems kind of high. I think that's this total, and we have to divide that. We need to divide this by 7 to get the actual average. Okay. Okay. So whenever we do the binary case, the formula actually reduces quite a bit into a simple formula here that depends on the label. So when our label is 1, we get this, which is just because remember, in a binary cross entropy, you're only going to produce a single probability. And what the intuition here is the same as usual. Whenever this probability is high, whenever it's close to 1, that's a good result in terms of the error. The error is going to be pretty small because whenever that's close to 1, this is a small value, right? Including when it's all the way at 1, if we had 100% probability, this logarithm would be 0. So we'd have no error. So hopefully that makes sense. Whenever the label is 0, we take 1 minus our probability. And so our contribution comes from 1 minus our probability. So if we're predicting like a 60% probability and the label is actually 0, that's a big mistake. Or like if we're predicting a 90% probability and our label was actually 0, that's a huge mistake, right? Because in the binary case, remember the probability is just a single value that represents like the class. If it's above, usually our threshold is zero point 0.5, right? If it's just above zero point 0.5, we predict a 1. If it's below zero point 0.5, we predict a 0. So that's why we do 1 minus the probability when the class is 0. And so that helps us penalize the right thing. So if it's again like a 90% probability, but our label was actually 0, that's a significant penalty. Because we would get logarithm of zero point 0.1, which is going to be a big negative number. So that's why we have a 1 minus there. Now 1 minus 0 is just 1. So this just is always going to be 1 in either case. But when the label is 0, we do 1 minus the probability inside this logarithm. But in the same way we did for categorical cross entropy, we're still going to average that across all of our examples. So we still, to compute our loss, to compute our overall loss against all of our examples, we're still just going to average that for all of our data, right? To get the average cross entropy loss. Okay, so that's really remains the same, just a simplified formula a bit whenever we have a binary case, because we're only producing one probability. Okay, so in code, this is kind of what it would look like in order to compute the binary cross entropy. Now, you may be wondering in this code, why do we have this number here? And so just to point this out, this is actually pretty typical in most implementations of cross entropy, is they have a small number here usually to avoid taking the logarithm of 0, because the logarithm of exactly 0 is negative infinity. So we don't want that. We never want to take the logarithm of exactly 0. So most under the hood implementations of cross entropy will safeguard against ever plugging in exactly 0. And because we don't want this to be exactly 0. So we'll kind of have this tiny, tiny, tiny amount to keep us away from 0 if just in case, right? Just in case to avoid this. Now, it's still going to be a huge negative number. It's just not going to be infinity. It would still be a huge negative number if we like let's say we predicted a 1 probability, but it was actually 0 class. That's a completely wrong answer, and we don't want to have infinite penalty for that. We still want a significant penalty, which we would have, but we don't want an infinite because that would just ruin the rest of the calculations, right? So that's why this is here. Okay. But of course, like we aren't going to use this because PyTorch and TensorFlow have their own way of calculating this. They have their own loss function that we'll be able to use. This is just like if we were to codify the math that we just saw for especially binary cross entropy, it would look like this. Okay, so the now inside of TensorFlow and PyTorch, they have a reduced version of that formula that we saw earlier with the cross entropy, and it looks like this. So the one that we actually will use will be this version. The reason that's the case is because remember, the only contribution we get from every single term is there's a 1 sitting right in front of this, right? That's the only contribution we ever get is 1 times the logarithm of the probability. So instead of writing out that formula like this, where we do y1 times logarithm of probability of class 1, um, and then we had plus um, y2 logarithm of probability of class 2 plus blah blah blah. We remember this formula is for the cross entropy. The in all of those cases, the only time we get a contribution is the term where for the actual class, right? So if the label had the second class, then no other terms contribute. This is the only guy that's going to contribute. So for that reason, we can actually simplify this formula to just this. It just reduces to this formula here where we're taking the logarithm of that class probability, and we technically have a 1 sitting in here, sitting in front of it, but that doesn't really do anything, right? It just multiplies by 1. And then we have our negative out front, which is this guy. And we have our average here, which is dividing by n and totaling all of these up. So the formula makes a lot of sense. It just is reduced significantly from what it's much simpler notation for writing that out than we had earlier. Okay, so this, by the way, this version of it is often referred to as the sparse version or the sparse categorical cross entropy. You can use either one. They give you the same result as categorical cross entropy. It's just a little bit simplified of a notation. That's really honestly the only difference. That's the only difference is we just simplify the notation a bit from what we had earlier. This is sometimes called sparse, so we can use either. Whenever we use PyTorch or TensorFlow, we can use categorical cross entropy or sparse categorical cross entropy. Either one gives you the same result. They're the same formula, really. Okay, so the reason we use that is to, obviously call out mistakes in the probability. So if you're wondering, like, why don't we just use mean squared error or mean absolute error? It's because we don't want to calculate like a numerical distance. That's not going to amplify those mistakes. What really is amplifying them is the logarithm. That's heavily penalizing the mistakes. So that's why, I think it's a valid question. Like, why wouldn't we just use the distance from the mean squared error? Because we kind of have almost like two vectors that we could calculate the distance between. But that's not going to emphasize the right penalty, which is really a probabilistic penalty that we want to apply. So in that situation, we would not use mean squared error, mean absolute error. We're going to resort to the cross entropy because it does what we want it to do as a loss function. It really penalizes those wrong probabilities. It amplifies them correctly. So you do not want to use mean squared error. You can get bad training in that way. So we want to avoid that and make sure we're always using cross entropy whenever we're doing classification. We should always be using that. We should never be using mean squared error, mean absolute error in any classification example, right? It's just not going to penalize the right mistakes. Okay. So just to recap, for regression, we should be using mean squared error. That's fine. That's actually what we would want to use for regression problems where we're predicting some type of continuous value that's coming out of our neural network. That's fine. For classification, we should be using cross entropy loss. And whether it's the sparse version or the regular categorical cross entropy, or in the case of a binary problem, the binary cross entropy, one of those formulas we should be using for the loss, right? And in classification, we should not be using mean squared error, mean absolute error. It's not going to do the right job in penalizing those wrong probabilities. Okay. So I also wanted to call out that there is another loss function out there that's sometimes used, I would say rarely used versus cross entropy for classification, and it's known as the hinge loss. I'm not going to spend too much time on it because I've rarely ever seen it used. The idea behind the hinge loss is to basically the take the cross entropy loss and have some type of regularization to it, almost like when we did lasso and ridge regression, where we had this kind of additional penalty, added on top of the original loss function of the mean squared error. If you guys remember all the way back in regression when we studied lasso and ridge, they added a penalty to just typical mean squared error, right? So hinge loss is going to be kind of that same idea. It's going to be a variation on cross entropy that aims to kind of penalize certain terms in the loss function. I'll show you what it looks like. But hinge loss also, by the way, is inspired by the SVM. It's actually the loss function that's used in training an SVM in order to find that hyperplane that separates the data, and increase the margin between the hyperplane and the points, away from that hyperplane. So it penalizes mistakes still in the same way that cross entropy does, but it also penalizes ones that are close to what we call kind of the decision boundary, which is the sort of like in SVMs, like that hyperplane that we're building to divide the classes. So it just has this kind of extra penalty there that I don't think is very natural for neural networks. I think it makes sense for SVMs, but it's not very natural for neural networks, which is why I think it's not used as much as cross entropy. So what is the hinge loss? The hinge loss is given by the maximum between 0 and then 1 minus y times f of x, which is the f of x is just a probability. So it's kind of an all or nothing loss in some ways too. It's also kind of a weird one in that it's much harder to train using this because it doesn't have a very nice gradient. That's another issue with the hinge loss is this function is very ugly. It doesn't have a nice gradient at all. And the reason it has this max is kind of an almost like a ReLU where you don't want to have anything negative. So your loss is guaranteed to be positive in this situation, and you don't want to have anything negative. But again, I don't want to spend too much time on it because we're not ever really going to use it. We're going to focus on cross entropy because that's what's used. I'd say 99 out of 100 times I've rarely ever seen the hinge loss actually used especially on a neural network. Now that's not to say it's never used. It is actually used on a support vector machine under the hood to train it. It is the loss function that's used, but it's not primarily useful. It's not that useful with neural networks. It hasn't shown to be that useful, but it could be used in theory. Okay, I'm just going to go through that. So I'm just going to go through this. I'm not too worried about hinge loss, so I'm just going to go past it. So one of the issues, that I had mentioned earlier is it doesn't have a gradient. It has a very ugly kind of gradient. So it's for this reason, it doesn't really perform well with training of neural networks because we really rely on that gradient in the gradient descent algorithm. So using this loss function can actually hurt the training process of a neural net more than it can help it often. Oh, that's interesting. Loss functions and metrics and deep learning. Thanks for sharing that. So there's other variations on the hinge loss. There's squared, which can square this, which attempts to make it better, and attempts to have slightly different penalties on mistakes and make it a little bit better in terms of the gradient, but still not nearly as good as what we see with cross entropy. So it does like using the squared version helps a little bit for gradient descent, but it's still not nearly as good as the cross entropy. So bottom line is we will stick with cross entropy, but just showing you that there are other loss functions out there that are sometimes used, albeit rare. There's rarely ever a reason not to use cross entropy. It's so effective at pointing out our mistakes in terms of those probabilities. There's really no reason to use anything else unless you have a really good reason to. Okay, so to wrap up the lesson, we're going to just review forward and backward propagation and then talk a little bit about some regularization ideas, which are a couple of ideas to help prevent overfitting. Just to remind us that, overfitting is a huge issue, especially with neural networks. So we'll just briefly talk about that towards the end. And we'll see those ideas come back up when we start building our own neural networks, especially. But let's talk about forward propagation just to remind us of what that really means. So forward propagation really revolves around sending data forward through the network in order to make a prediction. So whenever you hear that word forward prop or forward propagation, that's just referring to the idea that data kind of propagates forward from layer to layer to layer to layer. And we know what's actually happening there on every layer is really what we're doing is taking a weighted sum, passing it through an activation. That output goes on to become the input to the next layer, and on and on and on until we finally reach the output. And so this is just the forward propagation. Now, when we have more advanced neural networks, there may be times where there's connections that actually go backwards. And so not everything is forward propagating in those kind of networks. And the prime example of that's going to be an RNN when we get to that later. But right now, data kind of propagates forward for us always in the kinds of layers that we've seen so far. Mainly just a weighted sum through an activation, and that just goes forward through the network to ultimately to produce some type of output. And remember, the output is going to be different depending on the network. It could be a single value. If it's like a binary classification, it could produce a single probability. It could even be a regression, right? So if it's a single output like this, it could be a regression, might be a binary classification, or we might have more than one output node, or I should say neuron, which would be like in a multi-class classification. We might have three output neurons, or 10, or 1,000. Depends on how many classes we have we're predicting. And remember, those middle layers there are typically called the hidden layers of the network. We usually have our input layer up front, which matches the size of the input. So if we have kind of n features, we have n input nodes, and that just orients our data to kind of start flowing forward. And our hidden layers are going to be configurable. So of course, we're going to practice this today, like building out these hidden layers, especially in TensorFlow. But that's something we're going to be interested in doing is kind of setting up and architecting these hidden layers and architecting the output. Of course, as I said, the output depends on the problem, if it's regression or classification. Okay. So forward propagation is a good analogy to it if you think about it is kind of like our linear regression, right? In linear regression, and this is a very, very basic example of it with one feature and kind of one weight and one bias. So in this situation like this, forward propagation is just putting in our data and computing the output from the line, which is computing this y. That's what we're doing in forward propagation of the network. So what we imagine for the neural network is this is much more complicated. It's a weighted sum through an activation over and over and over again. So it's repeated quantities of this over and over and over again in our layers. So it's much more complicated, but ultimately it's the same kind of idea that we had in linear regression. We're just sending a data point in and getting an output back. And this is kind of like in linear regression, that's kind of like forward propagating. We just put in an input and it generates an output. Same thing with forward propagation. We're generating an output. It's just obviously the model is much more complex. There's more layers, there's more computations going on than just mx plus b, right? Just a basic linear regression. Okay. So I wanted to show this demo that kind of goes through forward propagation and just reminds us of sending data through these layers. So if you go into lesson 4, it should be the only notebook there. So you want to pull that up. I will pull that up as well. All right. So it should be this notebook. I just wanted to go through this to show us, just remind us of forward propagation and kind of how data flows throughout the layers. So hopefully you have this demo. This is, again, in lesson 4. It should be the only demo there. Okay. So we're going to use NumPy here and maybe some plotting. So we have PyPlot PLT from Matplotlib. Pretty standard. Now we're going to generate some random weights. So remember, this is what happens in a typically in a neural network. Whenever we initialize that network, it's going to have random weights to begin with. So this is not out of the ordinary for a neural net to kind of start with random weights. That's what's going to happen. Now this is mimicking this 11 here is just, it's nothing special, but it's just saying we have 11 elements. So this would be like we have 11 features and we have 11 weights and one bias. So this would kind of be like a linear regression that has these 11 features, 11 weights and one bias. So just kind of like that to initialize those random values. So if you look at this weights array, it's going to have 11 elements. The bias has one element, and the inputs have 11 elements as well. Now, we could take a look at the ReLU activation. So remember, the ReLU activation takes whatever input comes into it, and it computes the maximum between 0 and that input. This is the ReLU, right? Very, very basic nonlinear function that most of the time is just going to return whatever it was as long as that's positive. Very simple function, so we're just defining that. Now, hopefully this looks familiar here. So forward propagation for a single layer. So this is really mimicking a single layer in a neural net. Because if you think about it, what's happening is we are taking the sum of the weights times the inputs, which is what the dot product does, right? It's the sum of the weights times the inputs plus the bias. So we take that weighted sum, and that gives us this, and we put that through the activation. So that value is then going into our ReLU and producing an activated value, which is the output of this layer. So this is our forward propagation. We get this value. So we are forward propagating this data through this single, very, very simple layer, which is just has some weights and a bias, and then we pass that through a ReLU activation. Now, when we do TensorFlow, it's going to look much different than this. When we build out our network, going to be different, but this is the main idea under the hood of what we're doing. So hopefully this jogs our memory on what forward propagation is doing in the code. Weighted sum through an activation. We see that again. Now, we could calculate a potential error here. This would be like computing our loss. So if we come down here, if the target was 1, we could compute the mean absolute error, which is kind of what this is doing, is taking the absolute value between the prediction and the y. So this is mimicking the mean absolute error loss function. That's all that this is doing, because it's taking the absolute value and we would total that up. But there's really only one entry in this. So the sum is just it's just the single value. It's not really, there's only one error, but obviously if we were doing mean absolute error, we would total this up and then divide by the number that there are to average it. Actually, we wouldn't even take the sum. We would likely just call the mean, just do the mean to get the average of the errors. But in this case, there's only one entry in the error. So this is our mean absolute error for the loss. And we'd be often running with that. Like we could use that to go back and update our weights with a gradient descent update, all of that. So just reminding us of kind of the typical forward propagation, compute loss, back propagate, right? That's what we would actually be doing in reality. We could compute the mean squared error, which would be doing this. So instead of absolute value, we could compute the square. That'd be another option for our loss that we could use for this kind of regression example. And so the sum of squared error is 2.47. Okay. All right. Really simple example, but just wanted to remind us of kind of what forward propagation is doing, which is mainly this idea, weighted sum through an activation. And when we have a larger network, that would be occurring in many, many layers potentially, right? This weighted sum through an activation, and it would be in this network. It would be kind of managed doing that process. Okay, so let's remind ourselves of back. So forward propagation is just sending data forward, weighted sum through activations mostly. let's remind ourselves of backpropagation, which is going to be, remember, it is our way of going back and updating weights throughout the network based on the loss that we calculate, and particularly the gradient of that loss, because there's a gradient descent formula that dictates how every single weight should be adjusted. And remember on Monday, we did that very, very detailed calculation, which I encourage you guys to go back and kind of look through because I think it's a really good example that goes step by step. And I was saying the math isn't that important in terms of those gradients. I don't think it is, but I think the process is really important to understand that we are, going backwards in the layers to we're going backwards in order to adjust all these weights, right? We start from the end of the network and work our way back towards the front, updating all those weights. So backpropagation is really important for training. It's not important for predicting. So once it's trained, we will never do backpropagation unless we are going back and retraining. So backpropagation only occurs during the training process. Once a model has been trained, we only are doing forward propagation, right? Because we're producing predictions. So we're really only doing backpropagation during the training process. And hopefully that makes sense because the training process is what is adjusting all those weights. So of course, in order to do backpropagation, we need to compute the error. So once we've done forward propagation, we can compute the error based on our loss function that we have. And of course, the typical thing we use in the loss function is going to be whatever our model produced from a forward propagation perspective, whatever our neural network produced, and the actual label. So this is where I said last time, we really need the actual label. This is still a supervised learning problem. Really need those labels in order to compute our loss. Really need that loss in order to update all of our weights and adjust our network to actually learn anything meaningful, right? We need this loss. So what we just learned is we should be using cross entropy in a classification problem. We should be using something like mean squared error in a regression problem for our loss. And of course, we'll be able to set all that up inside of TensorFlow or PyTorch. They manage that for us. So remember, the backpropagation is utilizing or is being utilized by gradient descent because the gradient descent gives us the formula for what the weight update should be during the backpropagation process. And if you guys remember, I drew this picture, which I think is a really powerful picture, is this kind of idea that if we have, this is a graph of our loss function. What the gradient descent is really doing is finding out where we are on this, which is our loss value. So we know, because we can compute the loss, we know where we are on this, and we're taking steps towards the minimum, right? We should be taking these kind of small steps down this way towards the minimum of the loss down here, which once we get to that point, we have a very good model at that point, right? We basically have no error or minimal error, at the loss minimum. Back propagation, though, is going to take every one of these updates. So when we take a step, and we know, like when we take a step, that the step is going to tell us the formula for how we should adjust the weights. And really we need to utilize those calculations throughout the network to update all of those weights. And that's what backpropagation is going to do, is propagate those weight updates from back to front, according to this gradient descent formula here. So gradient descent plays a really important role in computing what our weight update should be. And then backpropagation propagates those weight updates from the back to the front. Okay. And then we had a picture like this. Remember, I drew a picture kind of like this earlier on Monday where we looked at the backpropagation really relying on forward propagation in order to produce the quantity of what do we have. And then we compare what we have to the label, and then we use that. That is what helps us compute the loss. Ultimately, the loss is what influences the gradient descent update, right? And that update gets back propagated throughout the network to adjust the weight. So you can think about like training a neural net. I think a really good analogy of it is kind of like we have a million little knobs and we're coming up with a formula that's telling us how much should I turn every little knob. And back propagation is saying what I should do is start with the knobs that are closest to the end. Start with those knobs, turn those however much I need to. Those knobs helps us compute how much I should be turning earlier knobs, right, that are in the front of the network. And so then by the time I do one training iteration, I've made all the little tweaks to my knobs that I need. And now I'm set up the next time around to hopefully do better. That's the idea for the training. So, ideally, when we make an adjustment, that's kind of what this slide is saying. When we make an adjustment in backpropagation, we should be doing better the next time. And what we should see visually, like if we were to plot the loss over the course of the training, um, we should see that decreasing. Things should be getting better over the course of our iterations, right? So maybe the loss starts somewhere up here. It should be getting better and ideally flattening out to kind of a minimum as we go through the course of the iterations. What we do not want to see is increases, right? We don't want it to kind of do this. That would be bad. We don't want that to happen because then that means that it's not really training. It's not really learning anything at that point. We want it to keep decreasing. And something that we're going to talk about coming up shortly is we really want to be cautious about this is like, yes, we want it to be decreasing on the training data, but ideally, if we like once we make all these adjustments, something we can do, we haven't really talked about this that much, is that when we make these adjustments, we can apply that network to test data that's been held out. And we can generate an equivalent graph to say, okay, what is our loss function on test data? And ideally, that's also decreasing. That would be nice. Like, so this blue line is the loss that's generated on a holdout set of test data. And that's actually going to be one of our strategies is to do a train test split on our data, just like we did in machine learning, and then evaluate our performance on the test set kind of simultaneously. So we train on the training set, make all of our backpropagation changes on every iteration. What we should be able to do is apply that new network, the adjusted values of the weights, the network, on both sets. We should be able to apply it on the training set. We should also be able to apply that on the test set and see what our performance is. Ideally, we see the same kind of trend. We see the loss decreasing on that test set over the course of the training. It should be getting better and better and better as well. What would be bad is a divergence of these two. So what I mean by that is if we drew a graph like this, let me go back and redraw this. So if we had our loss and over the course of our iterations, what we do not want to see is a decrease. This would be on the training data. So this would be on the training data. And then what we don't want to see is a divergence on the test data. So in other words, if we apply this to the test data, it kind of tracks initially and then kind of diverges away. This is kind of a difference, that's significant difference there, right? We don't want to see that because that would signal an overfitting. Overfitting. That would signal an overfitting. And why is it overfitting? It's because on the training data, our loss is decreasing very steadily and it actually gets pretty low over the course of the iterations. That's great. But there's a big difference on our test data. That signals that we're overfitting to our training data and not able to generalize our network to test data because our loss is much higher. So that divergence is a very clear picture of overfitting. So it's something we're going to be on the lookout for. What's really cool is like TensorFlow in particular actually gives you the ability to generate this plot during the course of the training. So every iteration it can update this plot and we can see it in real time how the training is progressing on these two sets of data. And that way we can kind of see that divergence occurring and then kind of stop it. Say, I don't want to keep training because I've already seen enough on the overfitting this divergence. So we'll see that when we get into TensorFlow is there is that ability to kind of visualize our training process, which is pretty helpful. If it's underfitting, what do you think? What would be a sign of underfitting? High. Yeah, it should be high. Because what is the loss function track? It tracks our mistakes. It gives us a distance, which is a distance between the actual label and our predictions. So the higher this distance, the more error we have. So the picture for underfitting would look something like this. Yeah, basically for underfitting, let me try to draw it alongside this graph. It would be, let me do it in purple. So for underfitting, it might be much higher, kind of like this. It basically never decreases. It basically never decreases and stays up way too high. The loss is just too high in general. This would be kind of underfitting. It actually, and even worse is if it kind of started increasing. That would be underfitting as well. It's just not performing very well. Our loss is either increasing or staying kind of stagnant and it's too high. If we add a hidden layer, is there any impact on this graph? There might be, yeah. So if we add a hidden layer, there's no direct way to know if it's going to help us on this graph. But that if we are underfitting, remember what underfitting kind of signals. It signals that our model is too basic. So if we're underfitting, one of the things we can do is maybe add a hidden layer. That might be something we want to do if we're underfitting, because maybe we need a more complex model. Okay. Now, on the reverse side, if we're overfitting, maybe our model is too complex and we actually want to remove a hidden layer. We have too deep of a network. That could be the case too. Does that make sense? So like underfitting and overfitting tell us maybe what kind of adjustment we should make to our network. Should we remove a layer? Should we make the layer smaller and less neurons? You know, those things we can kind of tell from a graph like this. All right. Let's talk about regularization. So we're kind of talking about that now in terms of overfitting and underfitting. And that's really what regularization is getting at. We talked about regularization actually a little bit in regression. Remember, regularization was involved us doing something like lasso or ridge regression, where we added penalties to combat overfitting. So with neural networks, you know, we can also talk about regularization because neural networks actually have a tendency to overfit. They are very, very prone to overfitting because they are, remember, things that are very complex tend to overfit. And neural networks are very complex. They can be very complex with many, many layers and many neurons. And so they can be easily susceptible to overfitting. And so we have a picture kind of like this, where I just drew something exactly like this. So, you know, we can definitely overfit in a situation like this where maybe on our training data, we have a picture like this, but then on our test data, we're kind of tracking with it, and then we kind of diverge, would be certainly an overfitting situation, because there's a huge gap here that's just growing and growing and growing between our training performance and our test data performance in terms of the loss. So that's overfitting. And this can easily happen. If you think about also the training process of a neural network, there's usually many iterations, and every iteration we're sending all of the data forward in order to generate the average loss, which updates all the weights. And if you think about it, we're making all these adjustments to all these weights just the fact that we're doing that and we're doing it so many times in these iterations means that the neural net, just the training process makes it potentially susceptible to overfitting, just relatively easily to overfit. It's such a complex model. There's so many iterations. Every iteration seeing all the data. It means it can overfit really easily to training data and struggle to generalize to new data such as a test set or in worst case scenario, like actual predictions that we need to make on real life data, right? So it can overfit pretty easily. Um, we're going to discuss a couple of ways to combat it. One way to combat it that is shown here on this slide is what is known as early stopping. So early stopping is a very interesting idea that PyTorch and TensorFlow both have an early stopping algorithm. And essentially, what early stopping will do is keep track of the loss on the test and the training. And if it sees a large enough divergence, meaning there's a divergence here that's greater than some threshold. So if this distance between the training loss, if the distance there becomes greater than some threshold, let's call it alpha, if this distance becomes big enough, then we kind of trigger a stop. Basically to say, I don't want to continue because my test evaluation of loss is starting to diverge away from my training. So I should just stop it here and stop training here, and maybe that's good enough. Or I should like I stop there so I can make some adjustments. I don't want to keep going. So this is actually built into TensorFlow and PyTorch, and it's called early stopping, and you're able to set that up. Another thing you're able to set up with early stopping is basically like a grace period to say, okay, if I see this distance greater than some threshold, I'm going to trigger an early stop if I don't see an improvement in the next X number of steps. So as we go through the next 10 iterations, if I don't see an improvement and I don't see this distance drop down back below alpha, I'm going to stop. So you can give yourself kind of a grace period there too in the early stopping to give it a chance to recover. Maybe it's just bad, it gets unlucky and it's just bad on that iteration, and I make some adjustments or the training adjusts the weights, and then it starts to do better on the test set and it goes back below that alpha in the next couple steps. And therefore we've recovered and everything's okay. So you can give yourself some grace there. And that's all configurable in the early stopping algorithm. And we're actually going to see an example of that when we get in lesson 5 when we do TensorFlow. So that is one thing we can do to combat overfitting is to just stop our training early. We don't want to let it keep going if it's performing poorly on test data. Don't let it keep going. That's basically the simple answer there. Just stop it. And either stop it and use that model from the point you've stopped, or try again and maybe make some adjustments to your architecture. Maybe remove a layer, lower the number of neurons, something like that, and try again. So early stopping, we're going to see that later. So that's one way to combat overfitting is to just stop the training early. A couple of others that are widely used are what are called L2 regularization and dropout regularization. And both of these are basically ideas that are used to mitigate against overfitting. Now, this one we've actually seen before with ridge regression. So this is very analogous to ridge regression. And remember when we did lasso and ridge regression, this is actually the same idea, is we're going to introduce a penalty in the loss function in order to penalize large weights, which is supposed to help prevent overfitting. So it's kind of the same exact idea there in like when we did ridge and regular linear regression is we wanted to discourage any one weight from dominating. So we penalize very large weights. We can actually do the same thing in neural net training and penalize large weights or any one weight from being dominant with a similar kind of penalty term in the loss function. That's one way to do it. And we're going to talk about dropout regularization, which is a whole different concept. This is actually a very interesting concept that is widely used in neural net training, way more than L2 regularization. So dropout is widely used, and we'll actually use it quite a bit in our examples, especially when we get into TensorFlow. So I'm going to talk about dropout regularization coming up and tell you more about what that is, but it is definitely widely used. L2 regularization, not quite used as much, but just something to be aware of that we could do is just basically adjust our loss function to to prevent overfitting. So what does that mean? We basically have some type of penalty term that we add to our existing loss function. So in mathematical terms, this C0 is just our initial cost or loss function. Whatever we had, we still have, but we add in this penalty that discourages large weights. So it penalizes weights with a squared penalty there to kind of discourage those. So when you're training, you're going to get an extra penalty if you have a really large weight. And so this helps make the weight adjustments and control those so they're not overly, overfit to the training data that it's being trained on. So it's the same idea we had. This formula might look a little familiar. It's because it is very familiar from the ridge regression. It's exactly the same idea that we had there. And the loss function there, if you remember, was just mean squared error. But here, in classification, it could be cross entropy. In regression, it could be mean squared error again. So same kind of penalization that we're doing that we had back then. Okay. So this is an option, and it's actually not too bad to set this up in PyTorch or TensorFlow to take an existing loss function and just make an adjustment to it. Most of them have a regularized version of the existing loss functions like cross entropy and mean squared error that you can just grab out of the box and use. One thing to be aware of is if you do use this, basically it can take longer to train because because it has this extra penalty, the gradient is a little bit more complex. And so the back propagation is going to take a little bit longer. So the training can take longer with this regularization in there. That's the only kind of caution. Okay. So that's one approach is to add a penalty to our loss function, which might make the training take longer, but it's designed to discourage large weights and prevent overfitting, just like we saw with ridge regression. So that's one option. Now, another option that is widely used as a very, very interesting idea is randomly getting rid of neurons during the training process on every iteration. So what you can imagine is that each iteration of the training, I basically select neurons, and with a certain probability, I'm going to turn them off. So it's as if they're not there. Now, doing that has a significant effect on the training because on that iteration, I'm going to basically have a much different architecture if I delete a bunch of neurons. And then maybe on the next iteration, I delete different ones. And then on the next iteration, I delete different ones. So it's not like they're permanently deleted. It's just during that iteration, they're going to be turned off. And so they're not going to be involved, and their connections are not going to be involved during every training iteration. And this is a very clever approach because essentially what happens during the training is your model learns how to adjust the weights across all of the iterations with some of the network turned off on every iteration. And the idea behind that is to prevent overfitting because you don't have a full network with all connections on every single iteration. And that basically prevents having over complexity in your model. It's a very interesting approach. So again, just to reiterate what dropout is doing is it is drop. The reason it's called dropout is because the deletion of the neuron is actually called dropping it out. So if I had a network like this, and let's say it produces one output, and so there's obviously a bunch of connections in this network. So it'd be, kind of like this. Um, and then connections like this. Essentially, what we're going to do is on every iteration, we choose with a certain probability to drop out a neuron or multiple neurons from each layer, from each hidden layer. So let's say we on this hidden layer, like on the first pass, we might drop out this neuron with a certain probability, right? It has a chance to be kept. And that's the probability of keeping the neuron is actually a hyperparameter that you have to choose whenever you use dropout. And it has an effect. Like if you were to lower that probability to be something really low, then you're basically you're risking not having anything and you can underfit, which could be bad. If you keep everything, like if you have a really high probability, then basically you're going to ensure all your neurons are kept, which basically will potentially lead to overfitting anyways. So you want that probability to be somewhere in the middle. You want a decent chance of being dropped out, but not overly low or overly high. And remember, if it's overly low, then you're going to drop out way too much and have an underfit model, a very simple model, because you're going to just delete so many neurons. You're not going to be able to train effectively. So that's kind of the worst case is you like drop out everything and all of a sudden you're not learning anything at all. You don't have any neurons to use. So you have a very underfit model in that case. So you don't want that to happen. So you want this probability to be ideally like something like 0.4 to 0.6, somewhere in that like middle range, maybe 0.5. You want it to be somewhere in there, but it is something you can change during the training. You could play around with it and hyperparameter tune, try out different probabilities for the dropout. Now, one thing I should also clarify is dropout is not permanent. So this is only during the training that the neurons get dropped out, and it changes iteration to iteration. So they're not permanently going to be deleted because on the next iteration we may keep this guy and then turn off this guy and keep this guy. So it's every iteration that probability resets, and you have a new chance to drop things out on each iteration. And then when the model is done, you're not dropping out in prediction. So in prediction, you're using the full network. Like when you do a forward propagation and you're sending data through to make a prediction, you're not going to turn off things randomly during prediction. This is only used during training. Only used during training, and it's the purpose of it is to prevent overfitting. It's a very clever approach to preventing overfitting, is to basically artificially kind of change our complexity of the model by turning things off and on. It's a very interesting approach. But one of the things we're going to see is setting up dropout in our network is a really easy process. It's not like in terms of training, it's not trial and error. Essentially, we'll just set up the dropout layer and have the ability to drop out any layer that we want. So we could set up and say, I want to drop out this layer, but of course, I don't want to drop out the output. We never want to drop out the output, and I don't want to drop out the input. I don't want those to be cut off at all. I only want to drop out the hidden layers. So we should only be doing this to hidden layers, right? I should not be dropping out the output and certainly not the output, and I shouldn't be dropping out the input. So only hidden layers should I really be doing this to. Okay. So here's a good picture, better than what I drew, is like if you're dropping out things, and again, the whole goal is to do this so your model generalizes better by during the training process by kind of strengthening its learning ability. It's not getting overfit by having everything activated all the time. It's kind of learning on the fly by, getting stronger in different areas by turning off certain neurons every single iteration. You get a picture that's kind of like this. When you turn off a neuron, you are severing their connections, right? So you can kind of see in this picture, you go from something that's really complex, which is the whole point of preventing overfitting, right? You go from something really complex to something simpler. That's the idea. But we're not going to keep it simple permanently. So on the next iteration, it might look slightly different because we would drop out different neurons, right? And so we're basically going to do this over and over and over again. And it's a good method. It turns out to be a really effective method to prevent overfitting by going, and the idea is just to kind of keep alternating from complex to simple, and that way you kind of distribute your learning very effectively, which is supposed to make it generalize. Okay. Does that make sense on the overfitting or the prevention of overfitting, like how it's preventing overfitting? It's going from complex to simple and really alternating that over the course of the training by it's all random. So we randomly choose which ones to turn off and on. I really want to emphasize that it's not permanent because like it could be like this on one iteration and then the next iteration completely different ones are turned off. And once the model has been trained, nothing will get dropped out. We'll use the full model to make a prediction. It's just that what's the idea is the training is supposed to prevent the overfitting so that by the time we get the full model, it has a better chance of generalizing because it's basically been taking on these different forms and learning in different ways the whole time during the training process. So yeah, this is called dropout. Dropout is very popular. It came around in the late 2000s, like early 2010s, I think it was invented. And it's been widely used ever since in most training of any neural net will use dropout to some extent. It's a very popular approach to prevent overfitting. And again, overfitting is a very prominent issue in neural nets. They tend to overfit very easily because they're so complex of a model. This helps eliminate complexity, right? It makes the model simpler every iteration. It's a very, very neat approach. So again, one of the things to be aware of is that probability of retaining a neuron. So that is known as the parameter P. And so when you have a very low P, meaning you have a very low probability of keeping a neuron, so most of it gets dropped out, you have underfitting. That makes sense. So if you go back to this picture, if we had a low P, basically everything's being turned off. So you have an overly simple model. Overly simple, so you're underfitting, right? So you don't want to do that. And so this graph on the next slide kind of shows that happening. Whenever they had a very low probability of being kept, they underfit, which is what this is showing. There's a high rate of error. The loss function is pretty high on the training and the test set. They're underfitting. Now, as they increase the P, which is going this way, and they got more into this realm, they got more into this realm, they saw better results. So they had low training error, low test error. It's still like not perfect. There's still some level of overfitting here because there's a gap between the two, but it was better. It wasn't as underfit as in this area here. So that middle ground is generally a good spot to be with a, kind of a 50-50 chance of turning off a neuron. Seems to be a good probability. Now, as they kept going, the overfitting got more drastic, right? Because what this means when the P is really high in this range is you have a really high chance of keeping every neuron. So you're basically learning on every iteration with a full model.
you're not turning anything off, which is keeping it overly complex, right? So when you have a very high P, basically everything's going to be turned on. It has a very high chance of being turned on, which means you have a you basically have this, which is a more complex model. So you're more at risk of overfitting in those situations. So that's kind of what they discovered, which makes a lot of sense intuitively. Like this just kind of verifies what we would think would happen, where you get more overfitting the further to the right you go on those probabilities, more overfitting. So very interesting. And by the way, this number, so if you're reading this slide, this number refers to the size of the layers. So it's 784 because the images on the MNIST data set. So if you guys remember, MNIST is the handwritten digits, right? Those are the images of things like a 2 or a 1 or a 0 or a 9 or whatever, right? Those are those images. So there's the look at what the output layer is. It's at the very end here is 10. That makes sense because it's the digits 0 to 9. So there's 10 different classes that we could predict. So the output layer needs to be a 10. That hopefully resonates and makes sense. And the input layer is 784 because it's a 28 by 28 image resolution. So 28 by 28 is 784. So the input has 784 pixels in total that are in this 28 by 28 image. And then they have 2048 neurons in this layer, 2048 neurons in this layer, 2048 neurons in this layer, and then 10 output neurons for the classes 0 to 9. Okay. So on that architecture is what they applied the dropout to these layers and came up with these numbers. Okay. So by the way, we're going to build a model that looks like this. We will build a model that looks almost exactly like this architecture. We'll practice that on the MNIST data set with those images. Okay. So a lot of ground that we covered there in lesson 4, but that pretty much wraps up lesson 4. We talked about deep neural nets and how to do forward propagation, back propagation to update all the weights. We talked about regularization, which is really helpful, especially dropout, to basically turn off neurons to prevent overfitting. We also talked about loss functions, which are really critical for doing the training process, right? We need to know what the loss function is, so that we can evaluate the error that is very critical in making that gradient descent update for the network. Okay. So if you want to pull up those notes, we're going to be moving on to lesson 5, which is going to be the first of 2 lessons that really get into our 2 frameworks for building neural networks, which are going to be TensorFlow and PyTorch. So this lesson will cover TensorFlow, and lesson 6 will cover PyTorch. And of course, along the way, we're going to do examples with both so we can start to see how we actually build neural networks and see what goes into the training process and building in the code, right, inside of our Python. So that'll be pretty exciting, I think. So by the end of this lesson, we want to see the main thing we want to do is get some hands-on experience with TensorFlow. So this lesson actually has a lot of slides that are with some different aspects of TensorFlow that we won't actually be touching, like TensorFlow Playground and TF Learn. Won't actually be touching those too much. So in the slides, you're going to see me skip around a little bit because I want to get to the parts that we are definitely going to use, which are mainly going to be TensorFlow and the underlying or the library that kind of goes on top of it, which is Keras, as kind of the interface to TensorFlow to help us build neural networks. So that's where we're going to focus our attention. I know there are other slides in here about different aspects of TensorFlow, but we won't actually be using those really for anything. And so we'll be using just Keras mostly to practice building our nets and training them. So that's where we're going to focus our attention in the lesson. Okay. So let's just get a basic introduction to TensorFlow itself. So if you guys remember, we talked about TensorFlow at the very beginning of this journey, where we talked about these frameworks being developed to help build and train neural nets, and TensorFlow is one of them. And so it is an open source Python framework for building neural nets, and it was developed by Google back in the day to help them build and train neural nets, and it was open sourced in 2015. So not that long ago, but by now over 10 years ago, it has been kind of open sourced and available for free use. Now, TensorFlow itself is a remarkable library. It basically handles all of that computation of forward and backward propagation, especially that backward propagation that we saw that was so tedious, right? Computing all those gradients and then multiplying all those pieces together to generate a weight update is very tedious and hard to keep track of, even manually. But what TensorFlow does is actually keep track of that very effectively in kind of a graph structure. So TensorFlow is really a library that manages the data graph and data flow of neural network data, which is primarily going to be tensors for us, which are basically like matrices. So it's this really remarkable library to manipulate that data in this kind of graph network format, which mimics, a neural net. So TensorFlow has a bunch of stuff that comes with it. Obviously, the core library is something we'll use mainly the library that's built on top of it, which is Keras, that kind of interacts with TensorFlow. But it also has surrounding tools and other community resources such as documentation that's really amazing, that we will look at from time to time as we need to. One of the tools that TensorFlow has that we'll look at later is called TensorBoard, which is a really amazing tool to kind of visualize that training process. So that the kind of graphs that I mentioned, where you can kind of see your loss over the course of the training iterations, is something that TensorBoard can do, which is a tool that was created by the folks who made TensorFlow. And they have many other tools like that. They have tools for like serving models, like in terms of deploying them and making them usable through like APIs and things like that. So I have a lot of other tools out there, but we'll focus our attention on primarily the libraries that enable us to build and train neural networks. So the reason TensorFlow is called TensorFlow is primarily because the fact that it manages this underlying graph of tensors. So all the data that flows through this graph is actually in this tensor object, which is very similar to kind of a NumPy array or kind of like a pandas data frame. Very simple, very similar kind of idea. So, but in reality, we can think of a tensor as kind of a matrix like kind of data object that contains kind of multi-dimensional arrays inside of the tensor. So we've been dealing with data that's in a matrix format in terms of a data frame. So this was our data frame. The vector was kind of our NumPy array kind of structure. And now in TensorFlow, we're going to be working with tensors, which are going to be these kind of like matrices of matrices, essentially. And so TensorFlow manipulates data that is converted into tensors under the hood of TensorFlow whenever we pass data into the network. So it's just useful to know that the data that TensorFlow is manipulating is actually tensors and not really data frames, not really NumPy arrays. But that's not to say we can't start with this kind of data and use it with TensorFlow. Of course we can, and TensorFlow will manage converting data frames or converting NumPy arrays into tensors under the hood. That's something that they do, but manages kind of the computations in this tensor kind of data structure in the same way that, the models that we've built to this point mainly manipulate things like data frames, right? They manage and manipulate data frames. TensorFlow manipulates tensors. But luckily, it will convert things like data frames into a tensor as needed. So we don't really need to worry too much about that. Just pointing it out, that's where it kind of gets its name, is that structure, that tensor structure. Okay, so mainly what we're going to be using TensorFlow for is, of course, for building and training neural nets, but TensorFlow as a library has a lot of other features to it. It has things on top of it that make life so much easier when it comes to building neural nets, and that's what we're talking about here with these high level APIs, which would be something like Keras. So we'll be able to utilize that to manipulate, like build and train neural networks. It'll be really easy to do with a library like Keras built on top of TensorFlow. TensorFlow also has a bunch of models that are built into it that are already trained. That'll be really useful for things like computer vision, where we want to pull things off the shelf and maybe fine tune it, or do what's called transfer learning to it to make it better on our own data. So that's really cool. It has a bunch of pre-trained models already built in. It can take advantage of GPUs really effectively. So TensorFlow manages GPU compute really, really nicely. It interfaces with GPUs really easily, which is a great feature for it because we're going to need that, especially to train computer vision models later on down the line, like when we get into object detection, things like that. GPU is going to be really important. I already mentioned TensorBoard. That's a really important visualization kind of library that TensorFlow provides to be able to plot a graph like this in real time, where we can kind of see the loss over the course of the iterations and see that kind of updating in real time as iterations are finishing, kind of see how that loss is progressing. And that can inform us if we need to stop, if we should let it keep going, all those kind of things we can kind of visualize with the help of TensorBoard. So we'll see that later on. As I said earlier, TensorFlow also has features that help for model deployment. Now, we won't really use that too much, but they do have that capability where you can build a neural network and kind of easily deploy it behind an endpoint. We won't really need to do that, but it does facilitate that in the library. So if we needed to, we could easily do that. Okay, so I hope it makes sense why TensorFlow was such a big deal, especially after going through our examples of like forward and backward propagation. When you're building a neural network, there's so much computation to keep track of. And we saw that, right? We saw that kind of firsthand is, forward propagation, you're multiplying and doing this weighted sum through an activation function, and you're doing that and passing that data forward throughout the network. And that's a lot of computation, especially if it's a deep network. But man, that back propagation was so tedious, right? Computing the gradients, that is challenging. And then keeping track of that and multiplying those together with the right terms and propagating that backward throughout the whole network is a very tedious and intensive process. But libraries like TensorFlow and PyTorch manage that for us, which is a huge deal. And that's why they were created, to really manage that computation and help us train and build neural networks. So that's why we need a library like TensorFlow, is to ultimately manage the computation that is inherent in a neural network. Is a lot. It's much more complex than any kind of machine learning model, right? There's a lot more going on with it. And so it necessitates these kind of libraries that are specialized in neural nets beyond scikit-learn. Scikit-learn was great. We've used scikit-learn for, so many machine learning models, but we really need to go beyond it to the specialized libraries for neural nets because there's so much going on with those. Okay, so as I mentioned before, under the hood of TensorFlow, and it's not like we necessarily need to know this, but just showing you kind of how it works, is TensorFlow will manage the network and break it down into really manageable chunks of computation by kind of organizing how that data flows and organizing that computation into really, really manageable pieces. So, for example, doing a weighted sum and passing that through an activation kind of gets broken down into a data flow graph that looks like this. So you can even see this here, like we do a matrix multiplication between the weights and the inputs, and that forms our weighted sum. That's just a dot product, right? Weighted sum. And then we add in a bias. So we add in a bias, which is what this does. So it manages adding a bias term here. And then it passes that into a ReLU function, which is doing our activation on this weighted sum, right? So everything that we've been doing, this weighted sum through an activation, is managed in this graph really efficiently to produce an output. And of course, the the deeper the network, the more sophisticated this graph looks. But this is just a simple, this would be like the perceptron, right? Weighted sum through an activation, it looks just like this, and on and on and on. So a more complex neural network is going to be represented by a much bigger graph here, but TensorFlow manages that under the hood, and it does that on purpose so that it can manage all aspects of the neural net. It can manage training, it can manage prediction by doing forward propagation like this. It can manage back propagation by doing all these gradients really effectively of the graph. So by putting it in this graph structure, it's able to manage our computation so effectively. That's the beauty of TensorFlow, is this data flow graph of tensors, and it manages it really, really efficiently. Okay. So basically everything I said is TensorFlow manages the computation through this graph. And it can also leverage parallelism by using GPUs. So it can basically optimize this graph execution as it needs to, parallelize things as much as it can. It can actually offload a lot of these calculations in the graph to a GPU, and that's something we will work with later on. So it's in that way very effective at managing the computation. So some of the benefits, as I said, using GPUs, it can parallelize things. It can be built in Python. This graph can actually be saved and reloaded really effectively. So the idea of putting things in a graph like this makes it really persistent. Like we can persist this graph architecture very easily and then reload it as we need to. So in that sense, we can always save our architectures and save any of our weights that are there, like this weight matrix. We can save. And so like loading and saving models actually becomes really, really easy in TensorFlow. And same thing for PyTorch. Everything that I'm saying here for TensorFlow is honestly applicable to PyTorch as well. I know we're going to cover that in lesson 6, but very similar, where PyTorch manages everything as kind of a data graph. And remember, PyTorch was made by Facebook. So they kind of made these libraries independent of each other to both try to tackle the neural network problem. And then they open sourced them to make it available for the community later down the road. But Google and Facebook were both working on neural networks quite a bit. So they had their own libraries to manage those, and they're both prominent today, right? TensorFlow and PyTorch. So when it comes to working with TensorFlow, there's kind of two approaches. One is to work at that graph level, which is kind of the low level of TensorFlow. So working at the graph level is sometimes known as TensorFlow core. It's just the core of TensorFlow. We won't do that. It's very complicated to do that. It gives you ultimate control over modeling, though, because you're controlling that data tensor graph. directly. So you get a lot of control and fine-grained control over building your models. We won't ever need to do that. We'll mostly work at the Keras level, which is kind of an abstraction layer on top of the graph. So Keras is going to be a library that sits on top of TensorFlow, almost in the way that like a Seaborn sits on top of Matplotlib or a Panda sits on top of NumPy, very similar way. Keras kind of is an interface to the low level graphs, and it makes it much, much easier to manage neural networks and training because we don't need to go into the graph level details. We can just stick at kind of a high level of building the models. So most everyone actually building neural networks will utilize Keras. If you're doing deep research and writing a paper and kind of really concerned with performance and coming up with new architectures, you may work at the graph level. We're not going to do that in this program because nobody really does that for the purpose of building a model. You would generally work at the Keras level, which is what we're going to do. Okay. So it makes it easier. And that's honestly what is practical is to work at that level because you could still do a lot. You could still do a lot in terms of building really effective models. It's just we're not going to be coming up with brand. So if you were to come up with a brand new layer, like an attention layer for transformers, you would be doing that at the graph level, the very low, low level. We're not assuming we're going to do that. We're just going to use what's already basically in our toolbox inside of Keras and build models off of that, which is plenty of complexity for us. Okay. So just to reiterate, some of the features of TensorFlow is that we are going to be it's open source, so it's easy to install even on your local machine. It'll be really easy to install. You could just pip install it just like you would any other Python library. It is free. And it supports building, basically doing GPU training, which is really, really nice. So TensorFlow will interact with GPUs really, really effectively, which is nice. Okay, so here's some of the advantages of working with TensorFlow. We've already talked about a lot of this, open source. It does GPU computation really easily, very flexible library in terms of the ability to build out different kinds of neural networks. It actually contains a lot of different layers that we may need. We're going to see that when we start building our own networks. The fact that it also has high level abstraction is really, really nice too. The fact that it has a Keras, we don't need to go into the graph level, makes it super approachable for us to get started and kind of learning how we would build and train neural nets. It's so much more approachable than having to get into the graph level details, which is very complex. Do we have to install locally or can we work in the cloud? No, you can work in the cloud. So the Colab has TensorFlow built into it because TensorFlow came from Google. So of course, Google Colab is going to have TensorFlow built in. You don't need to install it. So every Colab notebook can work with TensorFlow. In fact, it's actually really nice to work in Colab for this stuff because I think I've said before, Colab has GPUs for free. So you can connect to a GPU and kind of train your models on GPU really easily in the Colab environment. So I definitely encourage, especially for deep learning, to try to use Colab if you can. I think so. TensorFlow is also installed in the Simplilearn lab environment. So if you want to use that environment, it also has a GPU connected to it for free. So you can feel free to use that and it has TensorFlow set up in it. You would just have to install if you want to run locally. You probably would have to install because it's likely you don't have the TensorFlow package. And I can share some resources later on for utilizing the GPU locally, especially if you're like on a M1, M2, M3, M4 Mac. You can actually use the GPUs in the M1, M2, M3, M4 chips. You can actually use GPUs locally on those, which is really nice. Or if you have like an NVIDIA GPU, you can use that too. Either way. But I do recommend Colab strongly, because of its free GPU ability, and it all just works pretty seamlessly in Colab. Okay. So what's nice about TensorFlow as well is obviously everything is going to be in Python for us to be able to handle all of our neural network building and training. That'll all be in Python, but actually there's a lot under the hood, not that we need to know this, but under the hood of TensorFlow is a lot of like efficient C implementations that make the graph data flow as efficient as possible. So it's Python, but it's powered by C, honestly, a lot under the hood, which is a lot of libraries are like that. NumPy is very like that. It's basically an interface to low-level C code that's manipulating all the NumPy arrays. So TensorFlow is kind of no different. It has very efficient C implementation. It also has the parallel computation. It has parallel computation capabilities. This is something we're going to see that we can easily offload our computations to a GPU to get to have as much of it parallelized as we possibly can to speed up our computations. So what we're going to see is TensorFlow makes it, and PyTorch for that matter too, they both make it really easy to do that. So we'll see that later on. TensorFlow can run on many different environments, including mobile. And it's really important mobile to call out mobile on this, mainly because a lot of sophisticated AI programs that run on phones, like the Apple Intelligence, for example, are often powered by neural networks that have to run on a mobile device. So TensorFlow would be responsible for running that model, and so it has to be compatible with kind of edge devices like an iOS or Android or even like a Raspberry Pi, which is kind of a small computation platform. So TensorFlow works across many different platforms, which is great because people are interested in running neural networks on many different platforms, including those kind of mobile edge devices. Now, because it's open source, it has a really vibrant community. It's one of the most popular open source projects on GitHub. It still has a very dedicated team at Google that's dedicated to kind of maintaining it, even though it's open source. There's developers there that are kind of, focused on maintaining it and making sure it's in a good state. But it definitely has a very vibrant community. And one of the things that comes out of that community is really, really good examples and documentation. So I'll show us that probably later on today. The TensorFlow documentation is really, really good. So we'll utilize that in certain areas when we need to. Okay, so what we're going to be interested in, and we're going to actually get into this soon and then start building as well in our code. So that's coming up shortly, is using high-level abstractions like Keras. So the graphs are great, but we don't want to manage things at a graph level. That's very, very complex, as I've alluded to. So we want to be able to basically quickly prototype models, quickly develop them, and quickly train them. And we'll be able to do that using something like Keras because it'll make building a neural net and training it really only take a handful of lines of code, which is really amazing. It's actually remarkable how these libraries like TensorFlow and PyTorch, how easy they make building and training a neural net. They make it really easy to do, which is nice. And we've seen that before with, scikit-learn made doing machine learning really easy by basically making everything into a dot fit and dot predict, right? So Keras will be kind of the same thing and PyTorch kind of the same thing, making our life really easy in terms of building and training neural nets. So many different applications that use TensorFlow models that are out there today. So image recognition, videos, NLP, basically anything that uses neural nets. Transformers, of course, not listed on here, but anything that's doing it, anything with neural nets, often there is a TensorFlow model for it. Doesn't mean it's exclusively in TensorFlow. There may be a PyTorch version of it as well, but most of the time there's both, a TensorFlow version and a PyTorch version for many different models that are out there. They're generally developed in one of those two frameworks, if not both. So many companies leverage TensorFlow because they are using neural nets to do something. So like object detection, Uber, and a lot of self-driving is powered by neural nets. That TensorFlow helps provide. And many companies are using TensorFlow for different kinds of neural net applications, of course. So no surprise here to see a lot of big companies on this list. Google, not shocking, they created it. Of course, they're on the list. So some application areas, I mean, we've talked about these before, like medical images, diagnosing disease. So Google, for example, created this application called Germ Assist using TensorFlow, basically to make diagnosis on skin conditions, which is like pretty interesting using just pictures. So many like neural net applications are developed in TensorFlow. I mean, so many are developed in PyTorch as well. Those two libraries just dominate the market in terms of building and training neural nets. So the Twitter, or now X, their ranking of tweets to do like recommendation is all powered by TensorFlow. Google uses TensorFlow to do its search rankings. Photo sharing, VS Co. Uses TensorFlow to suggest filters. So many TensorFlow applications that are out there that are in use today. I mean, not to say there's not so many PyTorch examples. There are definitely those as well, but a lot of people chose TensorFlow. A lot of people chose PyTorch. They're both pretty represented in the community. So we can use it for text applications, and a lot of even up to LLMs, like transformer-based models, are built in TensorFlow, or PyTorch, or both. As I said, both very, very popular frameworks. So NLP applications, TensorFlow has been used for. E-commerce use TensorFlows for recommendation. So remember when I said recommendations, we studied recommendations and saw a lot of techniques to do that, like collaborative filtering and matrix factorization. Those are still used in some places, but a lot of places have graduated to doing neural network based techniques. And if you're doing anything with neural nets, chances are you're using TensorFlow or PyTorch to do that. And so many companies have adopted TensorFlow to do recommendation because they're using some type of neural net to do that. Pretty interesting. Okay. So what I wanted to do is show you one short demo on working with tensors, just so you can kind of see what the tensor data structure looks like. So I'm going to do that. I'm going to do this demo to start with. So we're going to start with the 5.02 demo from lesson 5, which is just going to be an introduction to tensors as a data type. And what you're going to see is tensors are very much like NumPy arrays, very much like data frames. They're just a basic data structure that TensorFlow works with. Now, these two demos I'm going to hold off on because they get into building a neural net. What I want us to see first is to jump ahead to the Keras notes here in lesson 5. So we're going to cover Keras first. And then once we've covered Keras in a few slides, work our way back to these two demos. So the plan for today is I'm going to cover this demo first. We're going to jump ahead to the Keras notes to get some information on how we can use Keras to build neural nets, and then get our hands on these two demos so we can see it in action. So these two demos are going to have kind of end-to-end examples on building and training neural nets. Obviously, we haven't learned that yet. So I want to jump ahead to Keras so we can see some of that, and then work our way back to these two demos to actually practice that. So that'll be kind of the plan. So with that being said, let me jump over to the 5.02 notebook, just so we can see some basic examples with just tensors as kind of a data structure. Okay, do you guys have this one? 5.02. This is the first demo in lesson 5. Okay, great. Okay, so inside of TensorFlow, you shouldn't need to run this. In fact, you can see it already says everything is satisfied if you do run this. This is just like for your local, if you want to run this on your local machine, you probably need to install these because you probably don't have them. So this would be for local machine if you don't have these libraries. You'd want to install them. They're already here in Colab, so it just tells us, hey, we already have all these. So nothing really happens. Okay. All right. So then we have some setup here. Now, these things are optimizations that are basically flags for TensorFlow to know if it should be using GPU or if it should be using CPU and if it should be making optimizations based on the GPU. So what we can do is basically disable GPU for this demo because we're not going to need GPU to do anything with tensors yet. We're only going to need GPU for later on when we're actually training more sophisticated models that are going to require it. So this is basically setting we're going to turn off GPU visibility here. So we don't use a GPU in any way because we don't need to right now. It's kind of a waste. It wouldn't be useful to us. And we're going to set this is just some logging output from TensorFlow in case there's any warnings or anything. So we'll just run that. Okay. So what I wanted to show you is, first of all, TensorFlow as an import is kind of like many other packages in data science and machine learning. It has an alias that is kind of an industry standard alias, which is TF. So this is an industry standard alias is TF for TensorFlow, right? So we can see as we import TensorFlow as TF, which is kind of the industry standard to alias it. So, just like we do NumPy as MP, Pandas as PD, TensorFlow is typically imported as TF. That's a very industry standard. So if somebody was reading your code and came across and saw TF, they would know what that means. They know it's TensorFlow that we're using. Okay. So in TensorFlow, as I said, the main data structure that gets manipulated under the hood that kind of holds our data for training and doing prediction with a neural net is known as a tensor. And you can create different dimensional tensors inside of TensorFlows, or inside of TensorFlow, I should say. The very the most basic tensor you can possibly have basically is dimension zero, also known as rank zero. So rank is equivalent to kind of the shape or the dimension that we had from like a NumPy array or a pandas data frame. So a rank zero is just a constant. It basically has no dimensions to it. It's just a single value. So in TensorFlow, you create a single value with tf.constant. So this creates just a single scalar value. It basically has no array dimensions, no matrix dimensions. It's like a zero-dimensional NumPy array equivalent. So what you can see is we create the tensor here and then we print it out. What you can see when we print it out is look at the data structure that it prints. It prints a TF tensor. That's mainly what we're seeing here is this is the kind of data that TensorFlow is going to work with is a TF dot tensor structure. So the TF, I should call that out here, the TF dot tensor structure is equivalent to a mp.array structure or a pd.data frame structure. It's equivalent to those, but it's just in TensorFlow, this is the primary data structure that's used is a tensor, TF tensor. This has no shape to it because it's zero dimensional. So it's just a single constant value of 4. It's a scalar. And you can see what its data type is an int32, which is just a default integer type for integer data. Okay, so we could make a one-dimensional tensor, which is basically just an array with basically a vector that has a few values in it. So a one-dimensional is still a TF dot constant, but you can see it now we have a list, or you could put a list. You could also put a NumPy array there. You can actually build a tensor out of either kind of data. And so this is just a single dimensional vector. And what I want you to see is look at the tensor now. So the tensor now has this array as its data, and it now has a shape of 3, comma nothing, which is to signal that it only has one dimension, and that dimension has 3 elements in its shape, right? So it's a shape of 3 nothing because it's just a single dimension. So that's a rank. That's what we would call a rank 1 tensor. It's just a single dimension. But again, the underlying data is a TF.tensor. This is what is manipulated under the hood of any neural net is a tensor structure. So just showing you this so you can kind of see what actually is being manipulated when we build a neural net. It's really this TF.tensors. All right, so we could build a rank 2 tensor, which is a matrix. So this is data that has rows and columns. It's 2-dimensional. So here we have a 3 by 2. We have 3 rows and 2 columns of data. And the other thing we can do when we build a tensor, so we use tf.constant to build the tensor. And so we put in this 2-dimensional array. We also specify that the data type should be float 16. So that's really interesting. The original data is just integers, but we actually have the flexibility to say, hey, I want you to put all of this in float 16 data type. So you can see when we create this tensor, it has this data and it's kind of casted over to a float 16 data type. Okay. So that is a 2-dimensional, and we could create even a 3-dimensional, just like we've done before with 3-dimensional NumPy arrays. So we have this is basically every entry in this tensor is a matrix itself. So we have 3 matrices. Each matrix is 2 rows and 5 columns. That's what these dimensions really represent. So we have one matrix here, one matrix here, and one matrix here. So we have 3 of them. Each of them are 2 by 5. And so we get a shape of 3 by 2 by 5. So 3 dimensions are actually very popular in TensorFlow because usually the data will be in either 3 or actually a lot of times 4 dimensions, because this first dimension may represent like a batch. Like we may have 100 images, and each image is this resolution, which is maybe like 28 by 28 resolution, like as a matrix. So 3 dimensions is actually very, very common for a tensor. And actually 4 dimensions is also very, very common because the first dimension is still the batch, but every image may be a 28 by 28 resolution and then have like 3 color channels like RGB, red, green, blue. So 4 dimensions is actually pretty common. 100 images, each one is 28 by 28 with 3 colors. This is actually, so 4 dimensions is actually very, very common in TensorFlow when we're working with data and building like image-based networks that have color images. It's actually pretty common to see 4-dimensional data. Okay, now what's nice about tensors is you can actually go back and forth between tensors and NumPy arrays. So all you have to do is just call dot NumPy on it, and this will convert any tensor over to a NumPy array. So this is a NumPy array, and the TensorFlow float 16 just converts over to a NumPy float 16 type very seamlessly. So it just retains that kind of type just in NumPy. Okay. So if you ever want to convert for whatever reason, maybe you want to manipulate that tensor in NumPy directly, you could just call dot .numpy on it, and it will turn that tensor into a NumPy array with the same shape. So now we have that two-dimensional array there. Now, as you can imagine, there's of course going to be operations between tensors, which needs to happen in order to do matrix manipulations and to do those kind of like weighted sums through activations and all the kind of computations that we need to do. There has to be mathematical operations between tensors. They need to support that in order to do any kind of meaningful computation with the neural network, right? So what you can see in this example is just some examples of adding, multiplying, and doing matrix multiplication between two tensors. So we have two tensors, which are 2 by 2 rank 2 tensors, and we can add them together, which will do an element-wise addition. We could multiply them together, which will do an element-wise multiplication, or we can do a traditional matrix multiplication, which is that, remember, matrix multiplication is that row by column dot product, constructing a new matrix out of that. And we can do all of those operations. So this makes sense. This, like, TensorFlow needs to support these kind of operations to do any meaningful kind of manipulations, right, of underlying data. Again, will we need to do this? Like, no, we won't really need to do this because this will be handled under the hood by the high level library like Keras. They will, in TensorFlow, will manage doing all these computations. But when they do those computations, this is what they're doing under the hood: multiplication, matrix multiplication, addition, passing it through an activation. All those kind of operations are managed by TensorFlow, which is really nice. It has other operations as well, things like finding the max, which makes sense because sometimes we need to find the max in order to calculate like the maximum probability or find out which class something should be, which is the argmax. So this is finding the index where the maximum is. That's an important operation for figuring out like which entry in this array has the highest probability. That's the class prediction is the argmax. And then what I wanted to show you too is the TensorFlow has built-in activation functions. So you can see one of them here, and we're going to get into a bunch of them when we start building our neural nets, is like the softmax activation. So you can see we take this tensor C, which is a two-dimensional tensor, and we actually compute the softmax of it, which will normalize it right into probabilities that total up to 1 across the rows. So because it's 2 dimensions, the softmax will make sure that like this adds up to 1, and then this adds up to 1. So every row adds up to 1. So this is just an example of applying an activation, like a softmax. Notice where this comes from is the RNN module, which is the neural net module. So that's from its built-in neural net module. It has a bunch of stuff like layers. It has a bunch of stuff like activations, those kind of things. We'll talk more about that as we get into Keras. By the way, have you guys been able to run the notebook? All of these steps have ran for you guys. Hopefully no issues. We're not doing anything fancy yet, just manipulating tensors, which are, hopefully you guys can see, are mostly acting like a data frame or a NumPy array, mostly acting in the same way. Okay. And then finally, just like NumPy arrays, TensorFlow does support broadcasting. So we've talked about broadcasting before when we did NumPy arrays. Essentially, if you take a vector, or in this case, I should say a tensor, and multiply it by a constant, then that will just apply that constant to every entry in that vector, which makes sense. And then otherwise, like if you multiply this times this, it'll just do an element wise. If you do, if you try to multiply different shapes together, it will attempt to broadcast to make the shapes fit, and it will give you an error if it cannot do that. So most of the time it's going to try to do element-wise multiplication and then attempt to do some broadcasting if the shapes don't line up, which we saw exactly, the same exact thing happened with NumPy arrays. So that's not entirely shocking that TensorFlow would support broadcasting in some way. So a couple more operations. You can actually reshape tensors, which sometimes is useful that for tensors to be reshaped, and sometimes that'll happen underneath the hood of TensorFlow, anyways. Like it needs to do a reshape to uh, manipulate properly. So we can take this tensor and kind of reshape it into a 1 by 3, which if you print it out would now would just kind of transpose it essentially from 3 by 1 into 1 by 3. Um, so what I hope you're seeing with this, and part of the reason to go through this is I hope what you're seeing is a lot of the same stuff that we had for data frames and NumPy arrays is really carrying over to tensors. In fact, it's kind of inspired by that. When Google made TensorFlow, they were kind of inspired by what was already out there in terms of NumPy and Pandas. So it makes sense that they're going to carry over a lot of the same operations like reshape and having things that look like NumPy arrays and Pandas data frames. That makes sense. Um, Finally, there's technically in TensorFlow, they have different types of tensors. Like you can have what's called a ragged tensor, which is basically allowing for different size dimensions. So you can have, instead of requiring everything to have the same number of columns, essentially like this first row has 4 columns, but this next row only has 2. This next row only has 3, and then this last row only has 1. So we basically pack that in as kind of like a list of lists in this what's called a ragged tensor. We won't really ever have a use for using ragged tensors, but just to say that TensorFlow supports having different size arrays inside of a tensor object. You can even have strings inside of a tensor. So you can see here, this string gets stored here, and you can see its data type is string. So it is possible to manipulate strings. That's not very common because most of the time when TensorFlow is manipulating strings, they'll mostly be like in an LLM, they'll be converted over into vectors before they're ever manipulated. So very rare you would actually directly be working with strings inside of TensorFlow, but it does support, you can actually put in string data into a tensor and it can hold that data, it just won't be able to do much with it until it's converted over to a vector, which is what we see with kind of language models. They tend to convert strings into vectors before doing any manipulation with it. But, we'll learn about that later. All right, so let's talk about Keras. So just a reminder of what Keras is. It's basically an interface built on top of TensorFlow to help us build and train neural network models without having to go into the weeds of the graph interface of core TensorFlow. So it's very, very nice in that way. It's really easy to use, really fast to build models and train them in terms of getting up and running with it, really user friendly. That's what it was built for, is to be really user friendly. And so it's kind of everyone's preferred way of interacting with TensorFlow, if you can, because it's so nice to use, as we're going to see. As I said earlier, unless we're doing very, very sophisticated research, there's no reason we shouldn't be using Keras, and people generally prefer using Keras. It's so nice to use for building and working with neural nets. So of course it's in Python, and it now Keras also does the same thing as TensorFlow in the sense that it allows us to use GPUs relatively easier, or easily, I should say. And it's really, really easy to basically prototype and build your neural nets and get up and running really quickly that way. So I think one of the ways to think about Keras is I used the analogy earlier of kind of like how we have pandas sitting on top of NumPy. The underlying data in a data frame is technically stored in a NumPy array. But we don't work with it in a NumPy array style. We work with it in a data frame because when it's in a data frame in Pandas, there's so much we can do with that data frame from a Pandas perspective, right? We can manipulate it, we can aggregate it, we can join it to other data frames. So many things we can do with a data frame that we cannot do with just a basic NumPy array. Same thing with Keras. There's so much we can do with Keras to help us build neural nets and train it, that it's sits on top of TensorFlow and the underlying tensor graphs, and it just abstracts that all away for us and focuses on the core things we care about, like layers, loss functions, setting up the training and all the hyperparameters around training. So it makes life so much easier than working with just the underlying TensorFlow, which can be challenging and take more time to ramp up to, for sure. Basically, as I said, Keras acts as an interface for it, and we only need a few lines of code to get up and running building any neural nets, which is really awesome. So Keras actually has extensions to other deep learning libraries. So not that we need to know that, but Keras has been extended to be an interface to many other backends that are neural network libraries. So many of them are way less used in the community than TensorFlow. So of course, we're going to focus our efforts on working with Keras as an interface to TensorFlow. But these guys here are other deep learning libraries that Keras has support for as well. But they're not nearly as popular as PyTorch or TensorFlow. Unfortunately, there's no Keras version for PyTorch, but that's okay because PyTorch is kind of has its own abstractions on top of the underlying tensor graph structure of PyTorch. So we'll learn about that in lesson 6. So just to say, Keras has grown really popular and has been extended to other deep learning libraries, but the other ones on this list are not nearly as popular as TensorFlow. TensorFlow kind of dominates the industry along with PyTorch. PyTorch and TensorFlow blow away all these others in terms of their usage. So just continuing the theme here of being really nice, time saving. We don't have to go into learning the underlying core TensorFlow, which I think from like a learner perspective, from your guys' perspective, is so nice. You don't have to spend a lot of time getting ramped up on the nuts and bolts of core TensorFlow, which is really challenging. It's not an easy library to understand. But Keras is really easy to work with. So it makes it really user friendly to get up and running. We just talked about this. Many backends are supported from TensorFlow or from Keras. And one of the reasons is, like, as I said, before TensorFlow was open sourced, a lot of people were developing their own neural net libraries. So these have been around, like Theano, MXNet, CNTK, which is from Microsoft. These are neural net frameworks that a lot of people were building because they needed them to be able to manipulate or to build their own neural nets. But TensorFlow emerged and PyTorch emerged as the dominant libraries. Keras is the main way that we interact with TensorFlow, which is why we care about Keras. But Keras has extensions to be able to work with other neural net libraries. It's just those others are a fraction of what we see PyTorch and TensorFlow being used for these days. Okay, so no need to keep selling you on it. Keras is really important, and of course, that's what we're going to be using here initially to build out our models and train them. So all of the things we've talked about. The other thing is it has really good documentation, and a good, solid open source community. Keras is open source, just like TensorFlow is. So it has really good support for people maintaining it and building out documentation and things still to this day. Okay, so we've talked about all of this. We've talked about how user-friendly and how easy it is. Quality documentation we just talked about. In fact, I'm going to show you some of the documentation coming up before we finish today, so you can see kind of what that documentation looks like in terms of a way to see all of the layers that are available, a way to see all the activations that are available, the way to see all the loss functions that are available from Keras. So I'll show us that. Multiple backends we've talked about, but we don't really care about that because we're going to be using it with TensorFlow primarily. One thing that's cool is just like underlying TensorFlow, Keras has easy ways to access pre-trained models, which will be important in like computer vision or even in NLP to grab models off the shelf so we can kind of use them for our use cases. So that'll be a nice feature. Keras allows us to work with GPUs. It can even work with multiple GPUs if you have them. So that's also really nice. And it makes sense. Like underlying TensorFlow supports that. So of course, Keras is going to make it easy to do that too. Okay. So let's start getting into some of the elements of Keras that we are going to use to construct our neural networks. So the first place to start is going to be the layer class. Now, there's many different versions of layers that are inside of Keras, and I'll show us a documentation of that later. But a layer is a fundamental building block of any model. And so when we build a layer, one of the things we need to decide when we build a layer is how many neurons do we want in that layer? And so that's going to be an important input. The other input that we'll typically need when we construct a layer is the activation. So what activation do we want to apply to this layer? Do we want to apply ReLU? Do we want to apply softmax? Do we want to apply sigmoid, hyperbolic tangent? What activation do we want to have inside of all of these neurons across this layer? So that's going to be important. And what's interesting is we will be able to connect layers together inside of a neural network. So when we build a neural net, we're going to be building out basically declaring layers and then connecting them together inside of this network structure. So we're going to see that in Keras, but the fundamental building block is going to come from this module right here, the TensorFlow Keras layers, and then there's going to be many different kinds of layers that are possible. This is just a generic layer, but there's going to be many different kinds of layers that are available for us to use. For example, there's going to be recurrent layers, convolutional layers. There's going to be attention layers, like in a transformer. The most basic kind of layer that is basically like a perceptron is known as a dense layer. So dense is the most basic kind of layer, and we're going to be using dense almost exclusively for now. So what a dense layer is basically like a perceptron. A dense layer just takes a weighted sum and passes it through an activation. So it's just a feed forward kind of layer that's just doing the most basic thing any neuron could do, which is weighted sum through an activation. So a dense layer is the most basic, but that's not to say there's other kind of layers. There's many different layers that we will see when we build our models. As I just said, convolution, attention, recurrent, LSTM, there's all kinds of layers, and I'll show us the documentation of what layers are available. But this is the one we're going to focus our attention on is the dense layer. It models just a weighted sum going through an activation. It models a collection of neurons where every neuron is just a weighted sum going through an activation. So this is going to be our most basic kind of layer. In the inputs for a dense layer needs to be number of neurons, usually number of neurons, and then the activation function. Again, we're going to see this inside of the code, but these are the two things we typically will declare when we build a dense layer to basically say, okay, this layer is going to have 20 neurons, or it's going to have 10 neurons, or it's going to have 256 neurons. And all of those neurons are going to have ReLU activation, or it's going to be softmax activation, or it's going to be sigmoid activation, whatever activation that we want to supply. Okay. So again, that's going to be tf.keras.layers.dense for us. Until we get into computer vision, we'll use something like a convolutional layer, or we get into RNNs, a recurrent layer, or in transformers, an attention layer, things like that. But right now, we'll mostly use dense, which is just the most basic kind of layer you can have. That's just basically short for feed forward, which means weighted sum through an activation. Okay. So we need layers and we also need models. So models will allow us to connect layers together. So think of the model as the overall network. So what we're going to do typically, the typical pattern is you declare a model and then add layers to it that will be connected together. Think of the model as our basically our object that contains our neural net. Our neural net is the model, and then within the neural net, obviously, are all of our layers with our neurons. So those are connected together, and then they generate all those connections by automatically under the hood whenever we add them to the model. And something that we'll see is that we can add them into the model sequentially, which means that they will be connected together in that order, meaning like we want this layer first, then we want this layer, then this layer, then this layer. We can also do it recursively, meaning we basically say, here's my starting point, here's my ending point, and I want you to connect everything in between, all the layers that I've declared in between. I'll show you both of those ways of building the model. But we need, typically for any neural net, we need an overall model object, and then we need layers to be, every model has layers inside of that model object. Okay, and then we'll just need a way to connect those layers together, which I'll show you how to do. But the model has some very important functionality to it. Mainly, it has these two functions, which are going to be really, really critical for us, such as the training. So every model has a fit function, which executes, this just executes the training. And then every model has a predict function, which now, does this look familiar to us? Hopefully it does. Fit and predict. What do you think that's inspired by? That should hopefully look familiar, right? A dot fit and a dot predict. That should look really, really familiar to us. And it's actually no surprise that they chose those words specifically, dot fit and dot predict. Those are directly inspired by scikit-learn, right? sklearn. Every model there had a dot fit and dot predict. Really no different here. When we build our neural net, training, it's actually just going to be a matter of executing a dot fit. The difference is when we execute that dot fit, we need to set a bunch of stuff up. We need to set up what the loss function is. We need to set up what our gradient descent algorithm is. And there's a lot of hyperparameters there that are involved in the fitting of a neural net. So this dot fit is a little more complex. And the predict is also kind of complex because under the hood, what predict is doing is forward propagation, right? It will generate the output for whatever input data we pass in. So it's just forward propagation is essentially this dot predict. It also has a convenient evaluate function. Every model has an evaluate function. which basically gives us back the loss. So we evaluate on a collection of data, and it basically gives us what the loss and any like accuracy metrics that we set up. So what's our precision, recall, accuracy, confusion matrix, those kind of things whenever we apply our model to some data that has labels. So assuming we have labels, we can do an evaluation, which is like what is our loss, and whatever any metrics we declare like accuracy, we can produce those pretty easily. So again, I'm going to show us all this in the code. I'm just trying to orient us right now into the different elements of Keras that we really care about. So right now we have two, which is the layers and the models. We care about those two primarily in order to build and train a neural net. There's going to be other things we care about, like declaring a loss function, declaring activations, those kind of things. So, there's other small bits that we're going to see along the way. But at the highest level, like the two things we care about are the layers and the model that holds the layers, that holds our neural network layers. Okay. Okay. So as I kind of alluded to, there's two primary ways of building models, which is going to be sequentially or recursively, also known as functionally. So sequentially is the simpler way of the two, which I think is a really good way to get started with model building, because it allows you to create models basically layer after layer after layer in a linear sequence. So what that means is you basically declare that you basically build a list and say in this list, this layer goes first, then this layer, then this layer, then this layer, which for some models makes a lot of sense. Like if it's a very simple model, that's really all you want is you want to say, okay, I have this layer, then this layer, then this layer, and it's going to go forward through that sequence, right? From layer after layer after layer, which is very natural. That makes sense. So the sequential way of building a model is kind of the simplest way to do it. But the recursive way to do it, or what I should say, the functional way to do it, is a little bit more flexible in the sense that it allows you to have layers that can be shared and non-sequential. So for like recurrent nets, that's really important. So what we're going to see I'm going to show you examples of both. We're going to build a model sequentially, and we're going to build a model using the functional API, so that we can get exposed to both. But most of the models we'll do to begin with, we can get away with just doing sequentially because they're actually going to be very simple. It's not until we start building some more complex models that the functional will be actually better for that case. But the functional allows us to have kind of exotic structure, because all we need to do is basically say how one layer acts on another layer, and we can connect all those kind of recursively. And so it gives you a chance to do things non-sequential because you can have a layer that's further down the line act on an earlier layer by having like a recurrent connection back to the previous layers. And you can do that in the functional API when you cannot do that in the sequential. So I'm gonna show us both ways. Both are widely used. I think both, like when you're building something relatively simple, I think sequential is the easiest for a reader to understand and see. But if it's anything that's complex, you're almost always going to be using the functional way to do it, because you have to. You can't really get away with doing sequential because you're not going to have a flow that's just directly and feed forward. Sequential is basically only for feed forward where things are guaranteed to go from one to one to one to one to one and just go forward, which for us in the beginning is going to be the case. That's all we really care about in the beginning. But as we get to more complex models, we're going to need that functional way of doing it. Let me give you an example. So let me give you an example of what the sequential way of building a model looks like. And this is actually a very prototypical case where you build your model as a sequential object. So you can see directly here we initialize a sequential model using the sequential object here. And look at what we pass in is a list. So inside of the sequential is literally a list of layers. That's what the sequential model takes. And it's purposely a list because what the list signifies is this layer should be first, and then this layer should follow it, which is exactly what we've seen in our drawings, right? Like there's a layer that's first on the left, and then that flows into a layer on the right. So it's sequential. It's this layer and then this layer and then one more layer and then one more layer, right? So sequential is just kind of for exactly those use cases we've been drawing. What I want you to see here is an interesting, very simple model, but what it's saying is here's our dense. So here's where we're using that layer. So we have a list of layers. Here's that dense, which is the most basic kind of layer we can have. What that means is I have a bunch of neurons. How many neurons do I have? I have 64, which is a choice. So I can choose how many neurons I want in that layer. So we're declaring 64 neurons to be modeled in that layer. And what we're saying here is there's an input shape, meaning the input data to this initial layer is this size. So this is just orienting the network to say my input layer is going to be this shape. So I should expect data to flow into this network that's this exact shape. So that's however many dimensions it is, which would be like however many features we have. For example, like if we had 20 features, that input dimension would be 20. But this is saying we have 64 neurons, and the activation of every one of those neurons is a ReLU activation, which is pretty standard, right? A ReLU activation is pretty common. And then here, now what this is signifying is this layer flows into this layer because it is next in the list. So the outputs of that layer flow into this layer, which has 10 neurons and a softmax activation. Now, what does that mean? That means that we are likely predicting 10 categories because I have 10 outputs, which are softmax activated. So that means they are all going to be probabilities. And not only that, they're all going to be probabilities that total up to 1. So this is likely, and by the way, this is the output layer because it's last. In the sequence, in the list, it is last. So it is the output. There's nothing else. It's not connected to anything else, right? So this has to be, so the last layer in the sequence is our output. It has to be. There's nothing else beyond it. Last layer equals the output. And so you can actually see this is a model. This is going to be a neural net that is designed to predict 10 different classes. It's providing us a probability for 10 different classes. So for example, this could be used for something like the MNIST data, right? It could be used for something like that where there's the digits 0 to 9, which are 10 different categories, right? That could be used for something like that. I'm just throwing that out as an example, but hopefully this makes sense. What you're seeing here is 2 layers. You have really this initial hidden layer with 64 neurons, and then you have a output layer that is size 10 with a softmax activation, meaning you're going to produce 10 probabilities. So it's a this is likely a network that's used for multi-class classification. But look how easy it is this is our network, right? This is our neural net. This here is our neural net object. Look how easy that is to create in Keras. It's just a sequential with some layers. That's really all it is a sequential and a bunch of layers. Okay. Let me show you the difference with the functional API, and you can see the difference, but hopefully it makes sense. Now, this is the exact same network. It's just built in the functional API. Exact same network, though. It's just going to look a little different. So what we do in the functional API is we actually are going to declare an input layer as the very beginning. So we explicitly define an input layer, which is this. Same thing though, it has a particular shape, but notice there's an input layer we're explicitly defining in the functional. And the reason we're doing that is because when we build a model, we need a layer to tell it where to start. We basically need a starting and stopping point. So this first layer is our starting point here. So we start here with this input layer. Now, what I want you to see is we now declare a dense 64 activation, but look at the notation of the code. We are basically applying this layer almost like a function, right? Almost exactly like a function. What are we applying it to? The input layer. That's really critical in the functional setup because what this is saying is I want to take this layer and apply it to this layer, which is the input layer. Now, if you look at the next layer, this is our dense 10 with the softmax. So this is our output. What are we applying that to? We're applying this to our hidden layer, which is what we declared here. So do you guys see how this is more functionally defining how layers act on each other? This is rather than building it in sequence, we're saying, okay, this layer acts on this, and then this layer acts on this. All we need to do then to build the model is to instantiate a generic model and tell us where the starting and stopping point is. And what it will do is connect everything together because we've already declared how they all act on each other. So what we're doing here is saying start here and end here. So we're saying our output should be here. And because we've specified out everything acts on each other, this model is going to recursively go through and build the graph because it knows how everything acts on each other. It knows that the input layer is an input to this, and it knows that the hidden layer is an input to this. So it's going to connect all those together in this model here. So it's a different way of declaring it, but it's the same exact model. But this is just the functional way of doing this. Now, you might ask, why would we do it this way rather than the sequential? It's because you now have an opportunity to build more complex architectures in this way of coding it. You have an opportunity to build in a much more complex architecture because what you can do is you can have things be shared. You can basically say, I want to take one layer and add it to another layer, like plus another layer. You can do things like that, which in more complex architectures, they actually do. And we're going to see that later on when we get into like convolutions and recurrent nets. Okay. Okay, so just to compare and contrast again, the sequential is mainly for a linear stack of layers, which is literally in that list. Usually because of that, it limits itself to simple models, limited customization, very simple models that you can get up and running. Again, which is going to be like in the beginning of when we're learning this, that's mostly when it's going to be applicable. But the functional has very high degree of customization, which lends itself well to complex architectures, which is going to be useful down the road when we get into those kind of networks. I think it's good to know both, and we will see examples of both for sure.
And that brings us to the end of this deep learning specialization session. In this video, we started from the fundamentals of deep learning and moved step up into neural networks, artificial neurons, perceptrons, activation function, loss function, gradient descent, and backpropagation. We will also explore how to build and train models using TensorFlow, Keras, and PyTorch, and how these frameworks help us solve real classification problems. The key takeaway is simple. Deep learning may look complex at first, but once you start understanding neurons, layers, laws, and optimization, you can start building powerful AI models with confidence. If you found this video helpful, make sure to like, share, and subscribe to Simplilearn for more such videos on artificial intelligence, machine learning, deep learning, and the latest tech skill. Thank you for watching and see you in the next session.